involved other people, and I'll refer to these papers as we go along. So our basic aim is to try to prove the ADS-CFT correspondence. And in order to explain to you our strategy, let me remind you very basically of what the relation between the parameters on the string theory side and the dual CFT side are. So what's important in particular is that we're going to be at large n, as always, and then the TUF parameter, that's the effective coupling constant of the gauge theory at large n, is related to the radius or the ADS space in string units. So this is the key relation that will be important for the following. Now, in order to prove the ADS-CFT correspondence, if you really want to have both sides under control, you have to be in the weakly coupled gauge theory regime in order to have the gauge theory side under control. And this therefore means that the TUF parameter will be small, and as a consequence, the radius in string units will be small, and that's what's often referred to as the tensionless limit. That's the limit in which the size of the string is very, very large. It's as large as it can become, namely as large as the space in which it propagates. So this is what happens on the string theory side when you are at weakly coupled gauge theory. Now, this is the regime where ADS-CFT becomes perturbative or has a chance to become perturbative. And let me explain to you what I mean by this. So on the gauge theory side, we are weakly coupled, so that's clearly as a perturbative description. Now on the string theory side, as I've just explained to you, the radius will be very small in string units, or the string size will be very large. So you're very far away from the supergravity regime. So this is certainly not a regime that's perturbative from the supergravity perspective, but the idea is that the string theory side has some other redeeming feature that makes it into a tractable theory. And in particular, as has been long argued for, the dual of free Super-Mills should describe some theory with a higher spin symmetry. And in some sense, you should think of it as being the maximally symmetric phase of string theory. So our working hypothesis is that what makes this theory perturbative should also have some imprint on the string theory side. And the imprint on the string theory side should be that while supergravity is not easily describable, there should be something very simple about the worldsheet description corresponding to this very special background, namely to the one that describes free Super-Mills. And the idea, our basic working principle, is that this worldsheet theory will be free, or will be at least solvable, exactly solvable. There should be something that refers to the fact or corresponds to the fact that something very special happens on the gauge theory side. Now, this is our working hypothesis, and we have very good evidence that this is indeed how it works out, at least for the example of ADS3 cross S3 cross T4, where we have a very detailed analysis. And let me briefly remind you of what the status of this is. So, as many of you know, string theory in ADS3 cross S3 cross T4 is dual to a two-dimensional conformal field theory living on the boundary of ADS3. And this two-dimensional conformal field theory is a conformal field theory that lives somewhere in the moduli space that also contains the symmetric orbifold of T4. That's the old folklore of ADS3 CFT2, as already pointed out in the original Maldacena paper. Now, what's the analog of free Super-Mills in this context? Well, the very natural idea is that the analog of free Super-Mills is the symmetric orbifold theory itself, i.e. the theory that is really the symmetric orbifold of T4, rather than some other CFT that is on the same moduli space as the symmetric orbifold of T4. Because you see, this is basically 4n free fermions and free bosons modulo some global conditions. So that's basically a free theory. So our idea is that this should be dual to some special tensionless string dual. And the idea is that what this should mean, if you believe that it could be described among the string theories that has pure Schwarz background, then you would think it should correspond to the background with a minimal amount of NS and S flux. And that theory has a description in terms of the hybrid formalism of Berkowitz, Buffer, and Witten that involves a Wess-Witten model based on the super Lie algebra PSU 1,1/2 at level 1 if k is equal to 1. Now, what's special about that theory is that this special super F-Heinrich-Moody algebra has actually a free field realization in terms of free fields, namely symplectic bosons, and I'll explain to you later on what that means in detail, and free fermions. And what we checked is that the physical degrees of freedom of this worldsheet theory, once you include spectral flow, as we know, one has to, when one describes string theory in ADS3, reproduces exactly the single particle spectrum of the symmetric orbifold theory. So the spectrum of the dual CFT is exactly accounted for by this worldsheet theory. So so this is the story for ADS3 cross S3, where we have checked many things, and I'll briefly review it in the following. But our basic tenet is that somehow the story for ADS5 cross S5 should work similarly. So what we propose is the dual of free n equals to 4 supermills should also be characterized by a free worldsheet theory. And the free worldsheet theory should be one where instead of PSU 1,1/2 at level 1, we'll have PSU 2,2/4 at level 1. The simple reason being that the zero modes of the super affine Kac-Moody algebra will be the global symmetries of the dual CFT, and PSU 2,2/4 is the superconformal symmetry of n equals to 4 supermills. So that seems like a reasonable idea. And then you realize that this has a free field realization in terms of fields that look very similar to the fields that appear in the twistor string that Berkowitz proposed many years ago. So that seems like a very good starting point. You make contact with the twistor string, and at the same time, you manifestly produce the correct symmetries to correspond to the dual CFT. Now, the key ingredients, as for the case of ADS3, are spectrally flowed representations, and I'll explain to you in detail later on how they come about. But the upshot is that there is a natural quantization. We haven't understood all the details of it, but there is a very natural idea of how you should quantize this theory, and it leads to what we call a reduced model. And this reduced model reproduces exactly the single particle, that's a single trace spectrum of free supermills in the large n limit. So this is showing that what we believe to be a good sign that we are on the right track. Okay, so this was the brief overview on where we want to go. So let me now try to review briefly what we know about ADS3, what we've learned about ADS3, and then I'll try to explain to you how the generalization to ADS5 will work. So the ADS3, I'll try to keep relatively brief because this really uses results that have been described at previous string conferences. So ADS3 cross S3 you can describe in terms of a RNS formalism a la Mendocino-Oguri, but there's also this hybrid formalism of Berkowitz-Vafa-Witten, and in that context, you have the super Lie algebra PSU 1,1/2 at level k, where k is the level of the SL2R in the NSR description of Mendocino and Oguri. And as I said before, we are interested in the regime where k is equal to 1, and then this has a free field realization. But to be precise, you don't get a free field realization for PSU 1,1/2. You get a free field realization for U 1,1/2. And that is in terms of what I called 4 symplectic bosons and 4 real fermions. So the 4 real fermions, you recognize, this is just the standard fermions that you have. And what I mean by 4 symplectic bosons is what you may want to call maybe a beta-gamma system of spin-a-half. These are boson fields, but they satisfy exactly the same commutation relation as the fermions satisfy the anti-commutation relation. Now, what you can easily show is that the bilinears of the suitable bilinears of these fields generate U 1,1/2 at level 1. And then in order to go to PSU 1,1/2, we'll have to gauge by some diagonal U1 field. And that's the diagonal U1 field by which we gauge in order to get PSU 1,1/2 at level 1 from U 1,1/2 at level 1. Okay, so that is the fields that our theory has. Now, these are free fields. So when you would naively ask, what is the representation theory? Well, you can either put them all in the Neveu-Schwarz sector, or you can all put them in the Ramond sector. And in fact, these are the only highest weight representations which this theory has. So the Neveu-Schwarz sector will not play an important role in the following. So let's concentrate on the Ramond sector. And it basically looks, if you picture it, it looks a little bit like that. So you see you have some ground states along which the zero modes move you up and down. And then you can, the negative modes just generate all the excitation modes. And here I've put down L0, and I've called it L0 of tilde for reasons that will become apparent in a second. And I've included J30, which is the Cartan generator of SO2. And the ground states, they form what you would call the singleton representation of PSU 1,1/2 if you think about them in terms of the PSU 1,1/2 generators. Now, these are highest rate representations, but as we learned from the work of Mendocino and Oguri, one of the key insights is that in order to describe string theory in ADS3, you can't just have highest rate representations for the ADS3 factor. And the reason is basically a simple one. You see, you have to have arbitrary excitation number to get a string spectrum, and therefore the L0 spectrum can't be bounded from below. And in this context, what it means, you need a theory that has an unbounded L0 spectrum, so as that to satisfy the mass shell condition, you can still have arbitrary stringy excitations. Now, what they proposed is that the additional representations you need are most easily described in terms of spectrally flowed images of, in our language, this Ramond sector representation. So what this means is we think of this same space, and it's a standard representation with respect to the tilde modes, but then we use some automorphism to write, to express the tilde modes in terms of untilde modes, and the untilde modes differ from the tilde modes only by virtue of the fact that their mode numbers are shifted up and down by W/2 in such a way that the commutators and anti-commutators are preserved. And then the idea is that you take this one and only representation with respect to the tilde modes, and you interpret it as a representation with respect to the untilde modes. In particular, the PSU 1,1/2 generators, including L0, well, L0 isn't strictly part of PSU 1,1/2, but it's part of the Virasor algebra, you can work out. And what you find is that in this space, L0 looks as such, and in particular, the states with L0 equal to 0 are the states along this line. So what you recognize in particular is that you have all these states here below this line, and obviously this continues ad infinitum, that have a negative eigenvalue of L0. So the L0 spectrum is unbounded from below. And what you've done by this spectral float trick is to produce a new class of representations that are not highest rate anymore. And that's what you need in order to get a sensible string spectrum. Okay, so that's basically just reviewing Maldaceno-Gori in this context. Now, what's special about PSU 1,1/2 at level 1 is that it has many, many null vectors. And one way to think about it is, you see, it has 4 symplectic bosons, but then you have to impose this U1 condition. And this U1 condition basically kills 2 bosons. So out of the 4, you only retain 2, but then you also have to impose the physical state conditions, as you always have in string theory, that will also eat 2 bosonic degrees of freedom. And what you learn is that there are no degrees of freedom surviving from the ADS3 cross S3 factor, and all that you left over is the T4 factor. And if you analyze it, what you find is you get the symmetric orbifold of T4, exactly the single particle spectrum of the symmetric orbifold of T4, where the W cycle twisted sector of the symmetric orbifold comes from the W spectrally flowed sector on the Worldsheet. And this is something Lorenz talked about at Strings in 2019. So this is as regards the spectrum. Let me also briefly mention that the correlation functions of the symmetric orbifold theory are reproduced on the Worldsheet, and that comes from a remarkable property of the Worldsheet correlators. So the Z's are the coordinates, the usual coordinates on the Worldsheet, and the correlation functions on the Worldsheet have the remarkable property that they are delta function localized. So they're mostly 0, except at isolated points where they have delta function support, and they're localized to those configurations that admit a holomorphic covering map, i.e. a map from the Z's to the X's, such that Zi gets mapped to Xi plus a correction term of the order Z minus Zi to the Wi. This is a very restrictive condition, and as a consequence, you get a discrete sum over delta functions localizing to these covering maps. Now, the nice feature or property of that is that if you then do the modular integral, these delta functions guarantee that you only get a finite sum. You get a finite sum over the covering maps, and that basically reproduces the structure of the symmetric orbifold correlators. And thereby you see that manifestly our Worldsheet description gives rise to the correct correlators of the symmetric orbifold. And this is something Rajesh talked about at Strings last year. Okay, so this is my lightning review of ADS3, and now we want to generalize this to ADS5 and basically take the same building blocks and try to modify them so as to fit the ADS5 cross S5 case. So our working hypothesis is that what we should do is we should start with 8 symplectic bosons and 8 real fermions. And as I'll explain to you, they'll generate U2,2/4 at level 1, and then you have to divide by some U1, and then you get PSU 2,2/4 at level 1, and that basically guarantees you, as I said before, that you get the correct space-time symmetry. So what does this Worldsheet theory look like more concretely? So we have to have 4 plus 4 symplectic bosons. So we organize them in 2 pairs. So there's a spinor index A alpha and a spinor index alpha dot. So we have 4 that are 2 doublets under alpha, 4 that are 2 doublets under alpha dot, and they satisfy the symplectic boson commutators as we had before. And then we have 4 fermions that sit in the fundamental and anti-fundamental representation of SU4, and they just satisfy usual fermionic anti-commutation relations. So that's our proposal, and as I mentioned before, that looks very, very similar than the field. In fact, it's essentially the same field content as the twistor description of Berkowitz. Now, the bilinears, when you take one generator out of the Y's and one generator out of the Z, they generate U2,2/4 at level 1. And in order to reduce this to PSU 2,2/4 at level 1, you have to gauge by an overall U1 field. And the overall U1 field you have to gauge by is this diagonal version. That's the generalization of what we saw for PSU 1,1/2. In fact, this construction is something that's also not that surprising, because this is really the affinization of the standard oscillator construction of PSU 2,2/4 that appears in the standard spin chain discussion. So in the spin chain discussion, you would just look at the zero modes of all of these fields. You would do exactly the same thing. You would get PSU 2,2/4. Here we use at the full non-zero modes, and you get the affine version of PSU 2,2/4, namely PSU 2,2/4 at level 1. Now, as for the case of ADS3, all the non-trivial aspects will come from spectral flow. Now, for ADS3, I said you have to shift the mode numbers up and down. And what distinguishes whether you shift them up and down was the eigenvalue under J30 minus K30, where J30 is what becomes the conformal dimension in the dual CFT, and K30 is the Cartan generator of SU2. Now, for SU5, ADS5, the natural analog is that you should take the dilatation operator to replace the conformal dimension and some asymmetry generator to replace the corresponding Cartan generator of SU2. So that determines how you spectrally flow these different fields. And then we do exactly as we've done before, except here it's convenient to start from the Lewis-Schwartz sector representation, but that really doesn't make such a big difference. So we impose that the tilde positive modes, the half modes and higher of the tilde modes, kill the ground state, and then you translate this into the untilde modes, and then, for example, this generator, the mu generator, will kill it, provided that R is greater or equal than W plus 1/2. That's the condition for all those that get shifted upwards, namely these guys, and for the other one, it's shifted downwards. Okay, so these are the generators that kill this ground state after spectral flow, but we have a free theory. So all those that don't kill create. That's the rule of a free field theory. So simply the complement of this set will freely generate the Fock space acting on this ground state. So if you think about it, from the first line, you get everybody where R is less or equal than W minus 1/2. And from the second line, you're going to get everybody where R is less or equal than minus W plus 1/2. So everybody will generate where R is less or equal than minus W plus 1/2. And in addition, from the first line, you get generators that lie inside this wedge between minus W minus 1/2 and plus W minus 1/2. Now, this is the Worldsheet theory, and so far we haven't done anything unusual, but now, unfortunately, unlike the situation for ADS3, where we had Berkowitz-Waffer-Witten, who told us what the correct physical state condition is, now we're a little bit on our own. So what's our working hypothesis? So for ADS3, the physical state condition was that the physical states are primary, or the critical states of an n equals to 2, the states of an n equals to 2 critical string. Now, our worldsheet theory is basically twice as supersymmetric because it has twice as many symplectic bosons and fermions, and therefore it definitely has an n equals to 4 superconformal symmetry. And what we want to propose is that the correct physical state condition is that you impose the n equals to 4 critical string. Now, exactly how these n equals to 4 critical string generators look like, we haven't quite worked out, but we think that's a plausible assumption. Now, n equals to 4 algebra has 4 bosonic and 4 fermionic generators. So if you impose that the theory is critical, you kill 8 bosons and 8 fermions. So you would think you kill everything there is. And we want to take this to mean that we kill all the out of the wedge modes. All of these out of the wedge modes will be non-physical by virtue of this n equals to 4 critical string condition. Now, the remaining modes we want to think of as being some generalized zero modes. So in particular, we want to think of them as one copy from the two. So we have left movers and right movers, and we want to postulate is that one copy of these left and right movers survive after imposing the physical state condition. So you kill all of the out-of-the-wedge modes and you keep one copy of these wedge modes. And there is some intuition that this behaves similar to these U1 flux solutions that, for example, Dolan and Goddard wrote down for this Berkowitz string theory. So we believe that is sort of the natural analog of what we are doing here. As a side remark, we've also checked this for ADS3, where we have a more first principles derivation of what the physical state condition is, and we also land on our feet in that context. So that's what we propose. We propose you keep one copy of these wedge modes, and then you still have some residual gauge conditions, which come from the fact that we've forgotten about the fact that we are dealing with PSU 2,2/4 rather than U 2,2/4. So we have to still impose this condition. And we have a mass shell condition, which we take to be of that form. The idea here being that the ground state has the same charges as the BMN vacuum if you identify P plus with W. And then if you take the BMN formula and work at a tensionless limit, then you would think that 2P minus is an integer. So that suggests that this is L0 being equal to an integer times W seems to be the right sort of residual mass shell condition. Anyway, that's what we propose. At the moment, that's a proposal. We don't have a first principles derivation of it. Now, if you take this, then we can show that the resulting spectrum reproduces exactly that of free superangles in the 4D planar limit. So how does this work? Well, you think of these wedge generators as being momentum modes, and you do an inverse Fourier transformation to turn them into position modes. So you have W of these momentum modes. After Fourier transformation, you end up with W such position modes, and they pairwise commute if they sit at different positions. And then the residual gauge condition that Cn is equal to 0 for all n greater or equal to 0 translates into the statement that at each side, you have to set the C correspond to 0. So at each side, you have basically a copy of the usual oscillator construction in the spin chain picture because you just have one generator, and you have to set C equal to 0. So what this means is that at each side, the states in the singleton representation of PSU 2,2/4 survive. You have W side, so you get the W-fold tensor product of the singleton, and then this just imposes cyclic invariance, and therefore you land on the spectrum of free superangles in the planar limit. More specifically, the states in the W spectrally flowed sector correspond exactly to the W letter words, where you see, so the singleton representation has one state for each of the fields of superangles and its derivatives. For each element here, you have a state in the singleton representation. You take W many copies of those, and then you take the cyclic combination that survives in the trace. So that's exactly what the W spectrally flowed sector gives you. So in particular, you reproduce exactly the spectrum of free superangles. And what it suggests is that this is some sort of string bit picture, where in this W spectrally flowed sector, we have W string bits, but the string bits are twistor valued. They take values with these variables Y and Z, unlike what maybe one may have thought of originally. So this is our basic result, that upon this natural generalization from ADS3, we end up with a worldsheet theory, which admittedly there are some hoops and loops we have to jump over, leads to a spectrum that's exactly the spectrum of free superangles. So I try to convince you that the free field realization of ADS3, that is directly dual to the symmetric orbifold of T4, suggests a natural generalization to ADS5 cos S5. Then we've made some assumptions about what the structure of the physical state conditions will amount to. But if you take them, if you accept them, then we can show that the resulting spectrum is exactly that of free superangles in 4 dimensions. And therefore, this theory has a chance to be an incarnation of what we're looking for, namely a theory that describes free superangles. And it's again a free worldsheet theory that therefore fits the bill of what we were looking for. Now, obviously, there are many open questions and things we need to understand better. So first and foremost, we have to understand this physical state condition from first principles. At the moment, this is a bit of an inspired guess. Then we would like to study the correlation functions on ADS5. So remember, the correlation functions from ADS3 have this delta function localization property. And this came all from the Ward identity of the symplectic boson fields. So you would expect that something similar will happen for ADS5. And that ties in with what you expect the worldsheet correlation functions that are dual to free superangles to look like. once we understand the correlation functions, obviously you can start to analyze the perturbation away from the free case and thereby really test this further and see whether we also produce the correct anomalous dimensions. Now, there are also more conceptual problems that would be interesting to understand. In particular, there should be a higher spin symmetry. We see this, but it's not manifest on the Worldsheet. Only PSU 2,2/4 is manifest. There's obviously a Youngian symmetry in the spin chain that should have some implications here. And this suggests novel ways of looking at the spectrum and looking at correlators, and it would be interesting to relate this to other approaches in the literature. But my time is up, so I'll stop here and thank you for your attention.
Thank you. You finished just on time, so. Okay. Ofer Haroni has a question.
Hi, Matthias. I'm not sure if I completely understood how you think this physical state conditions would come from first principles. So I assume you want to have some n equals 4 superconformal gravity on the Worldsheet or something like that. Or sorry, it was n equals 4 supergravity on the Worldsheet. But then on top of that, do you want to just add a single U1 field, or do you need to add the full n equals 4 multiplet of the U1 field? Or what's the picture for where it would come about?
Well, so the picture is that we are, so in the ADS3 case, you have an n equals to 2 algebra, n equals to 2 superconformal algebra, which you build out of the free fields and the ghost fields of the Berkowitz-Waffer-Witten construction. Now here we want to construct a corresponding n equals to 4 algebra out of the symplectic bosons fermions together with the ghost fields, and then we are going to impose that the physical states are the critical states of this n equals to 4 theory. Now, that's just, so that is basically all there is, except that once you removed all the negative modes and you're looking at the zero modes, on the zero modes, you still have to impose some residual gauge conditions. So this condition will not just produce the zero modes. For example, the zero modes don't respect this PSU 2,2/4 constraint. C is not equal to 0. So this condition, some analog of that condition you will still have, but this is only on this wedge modes. This is only the leftover piece on this wedge mode. And likewise, there's a zero mode condition coming from the stress energy tensor. This is some sort of residual gauge condition after the heavy lifting has been done by all the n equals to 4 fields. So this is our picture, but admittedly, we haven't worked this out from first principles.
Okay, the next one is Shota Komatsu.
Yeah, well, actually I had the same question as Ofa, but I can ask a slightly different one. So is there a kind of way to say topologically twist the theory and reduce it to string theory in lower dimensions?
Sorry, say again. I mean, this is meant to be the full string theory. This is not
right. But like, let's say we are interested in more like a restricted sectors. Or put in another way, like, is there any relation between the ADS5 model and ADS3 model?
Well, I mean, in some sense, I've tried to convince you that there is a relation by this being sort of basically what you've done, you've replaced the T4 factor by another free field theory corresponding to. So obviously what you could do is you could try to sort of look at an ADS3 subsector inside it. You could also try to impose some additional topological conditions. Obviously, you could restrict on some sort of BPS sector inside it. That would be some additional cohomology on top of that. I mean, what we are reproducing is the full spectrum BPS and non-BPS of n equals to 4 super nils. So therefore, obviously, you could try to identify some topological subsector in here and identify what it means from the Worldsheet perspective.
Okay, all right, thanks.
Okay, Igor?
Yeah, thanks for the interesting talk. Yeah, I couldn't follow all the details, of course, but I'm generally confused how a local, regular sort of Worldsheet theory can describe weakly coupled gauge theory, because essentially the local Worldsheet theory corresponds to only weak partons, only very soft partons, while in perturbative gauge theory you have, say, a lot of states where the longitudinal momentum, say, is divided between just a few partons. So if you, for example, just look at very naively what happens at weak coupling, you don't see the continuous sigma space that you see in standard Worldsheet descriptions. Sorry if this is vague, but it's a general confusion I have. There has some miracle has to happen for a regular string action to suddenly describe free Young-Mills theory beyond just the state production.
Right. So, I mean, obviously, what we'll have to do is we have to switch on the coupling constant. That's going to be a certain perturbation from the point of view of the dual CFT and a perturbation on the worldsheet. And then we'll have to see what happens to the spectrum. But I mean, the spectrum will stay intact. The question is whether we reproduce the correct anomalous dimensions. I guess our intuition is that it worked very naturally for the case of ADS3. And it combines various ingredients which people have seen in the context of what people believe could be the string dual of ADS5. But obviously, it may not work. But I think it has a fair chance to work, and I think that remains to be seen whether it will work out or not.
Okay, thanks. I'll think about it.
Okay, there's 3 more questions I'm going to allow, and then we're going to move to the discussion, and the questions can be moved to the discussion afterwards. So Mukun, you're next.
Thanks. Matthias, I'm confused about something. So I would have imagined that if you had tried computing the thermal partition function, you should see a Hagedorn transition here, which should correspond, which would be the free Yang-Mills Hagedorn transition. But I'm then confused about the n scaling. Can you explain where the n scaling comes from in this?
Yeah, so that, I mean, we don't have, yeah, so I don't really have anything concrete to say about that at that stage. I mean, we don't have any temperature here. This is just at the free point, and we haven't looked into any of these questions in detail, so I'm afraid I can't say anything.
Thanks.
Shiraz?
Hi, Matthias. Thanks for the beautiful talk. Quick question. If I understood right, you've got a free field realization of your worldsheet field theory with n equals 4 superconformal invariance on the worldsheet and preserving this ADS5 times S5 symmetry in target space. Now, in order to turn on the coupling, this worldsheet theory, I suppose, would need to have a deformation that preserves these properties, right? That preserves n equals 4 on the worldsheet and the invariance of the target space. Is it easy to check whether, is this the correct expectation, and is it easy to check whether it's true?
I think that's the correct expectation. Whether we haven't looked into it in detail, but the coupling constant is a deformation, so it should appear as one of the operators in our worldsheet theory, and therefore that's the operator by which you should perturb the worldsheet theory. And I think that has a chance to work, but we haven't tried to do that. We haven't tried to identify which exact vertex operator you would have to switch on the worldsheet in order to move you away from pre-super Yang-Mills.
Thank you.
Okay. And the last question, Ed Witten.
Can you give us any kind of hint of what the n equals 4 generators are supposed to look like?
Well, I mean, obviously, out of the symplectic bosons and free fermions, you can generate an n equals to 4 algebra. That's pretty easy to see. But that's not the right n equals to 4 algebra, because you have to combine it with the ghosts, just like you did for the ADS3 case. So it'll be some combinations of the ghosts together with the symplectic bosons and the fermions. So what we do is we take the formula of your n equals to 2 generators, we write them in terms of the free fields at level 1, and then we are trying to generalize this to an n equals to 4 algebra. But we haven't found the right n equals to 4 algebra so far.
This n equals 4 algebra is supposed to commute with PSU 4/4, I assume.
Yeah, I mean, so to be honest, we have a little bit of problem understanding exactly how your construction commutes with all of PSU 1,1/2. It commutes with a large chunk of it, but we haven't quite understood how it commutes with all of it. But that would be our expectation, that the n equals to 4 algebra that we find will commute with the PSU 2,2/4 generators, yeah, the global symmetry.
Okay, thank you, Matthias. And then any other questions will be moved to the discussion section afterwards. And I think the discussion section is next.
Yeah, thank you. Yeah, so let's start with the first discussion session of the day on proving dualities. So as usual, 20 minutes of setup. Those 20 minutes, let's try to keep them to 20 minutes. So she and Rajesh, please, 20 minutes. And then the 30 minutes, we are not very strict. We can go a little bit into the coffee break. So that is the more relaxed part. So she, please.
Thank you very much. Rajesh and I will discuss some aspect of proving dualities. I think I will talk about what to prove, and Rajesh will talk about how to prove. And I'd like to begin by reflecting a bit on what string dualities mean and what we actually want to prove. And the reason, part of the reason is I feel like our standard for what a duality is has evolved and improved over the years. And I think it's important to be clear about the content of the duality, what is actually defined, and be careful about things that that are not actually defined and maybe just wishful thinking, and to avoid the kind of circular reasoning. Okay, so first of all, I should say that I'm restricting myself to string dualities. I'm not talking about field theory dualities. Now, string dualities are a little bit different from field theory dualities in the sense that typically field theory duality, we talk about the equivalence between two different theories with different coupling parameters. Now, that kind of equivalence is not a symmetry because it changes the parameter of the theory, a priori, right? Whereas in string theory, these parameters are webs of fields, and the duality is a transformation on the field. So that in that sense, you have a symmetry of the theory, and then furthermore, all the symmetries in string theory are expected to be gauge symmetries. So one notion of string duality is a non-perturbatively realized gauge symmetry. And there's examples of these involve T-duality, mirror symmetry, S-duality, and so forth. And I would say that these dualities are not, this kind of dualities in the sense are not just properties enjoyed by the theory, but they are also essential to the very definition of the string theory. For example, they are essential for the existence of monodromy branes and more general class of string vacua, such as F-theory vacua. So this is one sense of duality we speak of. Now, there are some other kinds of dualities that we speak of that are closely related in various ways, but I would think conceptually slightly different. So another sense of duality is simply when we say that there are different weakly coupling limits of in the same moduli space of string vacua. Of course, there are well-known examples of type 1 heterotic SO32 duality and relation between type 2A and M theory and 11D M theory and so forth. Now, in each of these cases, let's say in the type 1 heterotic duality, we understand perturbation theory in principle from both sides. And of course, the big question here is to what extent they can be extended beyond perturbation theory and match in the middle. And there's a lot to say about this, but due to lack of time, let me go on to holographic duality, which is the third and probably the most important type of dualities that we would like to understand. I'd like to make a few comments on the evolving standards of derivation duality. After all, these dualities are not pulled out of the hat. They were good physical motivation. But I think, with better understanding what the standards of what duality is supposed to be and what it constitutes a derivation has improved. Let me take the C=1 string matrix model, matrix quantum mechanics duality as an example. In the early 90s, when this duality was uncovered, at least the way I learned from reading the papers, is that this is this based on the picture that you can discretize the worldsheet and looks like diagrammatic expansion of matrix quantum mechanics. But this is rather schematic. There's a lot of freedom here. And in particular, to me, the most unsatisfying thing about this picture, is a bit too schematic. It doesn't really explain why it is the specific worldsheet CFT and matrix quantum mechanics are involved on the two sides of duality. In fact, this worldsheet, as we know now, that involves Liouville theory with central chart 25, is in a certain sense strongly coupled, and it's really only formulated precisely in the years after this duality was understood to some extent. And then, of course, in the early 2000s, there's a new way of looking at this duality by thinking of it as some kind of holographic duality based on thinking about ZZ branes in C=1 string theory. But I would say that this is not on the same footing as how we normally understand ADS-CFT and decoupling limit, because I would say that there's actually no decoupling limit in the story that really explains why you end up with the specific matrix quantum mechanics. So I would say that what we actually want is to show that the open string field theory of the ZZ brane in sequence string theory is equivalent to the eigenvalue of fermion dynamics, not in the absence of the Fermi C, but in the presence of the Fermi C. In fact, if I look at the picture of the eigenvalue in the presence of Fermi C, surfing the top of the Fermi C, it looks a bit like the picture of what we expect to be the naive preserved quote-unquote tachyon potential. In particular, what I would really like to understand here, which I think can be made very concrete, is the rolling tachyon, the rolling open string tachyon, because this is a solution to the unlike the ZZ brane with the open string tachyon set to 0, which is unstable configuration and doesn't really make sense at the quantum level. The open string tachyon, the rolling tachyon, makes sense as in the full quantum theory. That's what we expect. And it has both an open string description and potentially a closed string dual description. And I think it would be very nice to, if one can derive this from open plus closed string field theory on the ZZ brane. And I think there's, by now, sufficient technology to attack this problem from the open plus closed string theory perspective. In particular, I want to highlight a paper of Min-Jae Cho from a couple of years ago, in which he constructed explicitly how to, using these hyperbolic vertices following the work of Costello and Zwiebach, that potentially would allow for a derivation of this kind of relation, passing from a mostly open to a mostly closed string field description by string field redefinition. I want to make some comment about the more conventional ADS-CFT, ADS 5 times S5. And I want to, in particular, address this statement that people sometimes make, shouldn't we simply view the ADS-CFT duality as a definition of string theory? The A equals 4 supremos is number 2 formulation of type 2B string theory, ADS 5 times S5. Now, if so, the content of duality, I would say, is that one has to understand how the A equals 4 supremos in this case reproduce everything we already know about type 2B string theory, that is perturbed strings, D branes in flat space, with some deformation, possibly, and the background independent low energy effective field theory. And in particular, one thing I like about this duality is that we believe that we can, in principle, at least some of us believe that we can, in principle, produce the non-perturbative graviton S matrix of type 2B in flat space by taking a certain infinite n but finite G-Mills limit. There are these dictionaries that has been written down, and I would say, I'll pose the question. So do we know whether this prescription results in a unitary S matrix of gravitons? After all, we think, at least I think, in type 2B string theory, the supergravitons are all the asymptotic states there are. And so if you can produce all the matrix elements in principle by taking such a limit, and that's supposed to be exact at finite GS, then the question is whether it is unitary. And because if it's unitary, then we're sort of done. After all, partially done in the sense that one of the important goal of any theory of quantum gravity is to have a calculable framework for producing non-perturbative graviton S matrices, and sounds like this would achieve that. But I don't really know how to prove the unitarity of this S matrix, and I think that would be an interesting challenge. And finally, let me just address the question of to what extent on the two sides of duality defined. I think it's important to always keep that in mind. Now, most of us believe that the A equals 4 supremos is non-perturbatively defined, not yet by the standard of a mathematician, but by all the standards of physicists. I would say that we have good confidence that it is well defined, either from a perspective of lattice or Hamiltonian truncation, or from bootstrap perspective. But what do we mean by type 2B string theory in ADS 5 times S5? Now, in practice, a non-trivial result has been obtained by thinking about Green-Schwarz effective action. I call it effective action because I think that is the real logic behind it, together with integrability, which appears to fix all the ambiguities, counterterms in principle if you try to quantize it. But I would say that that's not a first principle definition, because after all, integrability only applies to very specific backgrounds, and it doesn't explain or allow you to say what happens when you deform the theory between different backgrounds. I would say that the at least in I learned in
10 minutes.
Textbooks, yeah. I'm wrapping up very quickly. I learned in textbooks about definition of perturbative string theory and RNS formalism, and I would say that the RNS closed superstring field theory does provide a first principle definition of what we mean by type 2B string theory, A dash 5 times S5, at least perturbatively in 1 over the radius. We can view that as a background definition of flat space and then expand around this background solution and try to extract string spectrum and interaction. So we can discuss alternative formalism and to what extent we can establish their equivalence and so forth. Anyway, I'll stop here. Thank you.
Thank you. Rajesh, could you set up your screen, please, while we thank Chi for a very nice first half?
Yeah, I think she needs to.
No, you can start sharing and just you will run over Chi and kick him out automatically.
Not my intention, but yeah. So thank you again to the organizers for putting together this one of the, I think, the most participatory strings meetings ever, and also for inviting me to this this session. So you have just a little while ago heard from Matthias about a proposal to understand the Worldsheet dual to free super Yang-Mills theory. I want to put this in a slightly broader context and make some general remarks about deriving ADS-CFT, which are meant to be pegs for the discussion that follows. So she asked indeed, what are dualities? But I'll narrow my scope and I'll focus on gauge string dualities. And here some of you might be asking, why do you want to derive gauge string duality? Didn't one do it long ago? I think the more fruitful way of phrasing the question is, what is it that we can learn from deriving ADS-CFT that we didn't know before? In this, when you frame it this way, then the answer hinges on how exactly you are going to derive ADS-CFT or gauge string duality. So this is what I will mostly focus on, and I will make, I will come from a particular perspective and a strategy. And of course, there have been many other approaches, but some of which have connections and resonances with what I have to say. And hopefully some of that can be fleshed out in the discussion. So I see deriving gauge string duality as sort of like building a bridge between two river banks, and each of which has its own landscape and are well studied in its own terms. And of course, when you build a bridge, one of the first things you have to pick is a good spot to build it. And as you heard in the talk by Matthias, I think the free gauge theory or the dual tensionless or small radius ADS string theory is the sort of the tractable place to build this bridge. And so what I will have to say is, and then of course, when you build a bridge, you sort of build from both sides. You start from each side, and hopefully you're going to meet. So I'll try to therefore make some remarks in general about going from strings to fields and then from fields to strings. So gauge string duality is an open-closed string duality, as we've appreciated. So a question arises here, which is, how exactly do D-branes emerge from a closed string worldsheet, from the closed string description? Very long ago, in the context of the duality of the Chern-Simons theory with the conifold, with Qumran, we proposed an answer to this question through a linear sigma model perspective, a gauge linear sigma model perspective, which we felt actually has perhaps wider applicability. And the answer is what's written here, that we propose that the linear sigma model has two phases, a Higgs and a Coulomb phase, which coexist as the Toft coupling goes to 0 as you go to the free theory. So to be specific for the conifold can be described by the conifold is a geometry given by this equation for 4 coordinates for x's in C4, subject to this constraint. So the linear sigma model actually writes this in terms of a U1 gauge theory with a pair of charge fields A and opposite charge fields B, such that the space-time fields are bilinear neutral composites of these underlying charge fields. And Higgs space is the one where the charge fields have a non-zero expectation value, as always. But as lambda goes to 0, there is the possibility of a new Coulomb phase, which is where the theory gets unhinged. And it is this Coulomb phase that we proposed sort of nucleates the holes on the worldsheet. And the more complete derivation for the case of the Chern-Simons theory was made by Hiroshi and Qumran some years afterwards. And in fact, this is a very nice picture from their paper of this Coulomb phases sort of nucleating the large N worldsheet. Approaching from the other side, the question is sort of how the holes close up as opposed to the holes opening up from the closed string worldsheet. And here I just want to leave you with a picture again. And this is essentially the key point here is that starting from a large N Toft diagram in the free theory, there's a very canonical way in which you can associate a closed Riemann surface to it, and the Feynman diagrams appropriately can sort of have a dense covering of the moduli space, and this proceeds via something called the Strabel parametrization of moduli space. And I don't have the time to explain that over here, but I just want to mention that there is a very natural way in which you can sort of glue up these double line graphs to form a closed Riemann surface. And in fact, this picture has a lot of resonances with some of the work in the integrable literature, where again, in considering higher point functions of the Yang-Mills theory through the hexagon program in particular, you're trying to build up closed string worldsheets. Coming to the talk of Matthias today, so let's try to see how this fits in with what I said before. So Matthias described for you this twistorial gauge linear sigma model, and I want to emphasize here its structural naturalness in some sense. Not only is it a natural generalization of the ADS 3 times S3 case, which we now understand quite well in multiple ways from both the field theory and the string theory point of view, but it also has close connections with two other topics which Matthias mentioned, namely the open string theory, which of the same open twistor string theory, which gives rise to super Yang-Mills scattering amplitudes, as we heard yesterday, and the BMN light cone gauge string theory, which in some ways this is gives a covariant organization of the spectrum of the BMN picture. But more specifically, coming back to the remarks that I made at the beginning, the gauge linear sigma model, I believe, is very reminiscent of what we had for the conifold. To be more precise, the twistor fields, if one looks at correlators, and both for the ADS3 and we believe for the ADS5 case as well, the twistor fields have vortex-like behavior, and they have this non-trivial winding near the closed string insertions. And in some sense, the core of the vortex is where the Coulomb phase is nucleated, where the theory is unhinged. So this is what, in some sense, is happening even in these ADS5 and ADS3 gauge linear sigma models. And the twistor open string, we believe, when we understand the collection better, would be in some ways the description of D-branes in this closed string theory as appropriate for the small radius limit. Another thing which is very much in the lines is the fact that the worldsheet, as you saw, is rigid. There are in each spectrally float sector, there are these finite number W of these string beads, so to say, on a necklace, which gives exactly what the Yang-Mills spectrum gives you. And so there's really not much dynamics on the worldsheet. And this is also reflected in the localization and moduli space that Matthias mentioned that correlators exhibit, which is once again very much like the A model. So I believe that it's much closer in many ways to what we had for the conifold and Chern-Simons theory than might naively be thought or expected. And coming from fields to strings, this picture of these rigid worldsheet is very much like the 't Hooft, the picture I showed you of how the 't Hooft diagrams, the double lines are glued up, because you can think of each of these strips as sort of rigid strips. And this is what we see very explicitly in the ADS3 case. And in fact, we showed sometime a few months ago that the Feynman diagrams of the symmetric product CFT correspond precisely to discrete points on the moduli space through this treble construction, and that matches exactly with what the worldsheet gives you. And these discrete points are the ones which admit covering maps, and they correspond to, at least in a certain limit, for treble surfaces with integer length. And there seems to be a more intricate version of this picture in four-dimensional Yang-Mills in terms of covering space in ambitwistor space. And this is something we are currently working out. But I believe this picture is therefore more general, and it's a realization of this treble construction of the worldsheet from the Feynman diagrams. Both these pictures, both these pictures from the field theory side or from the Feynman diagram side, what they kind of tell you is that these glued Feynman worldsheets, I'm nearly done, are not only having some covering, but they also have a non-trivial radial profile, which is essentially hugging the ADS boundary. And I think this is very significant in how we try to understand the reconstruction, the holographic reconstruction of the bulk spacetime. But this is something that needs to be fleshed out. So I'll just conclude by saying, returning to the original question I started it, what is it that we can hope to learn through a derivation of ADS CFT? Well, I've made a list of various things. I'm happy to elaborate on many of these in the discussion session. I think the slides are up on the webpage and the Slack channel. But several of these, I think, are new. We get new perspectives on several of these questions, I think, through this explicit realization that I tried to sketch out for you. So thank you very much.
Thank you. Let's thank Rajesh and she once again. Very good. Yeah, those were very, let's start with the questions. Again, as Rajesh said, please check the website or the Slack for many inspiring points, but I'm sure there will be many, many questions. And as usual, I'll start by people that have not yet participated. So I'll start with Spenta, or not much at least.
Hi. Yeah, okay. Hi. I was participating, but quietly. So, so I have two questions. The first question is, this C equal to 1 matrix model, one of the reasons a lot of us worked on it very hard in the early 90s is because the two-dimensional string theory has a dual black hole, has a black hole solution. And I'd like to ask whether there is any progress in the recent times on some deformation of the C equal to 1 matrix model that can actually throw some light on this problem.
I would say that the last progress I'm aware of that has been published is in Juan's 2005 paper. I hope if others have worked on it could correct me. The idea is that you can take, the way, I think it's fair to say that the way Juan describing his paper was a bit obscure, was hidden, a little bit hidden there. But the idea is that you take a large number of FCT branes in C=1 string theory, and then take a certain decoupling limit at finite temperature, where you have a large number FCT branes, but they all recede off to infinity at finite temperature, and you're supposed to it's supposed to give a well-defined Twister-like limit, and the kind of background on the closed string background such that it gives rise to a class of deformation that interpolates between the thermal vacuum or sequence string theory and the black hole background, or the sine Liouville. With Bruno Balthazar and Victor Rodriguez, we've been exploring this in more detail recently, and we're hoping to perform some non-trivial check beyond what Juan did in his paper 16 years ago, but we haven't finished our analysis, so it's some work in progress.
Forgot to mention, please wave if you have a comment related to what was just said or what is being discussed.
I should add that I believe that picture is correct.
Emil, please.
Yeah, there's a thread of work by Givan, Kudasov, Rabinovich, and Sever, who argued in a paper that the black hole solution is not normalizable. It's not part of the spectrum when the level of the SL2R sigma model is less than 1 in some conventions. And so I think there's pretty strong argument that every example that's been examined where the level of the SL2R is less than 1, the black hole is really not part of the spectrum. And the C=1 model is a prime example of that, where, I mean, in a sense, it's impoverished by the fact that there are no non-abelian degrees of freedom. The matrix model, non-abelian degrees of freedom are shoved off to infinite energy in the scaling limit that gives the duality. And so there essentially are no black holes in those models.
Can I reply to that? We're not talking about the same matrix model. So I'm talking about adding the FCT brane, which requires going to the non-singular sector. In fact, we do not know the complete dual of the adding FCT brane per se, but in this the limit I'm talking about involves the long string condensation. So so it's definitely not the singlet matrix model. In fact, we're currently checking this, in the non-singular sector of the matrix model, which is a very different model, explicitly with the non-abelian degrees of freedom, and the dynamics is very non-trivial. It goes way beyond the free fermion picture. I'll be happy to discuss the technical details, but it's not something that can be explained in a few minutes.
Right.
So let's go on to Shota.
Yeah, I also had a question to Shi, so about this rolling tachyon stuff. So am I understanding correctly that the duality that you showed in the equation, the both sides are kind of string theory rather than like a string theory equals matrix model? Like the one rolling tachyon equals closed string.
Yes. There I was talking about a sort of open versus closed string duality.
Okay, yeah, but then like you can also ask that same question in flat space rather than in without talking about this C=1 context, right? Like there are rolling tachyon in flat space as well. And what buys you by considering rolling tachyon?
Are you talking about closed string tachyon or open string tachyon?
Open string. Okay, sorry. Open string tachyon, I think.
The reason I like the C=1 example is because first of all, it's it's free of the closed string tachyon issue. So often when we talk about bosonic string field theory, there's this belief that at least at the level of looking at the way we think about the modular space, the open string field theory, the cubic open string field theory could cover the entire modular space with all the closed string which freedom included. But the closed string tachyon will kill you, right? But in C=1 string theory, there's no problem with a closed string sector at all. And so now, but still, if you want to do the quantum open string field theory, perturbatively, you still have the open string tachyon, which will run in loops, and that'll be a problem. But I think if you expand around rolling tachyon, there'll be no problem. So I think you can do the quantum open string field theory around the rolling tachyon background. So I think this is a good setup to explore this this kind of field redefinition that goes from between open and closed string fields.
And you think like you can explore it just by the Worldsheet technique?
By the yes, in fact, you know, I don't know if Min-jae is here, but a couple of years ago, the Min-jae wrote a nice paper. Min-jae Cho wrote a nice paper extending Costello and Zwiebach's construction, in which he showed explicitly there's a consistent construction of this hyperbolic open-closed string field vertices with two parameters, the kind of length of these colors, circumference of colors, that allow you to dial. And you can dial these parameters, and which correspond to different solutions to the BV master equation that allow you to go between some mostly open to the mostly closed version of the open plus closed string field here.
I see. Yeah. What I just wanted to ask, like, do we really need to go use the string field theory, or like, is there a chance that we can see something already in the first quantized string theory?
I think from the Angshao perspective, I think Ashok has explored this some years ago, but I think there's some questions that really requires the offshore technique to address.
Okay.
In particular, the energy, let's say, stored in you know, open string fields versus closed string fields.
Mm-hmm. All right, thanks.
Ivano?
Yes, hi, thank you. I was wondering if there are any recent efforts in understanding earlier string dualities involving other matrix models, like the BFSS matrix model for M-theory in 11 uncompactified dimensions and other models like that.
Can I comment on that?
Sure.
So, I mean, I think that we've came a long way with the BFSS. I think it's been shortly after the original paper, it's been clarified by you know, several papers. I'm not trying to name all the authors, but that put it in the same context, the usual ADS-CFT duality, and I think that is the correct picture. And then there has been very non-trivial checks of black hole entropy, you know, in the bulk geometry. Versus you know, Monte Carlo study of the free energy of the BFSS at final temperature. So that was extraordinarily non-trivial. But on the other hand, I think IKKT matrix model, which is sometimes mentioned in the same context, is on a very different footing. As far as that is concerned, I'm not aware of any actual picture of a duality in the sense that I don't know what the dictionary would be if you want to produce physics of type 2B in flat space. The closest thing I know is the thing that Ashok mentioned, where IKKT matrix model provide a way to capture certain Dienstern corrections to graviton scattering. But beyond that, I'm actually not aware of any concrete, you know, mapping involving IKKT.
Right. Okay, thank you.
Let's, I'm sorry, jump a little bit to Samir. Sorry.
Hi, thanks. So I have a question for Rajesh and Matthias about this ADS5 free string. So if I understand correctly, you're taking n to be strictly equal to infinity. So is that correct? Yeah. So you won't see black holes. Yeah. Now,
yeah. So one could imagine doing a 1/n expansion in ADS3 that can be done.
Yeah. So but, yeah. That was the question. Can you contrast this with the with the ADS3 case? So in the beginning, you were also saying that n is, you know, it's only the planar limit in ADS3. So what is the status now in ADS3? Do we understand black holes from this free string perspective? And if so,
so firstly, I should say Lorenz Eberhardt, who's giving a talk today, I think at the end of the session, will be talking a bit about some of these issues, but especially to do with black holes. But just even around the plain ADS3 vacuum, many of the results that were mentioned in Matthias's talk about correlators being localized, etc., hold in a genus expansion. So that was also something that that's been already also shown now by several people, including Lorenz.
1/n expansion will never see a black hole, right? Because it's a non-perturbative object.
Yeah, so I will, maybe you should ask Lorenz this after his talk. He has a particular viewpoint on this, which I think, yeah, unless Lorenz wants to join, maybe wants to comment on it.
Well, I can comment on it.
Very good.
But yeah, I mean, so I think it was already realized some years ago that actually the if you consider the perturbative string theory in ADS3 with pure SNS background, it won't describe a single symmetric orbifold, but rather like the ensemble of all symmetric orbifolds. So it's like the grand canonical ensemble of all the symmetric orbifolds. So you don't get one boundary CFT, but you get like sum over all the ends in the symmetric orbifold. Because of that, you essentially can access finite n, I believe, because like you can now restrict like to some Legendre transform or something like that, and you can go to the finite n result. So
is it correct that one can account for the black hole entropy using those?
Yeah. So, but it works a little bit different than what I expected. So yeah, stay tuned for my talk. I hope I can answer some of these questions.
And can we go for something similar in ADS5 or not?
I believe with the current techniques, no, but I'd be happy to be surprised otherwise.
No, I'm just trying to understand what is the difference.
The difference, well, the very naive difference is that in ADS5, the background is created by D3 branes, and now you're throwing away in some probe strings, and you're computing some perturbative string partition function, and that will have a fixed number of D3 branes. Whereas in ADS3, you're creating the background, since it's pure in SNS flux, you're having some fundamental strings in the background, and you have an NS5 brane in the background. So it's not very natural to keep the number of fundamental strings in the background fixed, because you also have some probe string. So that's why you get this grand canonical ensemble. That I think, but if you would like describe the D1, D5 system, then I think it's again more natural to describe the canonical ensemble. Yeah.
Okay, thank you.
Let's go to Veronica.
Sorry. So this is a question inspired by Rajesh's last slide, which is, I was wondering whether you would like to elaborate on the what we learn about the quantum information sort of connections in the duality, in the coupling.
Yeah, I mean, I don't have anything very precise to say, except that I think, and in the slides that I put up, I actually stole a slide from Juan. Juan had a set of additional slides, which I think he didn't show. And so the last slide in my deck is actually from Juan, in which he has this, I mean, many others also have this tensor network picture of sort of building up entanglement and creating the space-time. So in some sense, I think in the tensionless limit, as I said in my last slide, the worldsheet is essentially at the boundary. So it has it's hugging the boundary. It's sort of, and what you have is this non-interacting string bits, and the worldsheet theory is free, and it's just these partons, these non-interacting string bits. And I think as you turn on the interactions, as you turn on lambda, they will start getting entangled with each other, and in some way, I feel it's these string bits which will be kind of building up. I mean, in some ways, the string bits are, I think, going to be the basic units of the this tensor network picture that will somehow grow. But it's a vague thought, and it would be great, of course. So it's still probably a long way to understand that in any precise detail. But I find this string bit picture very suggestive in that regard, and the fact that it's sort of going in from will go in from the boundary.
In particular, is there a hint that it's the entanglement between the string bits that's somehow
No, not yet. I mean, no, not yet. I don't see anything yet to be able to say that with any confidence, but I would expect so. But
okay, thank you.
Let me pass to Eric.
Thanks. Hi. So this is a little bit of a blast from the past for Rajesh and Sheet. Have we given up on embedding Vasiliev into string theory? We're trying to use that as a route to understanding proof of duality, and if so, is it to piggyback on Rajesh's point, because we're not sure what we would learn in doing so?
I can. I mean, I think for the ADS3 case, we. So the short answer is no, I don't think so. In fact, I feel that that's something that's a promising avenue, which we now have the tools to address that question much more precisely how exactly the Vasiliev theory is embedded in string theory. In ADS3, which is under more control right now, and there we have the symmetric product has this extended higher spin symmetry, which Matthias and I sort of explicated some years ago, and which is in some ways a sort of souped up Vasiliev theory. But now we have a dual worldsheet understanding of where all those higher spin generators arise from the worldsheet, how they sort of how the matter fields are sort of charged under them. We have a worldsheet perspective on this, which I think should enable us to understand in what sense you can kind of truncate to a sector of the string theory, which is the Vasiliev theory and the matter interactions, etc. And I find it very suggestive that it's a free field description on the worldsheet as well. And it's sort of like in these old, goes back to the old lore of sort of higher spin features on the worldsheet getting reflected features in target space. So I think the worldsheet description of the free field worldsheet description, I think can teach us more about how the higher spin symmetry, which is realized on the dual free fields of the dual CFT, how that's realized in a very, I think in a more explicit way, but I think it has not been explored yet. And I assume that for ADS 5 times S5, there'll be an analogous picture, but ADS 3 times S3 seems like the place to start. I don't know if she has.
No comments about ADS 4 from anyone?
I just want to make a
I
comment.
think what we heard about from Matthias earlier today is the kind of thing that one should be doing from that perspective. Because so some time ago, I also wondered how to write Vasiliev theory as a topological string theory, and then maybe try to deform it to the real string theory. But at least in the ADS4 context, but I find it hard to guess. This requires some guesswork because you're talking about the worldsheet theory with a lot of gauge redundancy, and it's not totally clear what the rule of or whether there's a rule or algorithm to how to proceed. So I have not really been thinking too much about that in recent times, but I think what we heard from Matthias is the way to go from that perspective.
I want to address something Juan has in the chat about the additional fields that are there in the free Yang-Mills theory, which in some ways are supposed to Higgs the higher spin gauge symmetry. Indeed, I think they will play an important role, and that was one of the things I had mentioned in my last slide as something to understand better how this Higgs mechanism sort of explicitly works, because we now can see from the worldsheet what these other subleading Rajesh trajectories are and how exactly they could lead to this sort of big, I think, what was it called, La Grande Bouffe by Bianchi et al., this big Higgs mechanism of higher spin symmetries. But but nothing concrete to say.
Offer?
Thanks. So I would like to make a suggestion following up on the last point that she was making. So maybe we should only call something a duality if both sides are really non-perturbatively well-defined, like in quantum field theory dualities, and then it really makes sense to derive an equivalence between them. While other things should be called the correspondence, like the ADS-CFT correspondence. And so in that case, as she explained, I mean, one side is well-defined, and the other side, namely the bulk, is only well-defined semi-classically in a one-over-n expansion or expanding around some semi-classical fixed points. And in that case, I mean, deriving a correspondence would mean being on the field theory side and deriving from that when you expand around appropriate semi-classical limits, you get the correct one-over-n expansion and de Bruijn effects and so on, as Matthias described trying to do. And of course, there's been lots of progress on trying to do that, starting from free field theories, and hopefully eventually we will be able to do that in the n=4 case. But I don't think there's really any hope of having a non-perturbative description for the bulk theory in that case, because space-time itself only emerges, I mean, in semi-classical limits. So I doubt if ADS-CFT will ever be elevated to the level of a duality in this sense. But of course, we should all continue to derive it in the sense of a correspondence, I mean, by showing that we get the correct semi-classical expansion.
So if I can briefly respond, I agree with you in spirit, except one point which I would like to, I think, this is related to what I mentioned about how one proves the duality. I can imagine a scenario in which one sort of tautologizes the duality in some way, that the string worldsheet in many ways is the Yang-Mills theory, and we see indications of that in the ADS3 case for correlators and the ADS5 case for the spectrum and so on. In this tautologizing, in this way of tautologizing the duality, you might learn how to non-perturbatively define the string theory as well in some way, because that might suggest, since you know how the gauge theory is non-perturbatively defined, perhaps in some optimistic scenario, you might learn how to define the worldsheet, and in worldsheet terms, non-perturbatively define it in worldsheet terms in such a way that it would sort of extend this tautology in some analytic way, but it's just a.
Do you mean something like a sensible, like a sensible, like you mean something like a sensible definition of a string field theory that would come out of such an approach, or something like that? Yeah, I can. Yeah, that's optimistic, but plausible.
Simon? Yeah, thanks. Yeah. Somewhat vague question about the tensionless strings in ADS5 cross S5 again. Once you have the spectrum and the free theory, there's two natural interacting theory you can go to. There's a user Yang-Mills, but there's also just self-dual Yang-Mills, which has the same spectrum, but roughly half the interactions are turned off. And its correlators are much, much simpler, but yet they compute things like loop integrands that tell you something about the full theory. So I'm just wondering if there's any idea how to get self-dual Yang-Mills from the tensionless string. Be very nice.
I agree. I mean, at the level of the spectrum, you can't distinguish between the two. I believe since our construction is sort of, in a way, ambitwistorial, it doesn't sort of, privilege right over left in some ways. So I believe that the natural interacting generalization will be that of the full Yang-Mills theory, but it's an interesting question whether there's some deformation. I mean, there is at the Yang-Mills level, I guess, and in the twistor open string description, there's a very natural way in which you can sort of think of the pure Yang-Mills theory as a deformation of the self-dual Yang-Mills theory, and it's possible that you might see a reflection of that on the worldsheet, that there is perhaps a choice that you can make, but this is something, yeah, it's at the level of the interactions, and I can't really say either way at this stage, but it's not impossible. I would think that it should, I mean, it should by rights come out, but we don't know.
Should ask? Hi, addressed to Rajesh and Matthias. Your construction of the string worldsheet had this n equals 4 superconformal symmetry, and if we expect that interactions preserve that symmetry, then we could take that interaction all the way to the strong coupling end, and that would give us an that would give us a worldsheet theory for 2B theory in flat space with n equals 4 superconformal invariance. That sounds sort of interesting. So would you expect, could we search for such a theory directly? Could we search for an n equals 4 worldsheet supersymmetric formulation of 2B theory in flat space?
I think Nathan is here. I mean, I think Nathan is skeptical that there is such a theory, but I mean, it is indeed a valid extrapolation. You would imagine that by turning on this marginal deformation, you shouldn't be able to you shouldn't change that. And the deformation should preserve this worldsheet. I should say that in the case of ADS 3 times S3, there is the hybrid picture, which tells you that at least by taking the large radius of ADS 3 times S3, you sort of go to an R6 times T4, and Nathan has a worldsheet description which has n equals to 2. So it's sort of an alternate, it's this hybrid sort of formulation. So it's not unnatural for one to expect that the maximally symmetric, maximally supersymmetric theory in 10 dimensions should have something like that. And I don't know, Nathan should comment more, I think.
Yeah, Nathan, yeah, please.
I can say something. So there's another aspect of this theory which hasn't been emphasized, is that the ADS3 times S3 is a WZW. So you have actually a supergroup, whereas in this case, it's a coset. And the question about the left moving versus the right moving sector is, I think, something key that also has to be addressed, is what do you do with the right moving sector of this theory? So I think that might be related to this n=4 question. As I said, I don't know any n=4 version of the string theory that works. So of course there's an n=4 topological thing that we did with Qumran, but that's different. That you don't gauge the n=4. So.
I don't see waving hands. Leonardo?
Oh, hi. Yes, I have two questions for Rajesh and Matthias. The first is whether you have thought about D-branes in your model, because one of the natural guess would be that the spectrum here would be just a super Yang-Mills multiplet, the free super Yang-Mills multiplet on the D-branes at your in your topological theory. So that would be very simple, and perhaps would offer the way to start perturbative gauge theories, gluon scattering from that viewpoint.
Yeah, I think Matthias should probably, I mean, we've discussed a little bit about D-branes in this model, but Matthias, do you want to say?
Yeah, so I think, I mean, at the moment we are trying to understand the D-branes for the simpler ADS3 case. I mean, which is basically, I mean, from the point of view of the Worldsheet GFT, that's sort of technically simpler. So we are trying to understand that. But yeah, so this is work in progress. So but the hope would be that this will work, and then one should also be able to understand it for the ADS5 case. I mean, these are very simple Worldsheet theories. So you are.
But in ADS3, the expectation for the open strings is less clear, whereas in ADS5 there's a sharp conjecture that one would make.
Right, but because of these spectrally flowed sectors, the construction of these D-branes is a little bit subtle for this Worldsheet theory. So first we want to understand how this really works for ADS3, and then I agree that the interpretation will be clearer for ADS5, but technically we first want to sharpen our tools for ADS3.
And then my second question would be in the same spirit as Simon's question. There are certain topological sectors, for example, this is chiral algebra subsector of the n=4 theory that, according to Gaiotti and Costello, is described by this B model on SL2C, and it would be nice to derive it from your construction.
Yeah, no, indeed, I think so. And I mean, even, it's, as I said, there are many things which are sort of like in the conifold theory. So, and for them, the dual sort of thing is a kind of a conifold, like a subsector of the ADS5 times S5 bulk. So it is perhaps not, I mean, I don't quite see how it would work, but it is perhaps this gauge linear sigma model perspective might tell you how to sort of embed some kind of a simpler gauge linear sigma model which would describe that sector, and then that would be dual to the chiral sector of the Yang-Mills theory. But yeah, it definitely would be very nice to see that.
Thank you.
While I don't see more hands, let me ask a question, maybe for Rajesh or for Nathan. In these limits of zero radius, of course, Nathan and Rajesh approach them differently. How hard is it to just compute at some simple correlation functions? Do you think for 4 points or for 3 points?
From the Worldsheet point of view?
Yeah.
So Matthias and I in the ADS3 case, I think, I mean, with initially with Lorenz and then later with Andrea Day and Bob Knighton, we computed several 3-point functions, and it's constrained very heavily by the sort of word identities that the free field construction automatically gives you. So it's and this is how we were able to map to the symmetric product CFT correlators. So this is something, as Matthias mentioned in the talk, for the ADS5 case. Many things, I think, work analogously to how it did in ADS3. So we don't expect the correlators, I think, at least simple 3-point functions and perhaps even 4-point functions at some point probably can be worked out. It's probably at the level of complexity. It's like like computing twisted sectors in a free theory, in an orbifold theory, in some sense. But Matthias, I don't know, you want to say more? Yeah.
No, I mean, I think we believe that the techniques we use for ADS3 will also work for ADS5, but we haven't quite completed the analysis yet.
Maybe I can just, Nathan also had different proposals, right? For zero radius, there's some topological theories and some idea for propagators appearing as some Wilson lines. Was that finished and checked if it really gives the propagators and so on?
So there are two things. So one thing is, I think for the Rajesh and Matthias, what they're doing, I think if they understood the Worldsheet, I think then they would be able to compute the correlators, I think, for the ADS5 case. So I think that's the missing ingredient. I think it shouldn't be difficult. What I was doing is more speculative. So I was starting from the full ADS5 times S5 sigma model and trying to write it as something which is purely topological plus a deformation. And the part that is more speculative for me is the topological part. So I don't think you should take the computations that I was doing in any rigorous sense. So it was just some hand waving arguments. So I think the approach of Rajesh and Matthias is much more solid. So, but you need to understand the Worldsheet. So I think that's the missing ingredient for them.
Let's go to the IAS node and then to Shai and then to Spenta.
Yeah, so this is a basic question about Matthias's talk. So these worldsheet variables that you had, are they purely right movers or purely left movers, or are they both, or what exactly?
Well, I think the picture we have is that they are both left and right moving, and that the physical state condition removes, essentially all the non-zero modes except for these generalized zero modes. And the generalized zero modes are somehow shared between left movers and right movers. But this is part of the story we don't really have a first principles derivation of. That's our expectation. Part of the reason is that that's similar to how it worked for ADS3. Part of the reason is that if you look at this classical solution of this Berkowitz type theory, these flux solutions, they have a certain number of holomorphic modes, and they match exactly the number of these wedge modes that we see. So we want to think of them as sort of part of this classical solution, and there's only one set of these modes. So that would suggest that you can end up with only one set of these generalized zero modes. But at the moment, this is somewhat vague. We don't have a very sharp way of getting that.
Okay, thank you.
Shai?
Hello, can you hear me?
Yeah. Yes, we can hear you. You seem to be on an airplane.
Wait, can you hear me? Sorry, I'm not sure this way.
Yeah, I can hear you. We can hear you. Yeah.
Well, okay. So, well, I don't know if you can hear me, but my question is for Matthias and Rajesh, if they could consider their construction in the case of ABJ theory, because in that case, there's a limit which has vector-like degrees of freedom, a free theory limit in particular. So I would imagine the construction might be simpler and also be easier to potentially connect to the Cilia theory. So that's the same number of degrees of freedom.
Thank you. Some reply about ABJ?
Yeah, I think there's a as is probably familiar to many people, there's the odd ADSs and the even ADSs. There's a slight there's a natural progression in the odd ones, and the even ones are somewhat exceptional in some ways. But so I suspect that the ABJ theory, at least our approach of finding the worldsheet, is going to be more complicated for the ABJ theory. And I don't have any good ideas of how to actually even think of the right generalization for that case. But I agree that for things like understanding some of the aspects of the Vasiliev theory, that's you have this tunable parameter there, but of course that takes you. Even if we did have a generalization, I think that would be out of the perturbative domain of the worldsheet to go to something like that, I suspect. But for the Vasiliev case, I think the ADS3 there's a even though the modes are non-propagating except for the scalar, except for the matter fields, I suspect that we can learn at least some of the structural ways in which Vasiliev theory is embedded in string theory and how it's Higgs, etc. Even in that case, but independent of that, I think the ABJ case would be very interesting to understand, and I don't have any good thoughts about it.
Spenta?
Yes, I have a slightly different question that also involves discussions from last week. So now, if we look at the n=4 super Yang-Mills theory, one would expect that as you dial the Toft coupling from 0 to very large values to infinity, you would not expect any phase transition, large n phase transition. I think that's perhaps a correct statement. Now, let's look at the presentation of Matthias and Rajesh, that there is a very good chance to formulate a perturbation theory around lambda equal to 0. All the string bits will become strings, and they'll sort of be able to develop a perturbation theory with a finite radius in lambda. Now, my question is really that now suppose I start jacking up lambda. So of course, the spectrum of the Hamiltonian will become very complicated. And at very large lambda, it becomes an extremely complicated spectrum that describes a black hole. The question is whether this idea that non-perturbative gravity or string theory would correspond to an ensemble of gauge theories, whether that idea actually can survive if these people are able to prove a correspondence at small lambda. That's my question, maybe.
I don't know who would like to take up on that. You can wave that sense. Maybe let's do the following. I have a suggestion. Let's thank Rajesh and she for the very nice formal part of the discussion. And we can continue informally for a few more minutes. So now we are in the informal part, so maybe people will feel braver to address Spenta's provocation.
Yeah, I don't know if someone else should perhaps say more. I mean, people who have thought more about the ensemble average this thing than I have, so all I would say is that at the moment, I don't think even our approach has much of an idea of these black hole states which are of order n square. How we would see them from this worldsheet, I don't have the faintest idea. So in that sense, it's not a question. Even if we are able to study it at small lambda or in this expansion around lambda, it would be limited to the perturbative string spectrum for the immediate future, yes, in the absence of any new idea about these non-perturbative states.
So you would agree that there is no ensemble picture there, at least in some
I mean, that
neighborhood of lambda equal to 0. That's the question I'm raising, actually, that now if you don't have an ensemble picture for small lambda in this type of theory, which has supersymmetry n=4, would you expect an ensemble picture at strong coupling? That's the question, really.
Sorry, but I'm not sure if I agree with you cannot access the black hole in the weak coupling regime. I mean, we know, for example, the 116 BPS states is presumably accessible from the Q cohomology at weak coupling. So, I mean.
Yeah, so maybe I should say that you wouldn't trust our expansion for at energies of order n square, because we don't know what else might be there. You can certainly, you're right that the 116 BPS states at low-lying 116 BPS states, you should be able to see because they're part of the Yang-Mills spectrum and you're reproducing the Yang-Mills spectrum. So that's by construction there, but this is just the single trace operators and it doesn't take into account the trace relations.
Let me pass to Offer, who is trying to wave, but the background is trying to fight with him.
Yeah, no, I was going to say exactly the same thing that Rajesh said, that the worldsheet breaks down well before black holes. It already breaks down at the level of operators of the dimension of order n, because it doesn't see these trace relations. So.
Right, but there you might imagine at least some D-branes sort of, you might be able to think in terms of maybe some giant gravitons sort of from a worldsheet point of view, and perhaps correct it. But yeah, but n square is even further. Yeah, that was the reasoning.
Mm-hmm.
But are you?
Let's maybe go to Hammer. He is one of the ones that hasn't been participating yet in this.
Thank you for giving the chance. I think the question has been sort of answered. I was going to ask about the contribution of the genus zero partition function order n squared, in the sense of at least which participates. I had in mind the finite temperature contribution, the finite temperature strings or finite temperature QCD at large n, where we know that after a certain critical temperature, whether it's the Higgadorn or even a critical temperature that's below the Higgadorn, the planar, the sphere, the genus zero partition function sort of contributes, but no one knows exactly how that is because of the instability of the canonical thermal ensemble and so on and so forth. So I was inspired by the Rajesh duality, if whether we can use, the description of the picture was that a sphere partition function sort of develops vortices, holes, such that there's the Riemann, the description in terms of continuum Riemann surface so breaks down. That was the description that was given back in the 80s. So I was now curious, or if the picture of holes developing on the worldsheet, like in the topological strings and the Chern-Simons, would give us a hope to describe this planar partition function contribution for the axis. If that makes sense.
So not obviously, at least to me. I mean, it's not obvious to me that you would find just from the holes can probably describe D-brane states of order n, right. But order n square, I'm not sure. I think Shiraz is waving.
Yeah.
Right. I just want to say that, I mean, what you could try to do just on worldsheet, in the classical worldsheet theory, is to find the background to the Euclidean black hole. And you can just find the sigma model describing time compactified with antiperiodic boundary conditions for fermions. That should be a classical solution, just like it is in gravity. So just the classical sigma model on that. I'm not saying that would be easy to do, but presumably in the ADS3 context, that's easy to do, right? Because it's just a space-time flipping.
I think that's what Lorenz is. What Lorenz sees, I think, is that that's already included in the original background as some highly excited state. I don't know whether he expects this to continue in ADS5 or I don't know.
I think I don't, because of this grand canonical ensemble thing. I have no reason to believe that in ADS5 that should be the case.
But more generally, I mean, why you shouldn't be able to describe all the detailed states at energies of order n squared using this classical string description. You should be able to get the thermodynamics, right? I mean, I'm not saying it would be easy, but there should be some sigma model that describes this.
Oh yeah, certainly, yeah, sure.
About the earlier, so I'm not sure I understand Ofer's earlier point about the trace relation. I mean, wouldn't you capture all the trace relation? You can calculate, let's say, endpoint functions in the free theory, just the level of free Yang-Mills theory, right? I mean, shouldn't that capture?
But how do you see that but on the worldsheet? You wouldn't see that, right? I mean, how would you see that on the worldsheet?
No, but I mean, if you can compute the tree level amplitudes, I mean, perturbative amplitude, let's say, in principle. I'm not saying that it's easy in practice, but in principle, if you have 1/n expansion of some.
No, I don't know how you'd see that from the 1/n expansion.
You're saying that you need the operators to be, well,
You need to show that, say, the operator trace of phi to the n+1 is related to other operators that are described in a completely different language, and that involves non-perturbative effects in the 1/n language. So I don't think you would see it at any order in 1/n.
Why would say it's non-perturbative though? I mean, the level correlator.
I would suggest to continue on Slack. I'm sorry, as we do need to screen share, and some of us might need to use the restroom. So let's all thank Shi and Rajesh for a very engaging discussion. And I remind people that I'm asking people to send us the slides of the discussions ahead of time. For example, the ones for today's integrability discussion are already posted. And Volodya and Grisha also posted a big list of questions on Slack that people send them beforehand. So do check out the list of questions there for further inspiration, and see you in 5 minutes again, or 4 minutes, 4 minutes. Hi, Andre. Volodya?
Can you hear me?
Yes, Andre, yeah.
Do you know the titles of the talks?
Yeah, they are on the web page, but they will be also on the screen. Don't worry.
I see.
So, Mykola, do you want to test the share screen?
Yeah, sure. One moment. Actually, can you? Sorry.
Let's go to Kevin first, then.
Yeah, let's do Kevin first.
Yeah.
Okay, so I'm using two devices, which I hope won't cause problems, like one for the screen and one for.
I see that you are co-host with two devices, so that should be okay. That's perfect. Do you want to scroll up and down just to check? Yeah, that's good.
Okay, sure. Stop sharing.
Yeah, please. Thank you. Mykola, are you ready? Yep, seems to be working. Do you want to test full screen and to change a few slides? Sounds good. Can you? Yeah, perfect. Thank you. Volodya and Grisha, are you there? Grisha, Volodya?
Yeah, I will try. Let me try to share screen. Do you see my slides?
Yes, we can see your slides and your pointer. Do you want to, and we can see when you change slide. Very good, perfect. Will you be sharing all the slides, or will Volodya?
No, I think Volodya has his own slides.
Okay. Volodya, are you there?
Shall I stop sharing?
Yeah, you can, please. Yeah, thanks, Grisha. And you will go second, right, after Volodya?
Yeah.
Okay. Volodya? Yeah, Volodya is online, but he might not be exactly close to the computer. Okay. Okay, no, it always works. I see. So, yeah. So Andrei, we should start in 1 minute, right? At 3:20, and it's 25-minute talk, 5-minute questions.
Okay, I guess I'll share my screen.
Yeah.
Okay, so today we are happy to hear Mykola Dedushenko. He will talk about theory changing interfaces and quantum algebras.
Thank you. Thanks a lot for the invitation, and also shout out to the organizers for being extra creative with the conference format this year. So this talk is based on the upcoming work with Nikita Nekrasov. It will hopefully appear soon. We're working hard to finish the paper. So here's some photographic evidence of hard work. The topic lies at the intersection of several general ideas. First, quantum field theories, as any natural objects, they come in families, so it's natural to ask about interfaces between different members of the family, whether they exist, and when they do, you can collide interfaces and see what happens. In particular, this leads naturally to the idea of sort of symmetries or more general groups or algebras acting on the families of theories, and they can act between different theories with generators realized by interfaces that would extend the usual notion of symmetries that act within one theory by could have mentioned one defects. And in my case, I don't assume them to be topological. And if those interfaces preserve some supersymmetry, they lead to interesting structures in the Q cohomology. And on the other hand, there's also the idea of wall crossing. Namely, we'll be looking at how spaces of supersymmetric vacua transform as you go across walls in the parameter space, namely mass and phi parameters of the theory. And that's also related to mirror symmetry and symplectic duality, where you could consider walls by adjusting parameters. You could consider walls between Higgs, Coulomb, or say CFT phases of your theory. But the main motivation really comes from Bethe gauge correspondence of Nekrasov and Shatashvili, where on the left-hand side, you have a quantum integrable system, and on the right, you actually have a family of quantum field theories, supersymmetric quantum field theories. And the Hilbert space on the left corresponds to the sum of supersymmetric vacua on the right, among all those theories. And there's an algebra A acting on the left, acting on the Hilbert space of your theory. The spectrum generating algebra that could be a Yangian or quantum loop or quantum elliptic algebra. So one could wonder what's the realization on the right, and if it acts between different members of the family, can you construct interfaces realizing those actions? And the main example of the family you can think of is the following. So imagine a gauge theory with UN gauge group and L fundamental hypermultiplets. So this is a theory with 8 supercharges. L is fixed, and N labels members of the family. It goes from 0 to L. And on the left, the corresponding integrable system is XXX or XXY or XYZ spin chain, depending on the dimension your quantum field theory lives in and the supercharge you pick. Another big motivation comes from the geometric constructions, namely the stable envelopes by Molik-Okounkov and also Aganagich and Okounkov in the elliptic case, which are certain natural geometric building blocks from which you construct R matrices. And once you have R matrix, you know how this algebra A acts. And related constructions by Nakajima and Vananolo, who constructed actions of Yangians and quantum loop algebras on the equivariance cohomology and K theory of the Nakajima variety. So, and in both cases, those constructions proceed along similar steps. They're using Lagrangian correspondences in the products of varieties, which look like BAA branes in some hyperkähler manifolds. So they suggest that there's some boundaries or interfaces, supersymmetric interfaces. Now, this slide contains some very limited list of literature. Of course, the actual list contains hundreds of references, but I want to, here at the beginning of time says this, the sort of precursors of these Nakajima and Vananolo papers, 9 years before the Bethe gauge correspondence, and already in the original idea, there was this idea that there should be some branes realizing the action of A. Yeah, I encourage you to go back to the PDF file and look carefully into this list of references, but I have to skip to save some time. So the basic setup is gauge theory with 8 supercharges, some gauge group on the flavor group GH. Let's fix the maximal torus of GH, and then U1 H bar is this special R symmetry of the theory with 8 supercharges that, from the point of view of theory with 4 supercharges, looks like a flavor symmetry. So backgrounds for U1 H bar break half of SUSY. And then we consider this also bigger torus T. Now we will be working in 3, 2, and 1 dimensions. When we are in 3 dimensions, place the theory on the product of elliptic curve and time, Euclidean timeline. And the interfaces will be wrapped on the elliptic curve. So they act on the corresponding Hilbert space and also on the space of ground states, since they're supersymmetric interfaces, as we will see. And then in 2-dimensional case, we just replace the elliptic curve by S1, and in the 1-dimensional case by a point. And additionally, in the 3-dimensional case, there is additional symmetry, the Coulomb branch symmetry, whose maximal torus is realized by the topological symmetries, as is well known. Now, as I mentioned, the structures are in the Q cohomology. So what supercharge are we looking at? It is most convenient to describe it in the 2D 2,2 language. It is probably the most familiar to everyone. So recall that there are 4 interesting supercharges in this case. So B model supercharge and the holomorphic supercharge, once you lift them to 3 dimensions, they both become the supercharge of the holomorphic topological twist, in particular known from these papers and most recent Costello, Dimov, Gayota. In the A model case, they lift to the 3D A twist supercharge, and but then there's 4th one, the omega deformation Q, which is sort of in between A and B. It is preserved both by A and B branes, and if you lift them to 3 dimensions, it is the supercharge that squares to the anti-holomorphic translation along the elliptic curve. That's at least how we choose it. And we'll be studying its cohomology. And operators in the Q cohomology are clearly, they are extended objects. They must wrap this E tau. They will be interfaces. Sorry. Well, you also can alternatively think of it as a 3D n equals 1 supercharge. Okay, so let's, I will mostly focus on stable envelopes and explain R matrices later. So this is the picture of our basic setup. We also turn on flat connections for the flavor symmetry and for this special H bar symmetry, and also for the topological symmetry. So these ones, the topological connections, they are usually referred to as Kähler parameters, and these are equivariant parameters. Now, when you reduce to 2 dimensions, Kähler parameters are replaced by theta angles, and in 1D they disappear completely. You only have equivariant parameters in the 1-dimensional case. Now let's focus on the theory in the Higgs space. Let X be the Higgs branch. We know that the space of supersymmetric vacuum in the quantum mechanical case is given by the cohomology, in our case, equivariant cohomology. That goes back to Whitman's paper on Moore's theory. Now, when we work with our specific Q and go to 2-dimensional case, it is natural to identify the space of vacuum with the equivariant K theory of complex numbers. And then 3-dimensional case, it's related to the elliptic cohomology, but not just strictly equal, because this LT of X, this object, at least following the same approach that Okenkov and collaborators followed, it's not a space, it's a scheme that generalizes the say such schemes as the spec of cohomology ring. But in elliptic case, it's no longer defined, so it's not really a spec of anything. So you just study bundles over this LT, and there is a natural bundle of vacua whose sections are related to this space. Unfortunately, no, I don't have time for this story, so I'll just focus on the cohomological case as it's simpler to describe in a short amount of time. So let me also quickly tell you what stable envelopes are. So let A be the torus of our flavor group. Could be it doesn't have to be the maximal torus, but you can think of the maximal torus. And X, it's our Higgs branch, and XA is the fixed locus with respect to the A action. Pick a fixed point P in the fixed locus, then you can consider the full attractor of P for the complexified action of your torus. So there are these red lines represent trajectories or orbits of the complexified action, you can consider all orbits that end at P. And if some of them also start at some other fixed critical point P prime, you can also consider all trajectories that end at P prime and so on. And this whole beast is usually referred to as the full attractor of P. Now, it turns out that there is a natural way to extend cohomology equivariant cohomology classes from the fixed locus to the entire X. And in such a way that you start with a cohomology class in your fixed point and you sort of extend it along the full attractor. And that's the idea behind the stable envelopes. And in our case, physically, of course, these are spaces of vacua. So we're going to get some map between spaces of vacua. And these things also have generalization to K-theoretic and elliptic cases. This fixed locus can also be identified with the Higgs branch of the theory in which you have turned on large real masses for the flavor symmetry A. So your original theory had Higgs branch X, then you turn on real masses for this torus A and crank them up to infinity. You get theory whose effectively the theory whose Higgs branch is the fixed locus. And it turns out that you can actually change masses in the supersymmetric way. So recall that R is our Euclidean time direction. It is possible to vary real masses in this direction, or I mean, if you're in a flat space in any direction, but we are on R times the torus, so we vary real masses in the R direction while preserving 1/2 of supersymmetry. All we have to do is to add this additional term in the action that has the derivative of mass in the Euclidean action. So in particular, we can have the following configuration where mass is 0 on the left and some generic large mass on the right. And there is a natural supersymmetric interface that interpolates between the two regions. So this interface, of course, we'll call them Janus interface for masses, or maybe mass Janus, as following the tradition in the literature for such objects. And the proposal is that it actually realizes stable envelopes in this gauge theoretic context. Now, why is that? Well, simply because the BPS equations give you flows for the complexified torus, or you can think of them as gradient flows for the following potential, where you take real moment map for the flavor symmetry times your y-dependent mass, and real moment map for gauge theory times sigma. Or if you restrict this to the Higgs branch, you will get the following Morse function on the Higgs branch, where, okay, of course, it's written in the ambient space coordinates. The actual function is complicated, but in theories with 8 supercharges, all critical points of this function have equal indices, equal to half the target dimension. So you get the corresponding gradient flows connecting these critical points. They don't really contribute to the differential on the Morse-Mail-Witten complex. So the critical points give you exact vacua, but these gradient flows nevertheless contribute to other things, like when you start changing your Morse function, start deforming your theory. And in particular, you can, so you see that here mass depends on y, and y is our Euclidean time. So what we really have is a time-dependent Morse function. So let me just consider the supersymmetric quantum mechanics as in Witten's paper, with the target space, the Higgs branch of our theory, and Morse function f representing the effect of masses. And the Morse function now depends on time explicitly. Now, where the Morse function is time independent, we usually write the action as a Q-exact term plus the topological term like this. We would like to use the same action in the case when f is time dependent. So you just have to make sure that this additional term is included so that you can assemble this total derivative term. And this additional term that we include is precisely what we had before to make the Janus interface supersymmetric. You can just independently infer it using the supersymmetry variations. So okay, so we're going to use this action, and you can see already from here, so that the variations of your Morse function that vanish at infinity, the Q-exact deformation. So in other words, the Morse function somehow changes with time, but if you keep, and you can wiggle it while keeping the asymptotic values, the asymptotic functions fixed, and then this gives you Q-exact deformations of the theory, and they should not be visible for the BPS computations. Now, if you look at the operator formulation of this theory, So recall that in the standard formulation, the Hilbert space is identified with the differential forms on your target, and then you have supercharges acting like these operators. And if you don't have this term, you just have the usual Hamiltonian given by the commutator, then this theory, of course, is unitary, but it breaks SUSY once that you start changing F with time. But if you include this additional term, you actually preserve Q while break Q dagger. And this conservation of Q is expressed by this equation, where this additional term reflects the explicit time dependence of F, but this is the conservation law for Q. But now this term breaks unitarity. So this is a non-unitary deformation. But it's actually perfectly fine, because what we want to do is an interface that interpolates between theories with different Morse functions. And that interface will act as some operator in the Hilbert space. And there's absolutely no reason for that operator to be unitary, because most observables are not represented by unitary operators. But we have to be careful because, so we actually choose this option, non-unitary deformation, but we have to be careful because now with this non-unitary evolution, like you might end up exiting the Hilbert space and getting some unnormalizable states. It is actually convenient to conjugate by e to the f such that the differential is just d, and now the Hamiltonian, because of the way it transforms under this conjugation, becomes d exact. This conjugation simply corresponds to dropping the topological term. So the action is q exact, and it's just the square of the gradient trajectory equation plus some superpartners. But because H is d exact, naively, it seems like the evolution is trivial in the cohomology. The Hamiltonian is exact, and that's correct if the target manifold is compact. But if your target is non-compact, things might happen. And in particular, as you'll see, an L2 function, for example, can become unnormalizable. Yet the overlap with a normalizable function is well-defined. So the matrix elements between normalizable states of this interface are well-defined, and that's all we need. Now, let me explain this in the toy example. Suppose the target is just a complex plane, and this is our Morse function, so just distance squared, and m is a parameter, real, like you think of it as mass. It can have either sign or be even zero. The Hamiltonian has two states in the kernel: the zero Fermi number state, the Fermi number 2 state, and if mass is positive, then only the first one is square normalizable. If m is negative, only the second one is normalizable. And furthermore, you can check that in the case when f is time dependent, the first one is actually still a solution when f changes with time. It simply solves the Schrodinger equation. So what you can do, we'll consider the following configuration. Start with positive mass in the far past and assume that mass becomes zero in the future. And in the past, we start with this normalizable state e to the minus f, but then in the future, because mass becomes zero, it just simply becomes 1, so which is not square normalizable. So we must be in trouble, right? But so far, I've ignored equivariance, just considered this without equivariant parameters, and equivariance actually saves the day. If you replace d by the equivariant differential for the rotations of the plane, you can solve the corresponding problem exactly and find the ground states, and they are always square normalizable even when mass is 0, because this epsilon is present here. And now you can compute the overlaps, this sort of transition amplitudes between regions with different m. It is convenient to assume that m behaves as a step function because it's of the shape independence. So we can just compute this transition from m to 0 and get some answer. In fact, we can do this in all possible cases, say going from m to 0 or from 0 to m. And notice that the corresponding answers are reciprocals of each other because, well, if you go from m to 0 and then back to m, in this configuration, you can deform the mass profile such that it remains m all the time, and hence nothing should happen. And indeed, we get inverse answers. Or you can go from minus m to 0, 0 to minus m, or from m to minus m. Now notice that this one, from m to minus m, can be deformed into going from m to 0, and then from 0 to minus m. And indeed, the corresponding answer is the product of these s's. So everything just, it confirms our expectations. And in fact, these S's are the analogs, the toy analogs of stable envelopes, and R, when you go from M to minus M, the analog of R metrics, as we'll see. So the general story goes like this: your fixed point P at infinity and the fixed point. And then the region with non-zero mass prepares you, in the limit of large mass and large metric, prepares you a certain wave function.
Mykola,
like yes,
5 minutes till questions
yes,
start.
Yes. It prepares you a certain differential delta-like form supported on the attractor, and then you overlap with the probe equivariant form in the mass equals 0 region, and that's the matrix element that we compute. Of course, this is all a simplification, and what we really do in the toy example, we had only one vacuum, so nothing could really happen. In actual examples, the target space is more complicated. It has many fixed points, and SM are non-trivial upper or lower triangular matrices that describe transitions between them. And also all computations are done in gauge theory in practice, because nonlinear sigma models are complicated and via localization. And also the time is replaced by an interval with some boundary conditions representing vacuum, thimble boundary conditions. Well, because it's a little bit complicated to unclear. There are some problems with localization on the non-compact space. I can comment on it later why. Here's a summary of the interval computation, which is just for you to look later if you want to. I'm gonna skip it. Just a comment that once we're working in quantum field theory, so besides this interval or the time direction, there's also circles. You can consider a circle as a time, as your time, and then it gives you a more conventional interpretation as an index in a certain soliton sector. But in 1D, there's only this interval direction, so it has to be considered as time. And if you want to work uniformly in that space-time dimension, it makes sense to think of that direction as time even in 2D and in 3D. Now, how do you construct R matrices? They are sort of as ratios of these stable envelopes, as I already said, where you go, which basically means that you go from one value of mass to another value of mass, which correspond to, say, different chambers in the parameter space. In the simplest case, when there's only one mass, you can imagine just the following configuration where mass is positive here, negative here, and this interface, that's what's gonna realize the R matrix. Let me give you an example. How to actually, that this one is enough to construct interfaces realizing the SL2 Yang-N in this case. So we wanted to realize the raising and lowering operators. In other words, the theory on the left is UN gauge theory with L hypers, on the right, UN plus 1 gauge theory with L hypers in the fundamental. And what we do is, inspired by Mykola, consider the following theory with one extra hypermultiplex. And in this theory, you have one more flavor symmetry, one more U1 flavor symmetry that rotates this additional hyper, and let M be the real mass for this additional hyper. If you crank up this mass to infinity, the theory decomposes into two sectors. One sector is just the theory without this hyper, and another sector is where gauge group is broken from UN plus 1 to UN times U1 by Higgs mechanism. So now to make these two sectors talk, we consider an interface where mass goes to large positive to large negative. And the interface is 0, and that's where the two sectors talk to each other, and you get a certain block matrix representing this interface. And in particular, the A, B, and BA blocks are where the rank changes. Well, you sort of ignore this trivial factor and just consider these two, and they provide the realization of the raising and lowering operators in the Yang-N. And then this can be generalized to arbitrary quivers. And of course, there's a lot of things I don't have time to talk about, like I didn't give you all details about the elliptic case, from which in principle everything else follows by taking limits. The details of interval computation, construction of more general R matrices for general quiver varieties. There's also Janus interface with phi parameters that realizes stable envelopes on the Coulomb branch. There's an interesting story about half index and index. You can take the three-dimensional index and stretch it into a cigar or into a sausage, and prove that the corresponding squashing parameter is a trivial deformation of the THF using techniques of this paper, and then use that to relate the holomorphic blocks and half indices, and then see that I'll use that to see that our interface sort of describes the wall crossing of the half index. You act with the interface and you get the value of the index in different phase of the theory. And finally, there also exists a string theory construction of these systems in the string theory compactifier in the LE space. And then you can use dualities to relate constructions in Q and QA supercharges, and also connect with the 4D Chern-Simons approach to integrability. And finally, the future directions include, so first, we really constructed our interfaces sort of up to quasi-isomorphism, which means that you can wiggle the shape of masses and you get, in principle, different interface, but at the level of Q cohomology, it's the same one. So that leads to questions about derived structures, higher operations, stuff like that. And the discussion in terms of Morse theory suggests that the generalization to few supercharges might be possible, maybe not as well behaved. Then our supercharged Q can be lifted to A model supercharged in D+1 dimensions in an appropriate way. So it suggests that these constructions have analogs in the quantum cohomology and quantum K theory cases, and lifting from 1D to QA in 2D suggests that there must be connections to Gayoto-Moore-Whitman paper where they studied the Landau-Ginzburg models with the interfaces where parameters change and with respect to the A model supercharge. And that's where I end. Thank you.
So let's proceed to questions.
Okay, see.
Gregory Moore.
Hi. Yes, I was meaning to ask about the very last point. I got a little worried when you started talking about the non-unitarity, the tension between preserving supersymmetry and non-unitarity. You're not saying that there's a problem with using this kind of construction to construct half supersymmetric interfaces in 1+1 dimensional series?
No, there's not really a problem because the matrix elements between the L2 states are always finite. And well, when you are in higher dimensions, you can always reinterpret the circle direction as time, and then there will be no problems with unitarity.
Okay, good. Thanks.
More questions? Then maybe let me ask a question. I understand that you consider mass deformation, which is Q exact, right?
Mm-hmm.
So does your approach include sometimes integration of this mass deformation in the spirit of string theory?
No, not really. So the dependence of this mass deformation is sort of, you can say it's pathwise constant, or so it depends on the chamber in which you take mass. So I mentioned that the parameter space is separated into chambers, and the walls are where the hypermultiplets become massless, and things happen when you go across those walls. But when you stay within the chamber and just send mass to infinity, nothing depends on that. And well, in fact, we work in the limit of this mass going to infinity. And yeah, so we are really in the field theory context, at least for now.
Okay, maybe a question from Jerome Gauntlet.
It's actually just a comment, and it's probably complementary kind of work that I wanted just to mention that I did with some postdocs, Igal Arav, Matt Roberts, Chris Rosen, and my graduate student Matthew Chung. But it's from a gravitational point of view when we constructed configurations which separate two different theories by an interface, preserving superconformal invariance. So we call these RG interfaces. So the nice example that we had was a gravitational solution that has n = 4 Yang-Mills theory on the one side, and the so-called Lee-Strasser fixed point, which comes from an n = 1 star mass deformation. And the configuration is supported by a mass deformation of n = 4 Yang-Mills theory, and realizes a superconformal symmetry on the interface itself. So it's, as I said, it's probably complementary work to what you're doing, but it may possibly play some role, or you might be able to use some of your techniques in that for that particular context.
Larger limit.
Yeah, thank you. Maybe I am actually. I suspect that it is included in the sort of larger list of references. I don't know, but you can send me the link just in case it's something I didn't know about.
I will do.
Thank you.
Gregory, do you have another question?
I do. Maybe it's a better question. So you have a raising operator. So presumably you also have a lowering operator. So now there's some nice algebraic relations like Serre relations and their generalization in the Yangian.
That's right.
Is that going to involve some kind of operator product of interfaces and things like that?
Yes. So in this approach through R matrices, all the relations, they just follow from RTT relations of the Yangian. And you get RTT relations by considering several walls. So the simplest setting is imagining that you have 3 masses. And so you have M1, M2, M3, and then there are walls where M1 equals M2, M1 equals M3, and M2 equals M3. And then you say go from one chamber to another, to the opposite chamber, and you can cross the 3 walls either this way or in this way. And that gives you the Yang-Baxter equation for the R matrices, which implies the RTT relation for the Yangian that you get using this construction. It would, right, yeah. So that's the simplest way to see it.
I think we should proceed to, thank you very much, Mykola. Let us proceed to the talk of Kevin Costello about 4-dimensional integrable theories from twistors.
All right.
Okay, so should I start, Andre?
Yes, please. Mm-hmm.
Okay, so thank you very much for inviting me to this fascinating conference. It's a real honor to be here. So what I want to talk about is something I've been kind of obsessed by during the pandemic, which is a class of unusual 4-dimensional quantum field theories, which have no supersymmetry, but which appear to have many properties in common with 2-dimensional integrable theories. So you might ask, well, why I'm interested in these things? Well, these models are non-normalizable. So normally people would say that non-normalizable 4D Lagrangians are just junk. There's too much ambiguity in building the theory at the quantum level to do anything meaningful. But these particular theories, by using twistor space, we constrain the counterterms very tightly. So we get a family of 4D theories with the following very strange properties. So the first property is that the orgy flow is periodic with imaginary period. This is a property I can prove in perturbation theory. The second property is they have some analog, not quite fully understood, I have to say, of the Yang-Baxter equation. So they have strings and they scatter in a way where an equation like Yang-Baxter holds. And the third feature of these theories, which I was really excited about over the past couple of weeks, is that the celestial holography program, which aims to describe the symmetries arising from soft theorems in terms of chiral algebras, works really beautifully. And so I've been working a bit with this on Natalie Piquet, and we conjecture, and we have some evidence, that in this case, celestial holography is the same as twistor holography, which is something I was studying with Natalie, and with Davide Gaiotto, and which many other people have studied. So to start, I think I will, one sec. I'll start by reminding people a little bit about background on what twistors are. So twistors have appeared several times in this conference, so I hope people are reasonably familiar with them. So twistor space, that's introduced by Penrose, is the following complex threefold. It's just O1 plus O1 over CP1, and it's an open subset of CP3. Now, as a real manifold, it's simply a product of R4 and CP1. So this means we could take a theory on twistor space and dimensionally reduce along the CP1 to get a theory on R4. I'm going to be interested in holomorphic theories in twistor space, things like holomorphic Chern-Simons. But because this factorization as R4 times CP1 is not as complex manifolds, but only as real manifolds, when we reduce to R4, they'll become ordinary theories in R4. Ordinary but very interesting theories in R4. So it's important to mention that this procedure of dimensionally reducing from twistor space to R4 is much more robust than the familiar KK reduction. There are no KK modes. So that the reduction procedure is just exact. The reason is holomorphic theories don't require a metric to define them. The metric only appears in the gauge choice. So the size of CP1 is only a gauge choice. So we get the same thing if it's big or small. And it's possible to make this argument completely mathematically rigorous in perturbation theory. Okay, so how can we build holomorphic theories in twistor space? Let me give some examples. So this kind of thing was, of course, studied many, many years ago by Penrose. And one basic example is the Penrose-Ward correspondence, which you can formulate as saying that holomorphic BF theory in twistor space is self-dual Yang-Mills in R4. So self-dual Yang-Mills has this very simple Lagrangian where B is a self-dual 2 form. And if we were to add a BB term, this would become full Yang-Mills. Okay, so another famous example is the Witten-Berkowitz proposal for the twistor string theory. They show that holomorphic Chern-Simons on a superversion of twistor space becomes self-dual n equals 4 Yang-Mills. And to get away from the self-dual limit, one has to study the D strings. This was generalized by Bowles, Mason, and Skinner, and they discussed versions of this with less supersymmetry and matter. And a really beautiful example is Penrose's non-linear graviton construction, which gives self-dual gravity, and that was extended to the supercase by Mason and Wolf. So these are all like beautiful examples. However, they all have one big defect. They're one loop exact. So perturbation theory stops at one loop. So they're kind of close to being free. So I'm interested in theories which are like that, but a little more rich. So I want to study something which does not stop at one loop. So the first class of models I want to mention is holomorphic Chern-Simons theory in twistor space. So holomorphic Chern-Simons theory is a simple Lagrangian. I take the Chern-Simons Lagrangian for a 0-1 form and a Calabi-Yau, and I wedge it with the volume form. Twistor space is not Calabi-Yau. However, it has a meromorphic volume form, which here I've written in coordinates, where Z is the coordinate on the base and VIs are on the fibers. Now, it turns out that this holomorphic Chern-Simons theory, and indeed the associated topological string theory, makes sense as long as we impose suitable boundary conditions on the gauge field, on the gauge fields at the locus where the volume form is a pole. So I announced a result in a talk a while ago, and a lovely proof was given by Biddleson, Skinner, and Penna, is that if we built this holomorphic Chern-Simons theory, and the corresponding four-dimensional theory is the WZW4 model, which was, I think the Lagrangian was first written down by Donaldson, but it was studied in detail by these authors. And it's a very simple and beautiful, in my view, model. So it's a natural deformation of the four-dimensional sigma model. The fundamental field is a map to the group. The Lagrangian has two terms. First term is just the usual sigma model Lagrangian. And the next term, well, what it is you note that the sigma model in dimension 4 has a topological U1 symmetry associated to pi 3 of the group. I can think it's a 3-sphere which wraps multiple times the group. So I can couple that to a U1 gauge field. So the next term is saying I just put a background U1 gauge field whose field strength is the Kähler form. And these coefficients have to be normalized correctly, and it gives you a very nice model in 4 dimensions.
What is J?
J is the current. So if we reduce to 2 dimensions, Middleton and Skinner and Peta show that it becomes the principal chiral model. Because this model, the Lorenz group is broken, what we get in 2 dimensions depends exactly how we reduce. So turns out that there's a single parameter in the way we reduce, and that matches the parameter in the principal chiral model. Okay. So this is all fun, but it's all classical. So it turns out it is pretty difficult to construct a field theory in twistor space. Most of the time, the classical field theories people have written down for many years just don't exist. Well, the one for n equals 4 self-Julian angles does exist, actually, but many of them don't. The reason is holomorphic theories in 3 complex dimensions can have one-loop anomalies associated to box diagrams like this. So one can do explicit Feynman diagram calculations. We use the local index theorem, and you find that the gauge variation of such a diagram will look like this kind of thing, where I take trace of the derivative of the trace of the field strength cubed times the gauge parameter. Fortunately, sometimes these anomalies can be cancelled by using a topological string version of the Green-Schwarz mechanism. So that happens when the group is SO8. The reason is there's a certain trace identity with the group SO8, similar to the one needed for the hexagon diagram in the familiar Green-Schwarz mechanism for SO32. So in this case, the anomaly associated to the box diagram cancels with the exchange of a closed string field. So here's the proposal that in the whole universe of all possible 4D QFTs, there's some tiny number which lift to local field theories in twistor space. So the main example I'm interested in today is WW4 for SO8, plus the closed string fields. And there's a couple of other examples. Basically, one can think about engineering examples by studying anomaly-free string theories, taking a supersymmetric sector of them, compactifying it to twistor space. So that gives you a bunch of examples associated to, for example, associated to free folds fibered over P1 where the fibers are K3s. We'll give you a task examples. My favorite example is associated to topological strings on a version of twistor space built from a genus 3 hyperelliptic curve. I won't have time to talk about that. Okay. So one can ask, what are the closed string fields? It turns out on twistor space, it's given by a version of Cadaver-Spencer theory. And if you analyze what that becomes in real space, the fundamental field of Cadaver-Spencer theory is a 2-1 form. I can take its primitive and view it as a 1-1 form and integrate it over a CP1. I get a scalar field on real space, which I'll call rho. And this scalar field should be interpreted as the Kähler potential. The reason is the WZW4 model is defined on Kähler manifolds. So it has a Kähler stress energy tensor, which I can couple to a 1-1 form. And if you compute how it's coupled, dd bar rho does indeed couple to the Kähler stress energy tensor. But it also has some self-interactions in kinetic term. It has this weird 4th order kinetic term, Laplacian squared. And this interaction, these dimensions and symmetry will tell you that these are the only 2 possible terms, and then you can compute the relative coefficient. Looks like that. I was unable to compute beyond cubic order, so I don't know what happens to order 4. It turns out that the equations of motion are that this, at least to the order I can compute it, or that the scalar curvature of the modified metric vanishes, or is proportional to dd bar of the Kähler stress energy tensor. So that is, this model is a simple model coupled to gravity, and it comes from a local theory on twistor space, and I'm claiming it has a bunch of nice properties. Let me see what the properties such theories have. The most important one is that though it's non-normalizable, the counterterms are uniquely defined. The reason for this is that, most of the counterterms you might imagine writing down are not local on twistor space. Say, for a scalar field, phi to the n is n local. I have to integrate over n points on twistor space. There's a very tiny number of actual local counterterms. So some years ago, not that long ago, C. Lee and I proved that holomorphic Chern-Simons plus Kodaira-Spencer theory for SO8, the counterterms are uniquely fixed by asking that there's no anomalies. This tells us that WZW4 plus the gravitational field has a canonically defined quantization. Sorry, I should stop at 11:10. Is that right, Andre?
Yes, you still have 9 minutes.
Oh, 9 minutes. Okay, good. Okay. So another important property is that the org flow is periodic. So let me explain why this is. Org flow is simply scaling spacetime by a real number. On twistor space, I can scale spacetime by a complex number because all we do is we multiply the fibers by an element of C star. Because it's a holomorphic theory, everything depends holomorphically in how I scale it. So it's very, very formal and trivial argument that tells us any holomorphic theory on twistor space gives rise to a theory on O4 where the dependence on the scale extends analytically to C star. This implies there can't be any log divergence. It also implies any familiar theory, essentially any familiar theory, cannot arise as a local theory in twistor space, with the exception of CFTs. So Losov et al., I mistakenly claimed that there was a one-loop divergence cancelled by Green-Schwarz at a different talk. This turns out to be incorrect. The right result is by Losov et al., that the first divergence can happen at 2 loops. Okay, so I'll try and move a little faster. So these theories, because they come from theories in twistor space, holomorphic theories, topological strings, they have D strings, just like in the original proposal of Berkovitz and Witten. So these D strings can wrap a curve in O4, and they're really strings because their position is dynamical. Now, very simple formal arguments tell us that these D strings can't touch, that because they don't touch in twistor space, we can move them past each other without introducing any singularities. And similarly, I can move them past each other in this way. It turns out this is something you can check that only works because of the Green-Schwarz mechanism. I believe I can show that this fails at 2 loops without the Green-Schwarz mechanism. Here's my hope. So these 4D theories, which have these D strings satisfying a Yang-Baxter-like equation, are just as nice as the familiar 2D integral models. So I was unable to really compute anything about the scattering of strings, but I would really, my dream is that it's solvable in the same way the 2D models are. So this is really a hope. So the last 2 minutes, I want to explain quickly a little bit about what we're looking at with twisted holography and celestial holography. So in twisted holography, well, we build a chiral algebra controlling scattering of states in some supersymmetric subsector of n equals 4 Yang mills. So the basic example is we, take SL2C, which is ADS 3 times S3. And on the boundary of ADS 3, there's a chiral algebra, and the OPEs describe scattering. So we can do the same construction for twistor space. We can build a chiral algebra by studying states sourced by operators at infinity, and it works just the same. And the conjecture is that this chiral algebra just is the same chiral algebra as people studied in the celestial log literature. So we computed this. We start with self-dueling Mills theory. We do this computation. We get exactly the same algebra studied in this paper. Probably, I haven't done the computation, but it's probably true with the gravitational sector as well. Of course, this is anomalous. This theory is anomalous, as I mentioned. I'm not quite sure what that means for the celestial log proposal. For the WZW4 model, if we run the algorithms from the celestial log literature, then we do find that the states they write down of negative dimension are exactly the states sourced by the single particle primaries in our chiral algebra. When we can compute the tree level OPEs, they seem to match. In this case, we can also go beyond tree level, though. There's a nice computation by Lorgat, Musavi, and Joe. And they computed some subleading correction. It's no longer a Lie algebra, leading to the possibility that the soft theorems at the loop level may be described by these kind of strange Yangian-like quantum groups. Okay, I think I should stop there. I'm a minute over. I'll put the last slide up, but I want to read it.
You are not over.
I'm not over? Oh, okay, sorry.
Allow it to speak a little more.
Okay, so let me do the last.
You have 3 more minutes.
Okay, well, why don't I read the last sentence? So I was going a little fast because I really thought I was over. So these examples, it's also fun to think about back reacting a D1 brain. And this will bring us to a situation much closer to usual holography. We do this in twistor space. What it will become is like some quotient of SL2C by the integers union some stuff. We can ask what happens in real space. If we place a vertical D1 brain over the origin, it back reacts by changing the Kähler potential in this way. I add on log of the radius. So it's natural then to conjecture that if we take this WZW4 model into back reactor geometry, the chiral algebra, which controls scattering of states, is exactly the large end limit of the chiral algebra on ND1s. This chiral algebra is known in the literature. It appears for a certain family of n equals 2 theories with SO8 favor symmetry. Okay, so I will stop there, and I hope my talk was not too fast to be coherent.
Thank you very much, Kevin. Let us see if there are questions. Yes, Hiroshi has a question.
Yeah, so I have a question. So I'm assuming that you are doing quantization in 6-dimension twistor space rather than 4-dimension. I think there is a distinction between them, even though there are no Karuta-Klein mode, because there could be different on-share degrees of freedom. And you said that almost all counter terms local in 4 dimensions are non-local in the twistor space. I think that's the reason why you say that this is spatially non-renormalizable, but still makes sense. But could there be counter terms that are local in the twistor space?
Asking, are there any counter terms that are local in twistor space?
My question is that could there be counter terms that are local in the twistor space? because you said that you do not have to worry about counter term in 4 dimensions because almost all of them are non-local in twistor space. But if you are quantizing in 6 dimensions, should we also be worried about other types of counter term?
I suppose the issue in 6 dimensions is more with anomalies, and because in 6 dimensions it's a gauge theory, whereas the gauge symmetry is broken when you go to 4 dimensions. So the question of whether there are counterterms are you look at the algebra of local operators, which is entirely concentrated in positive ghost number, and you're interested in things of ghost number 3 because you want to descend them 3 times, or of ghost number 4 because they will contribute to anomalies. And so there's some cohomology computation which is quite challenging. But it seems like so we did these computations with C. Lee, and we found there was nothing in the relevant ghost numbers except for the Green-Schwarz, except for the box diagram anomaly.
So in the direct 6-dimensional analysis, there are no conceivable counterterm. Is that a statement?
Yes, but only when you couple the open and closed string sectors.
Okay. So anomaly guarantees that there are no counterterm.
Yes.
Thank you.
Mykola.
I have 2 quick questions. So first, silly question. I missed, what was the PCM in your slides? What is the, what does?
Oh, sorry, but it's principal chiral model.
Ah, okay. And you said that the RG flow is periodic with period 2 pi I. Is there like some scale because it's a dimensionless number? What does it mean? There's a period 2 pi I.
I mean, it means something very simple. Like if this is a statement in perturbation theory, and if you look at all of the counter terms, they're functions of the cutoff, and you try to extend them to analytic functions of the cutoff, and they have no branch cuts. That's what it means.
Okay.
Question from Atul. Atul Sharma.
Yeah, I wanted to ask, in the gauge theory case, in the 4D Wessumino-Witten case, you can at least, from what I understand, start with the 6D theory on twistor space and exactly compactify on CP1 and get the only interaction that you get a J-cubed interaction, no higher order terms. So what is your procedure for the corresponding Kähler-Scalar case that is generating all these higher order tower of terms?
Well, I think it's a little misleading to say there's no higher order terms because the WZW4 Lagrangian takes such a simple form because you've written it as an element of the group instead of the exponential of an element of the Lie algebra. It's like the element of the Lie algebra is what corresponds to the 6D gauge field. And if you expand it in terms of the logarithm of sigma, it's a huge series. So anyway, so my procedure here was I found it pretty challenging to compute directly. So what I did was I know that whatever you do, if I take the OPE of this scalar with its derivative, this is going to be analytic in X. So it's not going to have any logs. And then you compute like each of these terms separately introduces some log, and you have to arrange the coefficients so that it cancels. And that method will continue as you go further if you want to, but it becomes more challenging.
Oh, I see. So you haven't started with a 6D theory for the Kähler-Scalar, like the Jern-Simons theory for the gauge case.
No, like there is a Lagrangian. I mean, it's kind of stupid that I wasn't able to do it directly. In principle, you could do the same procedure you do for the WZW4. I just found the direct analysis kind of challenging, so I took the shortcut.
Sure, thanks.
Question from Edward Witten. Unfortunately, only 1 minute or so.
What would your Lagrangian have been in 6 dimensions for the gravity?
Sure, it's so the fundamental field is like a 2-1 form.
Yes.
Which I can also view as I can also view as a Beltrami differential with certain zeros.
Yes.
And then I just do the usual kind of Kodaira-Spencer thing. So you take literally the usual Kodaira-Spencer launching for a Beltrami differential. And then you notice that if I started as a 2-1 form, I turned into a Beltrami differential at a certain zeros, and those zeros cancel any poles in the 3 form. So it makes sense.
And that leads to your theory with the row in 4 dimensions.
Yes. So the reason is there's a constraint in Kodaira-Spencer theory, I'll call it eta, as that this is closed, so I can take the integral over P1, del inverse eta, that's rho. And then you can compute explicitly the 2-point function of that one itself, and you find that's log, and that tells you that this has to be the kinetic term. And I found the interaction challenging, but I did this kind of procedure that I knew it had to be analytic. So.
Thank you.
I think that unfortunately we have to proceed to integrability discussion. Thank you very much.
Thank you.
Before we start, let me remind that people are, of course, welcome to continue asking questions on Slack, on the Zoom chat, or during the discussion. After all, this is an integrability-like theory, so I hope we can continue there. So let me pass the floor to Volodya. Volodya and Grisha have 20 minutes. That part is the strict part. And we will follow with 30 minutes of questions and comments from everyone. And that's the relaxed part. So Volodya, you have, I believe you are muted. Or no, you are not muted, but I cannot hear you. Good.
Do you hear me? Yes. And
yes, I can hear you and I can see your slides. So I will start counting 20 minutes now.
Okay. Thanks for this. Hello, everybody, and thanks for this opportunity to lead this discussion. I should warn from the very beginning that it will be mostly the integrability in planar n equals 4 super Young Mills. And let me first declare that n equals 4 super Young Mills and ABJM model are integrable in the planar limit, as we now know. And the global questions which we want to pose in our presentations with Grisha Korchemsky is, first of all, what does it mean, integrability in this case? What are the origins of this integrability? What is achieved due to the integrability? And what else might be achieved? Okay, then one must say that the origins of this integrability are still quite mysterious, because our final results, our most advanced results, are based usually on matrix bootstrap approach, which is far from being proven for more or less complicated sigma models, maybe only for the simplest ones like Sine-Gorton. So from the very beginning, we have to ask the same question here in the string sigma model, in the dual string sigma model. But we have some exact observations. First of all, we have explicit integrability in the lowest orders of perturbation theory in n equals 4 Young Mills. Then we have also perfectly visible classical integrability on the Worldsheet of sigma model. And even the rest of it are some mysterious constellations in planar perturbation theory or on the string Worldsheet. For example, the highest transcendentality graphs survive for physical quantities by the reasons which are not understood. And many of you working not necessarily on integrability in n equals 4 Young Mills observed a lot of mysterious facts. That's why so many calculations are possible in this theory. But there is little glimpse of hope for this understanding. This is a fishnet CFT limit of gamma twisted n equals 4 super-Young mills. I think it's a real chance to understand what where this integrability comes from. I will explain it later in a little bit more details. Okay, and now, first of all, the problem of planar spectrum of anomalous dimensions is a great success story, thanks to the efforts of many people over maybe 20 or more years. This scheme of integrability allows us for calculation of any local and sometimes even non-local operators at any coupling analytically. So the ultimate formalism, which probably hardly can be improved anymore, but still something much simpler than the original functional integral, is the so-called quantum spectral curve, QSC, which Shota already presented a little bit in his talk. I will probably have a little bit different angle of view on the formulation of QSC, and roughly it's a Riemann-Hilbert, a nonlinear Riemann-Hilbert problem on a few Baxter functions, labeled in such a way that they can be placed on so-called Hasse diagram and 8-dimensional hypercube. So there are 128 such functions. 8 corresponds to the rank of symmetry group PSU 2,2/4, and they're related by a known algebraic Grassmannian structure, and also we have enough of knowledge about their analytic structure. Those Baxter functions are a direct generalization of standard, this couple of solutions of Baxter equation in Heisenberg spin chain, and Shota already mentioned this story. And in the spin chain, they're simply polynomial encoding all the beta roots of the Magnon rapidities. But of course, in our string sigma model, this is a much more complicated object. The analyticity is much more complicated than just polynomial. To precise a little bit the labeling of the functions, I go to a simpler 4-dimensional hypercube Hasse diagram, which corresponds to GL2,2, for example, where you put on one of the vertices the Q empty set function, then the next, the nearest neighbors are Q1, 2, 3, 4, the single index functions. Then the neighbors of 1 and 2 on the next level, the neighbor of 1 and 2 is Q1, 2, etc., etc. So up to the full set function Q1, 2, 3, 4. So you can imagine the same on this 8-dimensional Hasse diagram. But these Q functions are not independent, they're algebraically independent. They are related on each face, on each 2-dimensional face. They are related by Plücke relations. For example, the product of Q1 and Q1 to 1 to 4 is the Wronskian of Q12 and Q14. This determinant with characteristic shifts of the spectral parameter by plus minus I/2. And then all these relations reduce the number of independent Q functions to essentially 8 here or 4 here. And then we have to impose some analyticity conditions, namely for some of these functions, we know the large U asymptotics, which are completely related to the charges of the solution and to the symmetry charges, like anomalous dimension delta and conformal spins, or 3 R symmetry charges for another function. So I give only examples, of course, but we know all this information. And also on the physical sheet, we have only only one singularity, only one type of singularities, namely two branch points placed exactly at the points minus G and G, where G is the 't Hooft coupling. So it's the only place where the 't Hooft coupling enters the construction. And then we have the most important, we have gluing rules, the monotony, which relate some of these functions by complex conjugation. So that's it. And once you fix, for example, the integer charges S1, S2, and J's, and you can solve the problem and find the discrete spectrum. You read off the discrete spectrum of delta from some of these Q functions. That's it. And more or less, this is the construction. I think it is mathematically quite beautiful, and it begs for the analysis by mathematicians, and maybe the attempts to find more of such quantum spectral curves, maybe, and the corresponding theories which are behind them. Of course, the same exists for ABJM, but that's it. We don't have any other theories of this kind of algebraic and analyticity properties describing higher dimensional quantum field theories. Okay, and then QSC provides
9 minutes.
5 minutes. Okay, great.
You are at 9 minutes. I'm just warning. You are at 9 minutes. Right
9 minutes. Okay, 3 minutes more. I'm done. So a few results obtained from this scheme are regular weak coupling expansion, then strong coupling, a few others, but not yet regular expansion. There are other approximations, quite successful approximations like large spins, next to next lowest order for BFK spectrum, quasi-exact numerics, easily 5 digits or more, 50 digits or more of precision for anomalous dimensions. This graph for Konishi was shown already, more or less the same graph by Shota, and I like this spectacular graph which shows the twist2 operator anomalous dimension as a function of complex spin. And then I also stress that we see in quantum spectral curve the ADS CFT correspondence in full glory. Okay, and then the last slide, the fishnet CFT limit, which corresponds to large complex twist and weak coupling. The theory, one of the theories of this family has only one coupling. Two complex scalars with one coupling, sort of chiral coupling, and this theory is explicitly integrable in planar limit in all loops. The integrability corresponds to the non-compact SU2, 2 spin chain. QSC exists only in the form of TVA, not of the QQ system. Feynman graphs for this theory represent the regular lodges. That's why it's fishnet structure. That's why it's an integrable statistical mechanical model. But there exists a more complicated dynamical fishnet, integrable fishnet structure for the most general three coupling model of this family, of this fishnet family. And you have three lines corresponding to three families of bosons and fermions. They are both here. And these lines can move through each other, giving every time a new graph if you cross the crossings by other lines. And you can always decode each of these structures in terms of Yukawa couplings and 5-4 couplings in an unambiguous way. So this is another sort of dynamical fishnet, already more complicated, whose integrability is still to understand in terms of spin chains. But I think it hints on maybe a regular dynamical lattice structure of planar graphs in the full n=4 superior nuls. So this is one of the hopes of understanding integrability. Also, the explicit ADS CFT picture was constructed for fishnet CFT in terms of so-called fish chain model. a chain of particles on ADS or string bits on ADS. And there is also an interesting integrable model for O1 5 sigma model for dense fishnet graphs, hinting on another stringy feature of fishnet CFT. And also the fishnet CFT for two scalars exists on any dimension and is also integrable in the planar limit. Here I stop and I pass the baton to Grisha, and later we formulate our open problems and questions. Thanks.
Thank you very much. Let's thank Volodya while Grisha sets up his share screen. And while Grisha sets up, I remind people that there are also more questions on Slack that Grisha and Volodya collected from the community. So.
Do you see my slides?
Yeah, please take over.
Yeah. So we believe that planar and L4 theory is integrable, and basically this statement based on two observations. One observation comes from weak coupling, that we encounter spin chains computing dilatation operator, and strong coupling we know from IDS-CFT that we're dealing with sigma model which is integrable. And we believe that IDS-CFT organized in such a way that integrability is preserved all the way when we go from weak to strong coupling. I'm not going to discuss the proof of the statement. I will take another take on it. Namely, I will take it for granted the integrability is there. I will try to use integrability to discuss possibility of computing various quantities in N=4 planar L4 theory of arbitrary valued hoof coupling constant. And as we have heard yesterday, there was quite spectacular progress in solving this theory. And here I have selected 3 different problems. And these problems are ordered in the exponential order of complexity. So the first one is spectral dilatation operator. And as Volodya explained you, quantum spectral curve gives you solution to that particular problem. Second one, on-shell scattering amplitudes. And finally, there is correlation functions. So our goal is just to compute all those quantities in planar L4 for any valued hoof coupling constant by making use of integrability. It's a natural question to ask what do we expect to find at the end of the day. And before answering that question, let me take one step backward and let me take as an inspiration what you know about classical quantum integrable models, the field that has been developed over many decades. And what you know from those models is that sometimes the dynamics, which looks very complicated in the regional coordinates, becomes kind of simple if you do appropriate change of the variables, which is canonical transformation in classical models or unitary transformations in quantum models. And one example, which already was mentioned by Schlotterer yesterday, is, for example, separation of variables, planning separation of variables. So the main lesson which you could draw from integrability continuing L4, one has to find appropriate coordinates in which complicated dynamics of planar L4 becomes kind of simple. And let me show that this philosophy goes very well if you go from scattering amplitude to correlation function. And as warm-up example, let's give an example of so-called cusp anomalous dimension, which is quantity which is important in all gauge series because it appears, for example, as controlling infrared divergence of scattering amplitude. It controls large spin asymptotic anomalous dimension, correlation function, etc., etc., etc. So what do we know about this quantity? So if you just start from V coupling, you turn on machinery of computing Feynman diagrams, and you will find corrections which are shown on this plot right here. And you see that if you start increasing number of loops from 3 to 4, you have an unstable result. And actually this dashed line, which indicates the positional stability, is exactly the radius of convergence of this V-coupling expansion, which Schlotterer mentioned yesterday. So now if you go to strong coupling and you invoke IDS-CFT correspondence, you have a well-defined setup which allows you to compute cusp anomalous dimension of strong coupling by going through some classical quantization of Gapser-Klebanov-Polyakov string. And this way you get some series which turned out to be non-barrel summable. And finally, you go to integrability and you remember what I just said. You identify right collective coordinates. And those coordinates turned out to describe the dynamics of magnons in the SL2 spin chain. So when you take into account those collective coordinates, you could formulate certain integral equations. And those integral equations allow you to interpolate between weak and strong coupling. So this is exactly the philosophy which I mentioned. You have weak coupling, strong coupling, you have collective coordinates, you formulate dynamics and collective coordinates, and here you set up. So now let's push this philosophy going to the on-shell amplitudes. So as I told you, on-shell amplitude is much more complicated quantity. And therefore, you would expect to have some additional property which will simplify your task. And those properties go to the name of symmetries. So what was found that there is two remarkable properties, the amplitudes in planar Electron 4. One of them has to do with duality between amplitude and light like Wilson loop. And this duality goes as follows. So you start from scattering amplitudes with k, etc., k1, etc., kn on shell momenta of scattered particles. And then you go to dual descriptions, putting some axes in such a way that the segments stretch between neighboring axes is exactly light-like momenta corresponding to scattering particles. So in this way, you map configuration of on-shell momenta and configuration of points in Minkowski spacetimes, which form naturally null polygon. And then you define Wilson loop on this particular null polygon. So the statement goes as in planar NCL4, amplitude computed for configuration of on-shell momenta coincides with the Wilson loop computed on this red null polygon. And this property becomes quite important because it allows you to continue further and formulate another property, which goes under the name of dual superconformal symmetry, which essentially is a statement that Wilson loop in this dual configurations has conformal symmetry, which translates into dual conformal symmetry of the amplitude. And being combined with conformal symmetry, this gets promoted to Youngian symmetry. Youngian symmetry is synonymous of integrability. So these two symmetries simplify a lot computing amplitude both at weak and strong coupling. At weak coupling, this allows you to formulate a regular procedure of computing fast integrand that define class of function and then bootstrap functions based on analytical properties. And strong couplings this give you possibility to compute amplitude to the minimal area in a DS5 attached to the polygon null Wilson loop. And then you go to the final coupling. And as I told you, the key point going from final coupling to identify this new collective degrees of freedom, which simplify your task. Is those new collective degrees of freedom are naturally defined on the Wilson loop configuration, which is shown here. And they describe the fluctuation of surface which are stretched to this polygon contour. So those fluctuations could be identified as fluctuations of JKP strings propagating across this polygon. And then you could formulate kind of generalized OP expansion. It's generalized in the sense, instead of talking about short distances, we're talking about the limit. One of these kinds cast point becomes kind of flat. And this flattening corresponds to going situation which you have n points to n-1 cast points, which are quite similar to the OP philosophy in the context of the normal operators. So if you push further this ideology, you could come up with very precise formulation of this now Wilson loop, which according to our duality is exactly the same as amplitude, which factorizes the product of objects which are called pentagon transitions, which could be bootstrapped by integrability. And in the context of the OP, those pentagon transitions are analogous to the conformal blocks. So this, once again, becomes a very well-defined definition of the Wilson loop, which although involves infinite sums and integrals of a number of excitations propagating and their quantum numbers. But as it stands, it's a well-defined object. Unfortunately, it's very hard to compute it for final couplings, but there is some progress in computing in different kinematical limits. So this is a story with amplitudes. Now let's continue further, and then now go to correlation function. As I told you, correlation function is even harder than amplitudes. So how could one proceed here? So we start with the simplest correlation function, which correlation function of half BPS operators. So this is the half BPS operators which built out of the R copies of the scalar field, appropriately symmetrized with respect to R indices. And this operator has some R charge, and the length of the operator or its scaling dimension is exactly the same as R charge. Now we want to compute correlation functions. The first and trivial correlation function is the one which involves 4 operators. So once again, you turn your Feynman diagram technology, and you could show that those correlation functions could be bootstrapped quite efficiently to first few order of perturbative expansion using superconformal symmetry plus additional OP constraints. So then you go to strong coupling, and strong coupling at DSCFT allows you to map the problem into problem of computing scattering amplitude on DS space. And there was recently progress in computing some loops on gravity side and string sides. And then finally you come to the last step, and exactly the same as before, we have now to define those new degrees of freedom. And these new degrees of freedom appear in the framework which goes under the name of hexagonalization approach, which already appeared earlier this morning. And the idea of this approach is just to look for the all Feynman diagrams you could consider computing those correlation functions as forming some surface in the 't Hooft sense. And then you look for the surface and you start to thinking about the surface as a worldsheet of some effective integral two-dimensional theory. So then what you do, you chop it into different patches. In total, there are 6 patches excuse me, there is 4 pages for point correlation function with some holes representing operators. And then what you do, you resolve each page by putting some full sum of the states. And those states describe the fluctuation at the top of the surface. So in this way, this correlation function could be written as these new effective coordinates into the product of 4 hexagon form factors. And hexagon because it comes from the shape of these pages. Each of these form factors could be, again, bootstrapped for any value of the coupling constant. And in this way, you get a representation for full-point correlation functions, which again is infinite sum of the integrals of those fluctuations which are propagated at the top of each hexagon and the cross hexagon. And those L's correspond to the R-charge which are transferred from one hexagon to another one. So similar to the amplitude story, this is a well-defined representation, but it's very difficult to use it because of technical difficulties of computing. There is different limit you could consider, and one of the limits correspond to the situation when each of these operators sitting in each of this hole has infinitely large R charge. In this situation, this full-point correlation function in this effective dimensional field theory factorizes into product 2-point function. Each of this 2-point function becomes effectively octagon. So this is exactly the octagon which appeared yesterday in the talk of Frank Caronada. And this octagon becomes a very nice object because, first of all, you could obtain very concise representation in terms of Fred-Gordon determinants. And secondly, applying the techniques for those Fred-Gordon determinants, you could get quite a number of analytical results. So this becomes the end of the story. So I try to show you that if you knew from the very beginning what are collective coordinates and what effective dynamics of those coordinates, there is quite a regular way how you could go from the first principle definition of the object to some representation which make use of the integrability. So with this, I will finish and I will give word to Volodya because now we switch to the open questions.
You are, though, out of time, so you might consider to just flashing them or being super, super brief, because, yeah, otherwise we'll run out of time for the free discussion.
Yeah, I think I mostly already pronounced this kind of problems. I think it's good just to flash and then.
Well, let's go then to the final slide. Let's be then brief. So basically, if you're talking about questions, first of all, questions, as I already mentioned, you could find file with all questions in the Slack. But basically, there is 5 class of questions which one might ask. So the first one is the one which addressed by Volodya. What's the origin of integrability? Second, given information which we provided you, do you believe that we solved the theory? Third question, is it possible to think about n equal 4 theory, some kind of deformed version of the fishnet theory? Fourth question, we didn't discuss non-planar correction yet. So there's quite a critical number of evidences coming both from correlation functions and amplitudes, so the integrability actually holds in kind of non-trivial way beyond planar limits. And finally, the last question, which is most interesting to my mind, if we will solve n equal 4 theory, what did we learn about QCD? And there's quite a number of lessons to learn. So I think at that moment I stop, and probably now time to look for questions.
Thank you very much. Let's thank Volodya and Grisha for a very nice discussion, for a very nice introduction. And as I said, we move to the informal part, and we can go a bit into the coffee break. That's totally fine. So
can I stop sharing screen? Pedro, I stopped sharing screen.
Yeah, why not? Yes, you can stop sharing. Yeah, people are encouraged to check the questions, especially on Slack, where there are many. You had some questions in the chat.
I want to ask a different quick question about the last point that was raised in the open questions. I guess what are some viable, plausible proposals about integrability in non-conformal planar gauge theories?
Could you repeat the last part of the question? I didn't hear.
It's about the last question that was in the last slide. What are some plausible proposals about the meaning of integrability for non-conformal planar theories, such as large N pure YAMYOs?
Sorry, before you answer, Grisha, let me remind people something I forgot. Sorry. But that turning on your camera for this informal part is very nice, if you can, if your internet allows, of course. Yeah.
Oh, the problem. Go on, please. Okay, what I propose, I couldn't. Let me now return to my slides, just to show you the slides which I skipped. Yeah, this one. Do you see my slide? Hello?
Yeah, we can see your slide. Yeah. We can
So coming back to the question, so about integrability in non-conformal, non-supersymmetric series. So there's different questions about non-supersymmetric and non-conformal. But if you're talking about QCD, so these are the worst scenario in the sense that you're breaking everything possible, right? You have broken conformal symmetry, broken supersymmetry. So what we know, and these are experimental results, that if you're thinking about places where integrability could appear in QCD, then it appears exactly the same places where you see it in equal 4. Namely, you go to dilatation operator. So even though conformal symmetry in QCD is broken, you know how to control it. You have Kalan-Semantic equation, and you could define dilatation operator in Kalan-Semantic equation. Then you would find that in general, dilatation operator in QCD is broken, but there is some sectors, special sectors, in which it's integrable up to 2 loops. And let me remind you that starting from 2 loop, you're already sensitive to conformal symmetry breaking. So, which means that this integrability I'm talking about, it knows about breaking conformal symmetry, still there is integrability. And second example is amplitude, scattering amplitude in the radial limit. So if you're taking scattering amplitude, for example, 2 to 2 gluon scattering in QCD and equal 4 theory, you will see they're completely different. But if you go to the radial limit, which is the limit when you fixed momentum transfer T fixed and S goes to infinity, you will see that this 4 gluon amplitude in QCD looks remarkably similar to an equal 4 result. So in that sense, what I'm saying is that there is these facts which come from the explicit calculation of certain coordinates in QCD, but we don't understand where they come from. And if you believe that explanation n equal 4 about integrability comes from a DSFT, then you should naturally conclude that if similar phenomenon happens in QCD, you should go through some dual stringy description. And given the fact that integrability appears on the radial limit is exactly the limit when you're expecting QCD described by some string theory, one may speculate that it's some kind of effective QCD string we should know about integrability.
Sorry, can I interject?
Hey, may I add something? I wanted to also to notice that actually Lipatov's Lagrangian for regiized gluons, which is at the heart of this integrability in QCD, is in the same integrability class as fishnet, two-dimensional fishnet theory, which I presented. They have the same set of integrals of motion, so it's another interesting link. That's it.
Maybe let me ask a question about that, Volodya. Is this Lipatov story seen in experiments?
Actually, some people said that it will be never seen, but recently I heard that something was seen, and maybe there are some people in the audience who heard more about it. But I heard that in some experiment it was seen.
I could comment.
In Grisha, yes. Mm-hmm.
So there are some things which you have to take into account, namely talking about n equal 4 theory, talking about perturbative theory, meaning that there is no genuine non-perturbative effects aside from the instant ones. QCD is completely different theory in the infrared, right? So now the question is, if talking about if you go to the experiment and you try to do some comparison between what the computed perturbative expansion and experiment, you should always be careful about what you're comparing. Namely, have to be sure that the number you want to compare with have the same origin. So now what people measure in the experiment, for example, they measure total cross-section. And recently, there was a lot of data coming from LHC, for example, for proton-proton cross-section. And people use previous data from Tevatron, proton-antiproton, to look for the difference between proton-proton and proton-antiproton cross-section. And the reason why the difference is important, because it gives you access to so-called order.
Mm-hmm.
So now, what happens if you go to the proton-proton cross-section and you plot it as a function of total energy? You will see that it grows, and the way how it grows like a power line, with the exponent being roughly speaking, 1.08, which normally called soft polymeron. Now, if you go to Lipatov approach, more precisely, it's BFK approach. The BFK approach resumes certain class of fishnet diagrams, and they give you a number, which, depending on different estimates, is 1.2. So now the question is, if you compare number 1.2 and 1.08, they look similar. But the main problem is that one number comes from the perturbative physics deeply in the infrared. Another comes from the perturbative. So therefore, even though this number looks quite similar, they have completely different physics behind them. And talking about Oderon, for the Oderon story, even more interesting, because for the Oderon, integrability gives you predictions that the cross-section should be constant. It shouldn't depend on the energy. And what I mean by this, following with the Beth-Kelly approach. And quite surprisingly, experimentalists found more or less the same. So they found the difference between proton, 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 and proton, roughly speaking, flat in energy. So once again, you have two numbers which you take with grain of salt, because the difference, you're comparing two quantities which come from different parts of physics, infrared versus infrared, ultraviolet. So the fact that they agree is nice, but I wouldn't say that this is a proof that the perturbative approach successfully described the perturbative physics.
I'm not sure if Gabriele Veneziano wants to add something. If he raised his hand at this point, I don't know if he was waving or not, because you don't have your camera on.
I had a little comment on this point. I wasn't waving. What I can't understand is how the Regge limit can be integrable in pure Young-Mills, because that would amount to really solving the confinement problem altogether. I can understand that you can approach perhaps the so-called hard Pomeron, but the soft Pomeron, I don't think you can expect it to be calculable by an integrable theory. Do you agree?
Probably I expressed myself in the wrong way. I completely agree with what you were saying. And basically, this was my punchline. I was saying that if you're thinking about QCD being n equal 4 plus something, I was saying n equal 4 is completely different exactly for that reason, that it's trivial with infrared.
Yeah.
QCD is non-trivial infrared. And
since you were talking about the Regge limit is soft physics.
Exactly.
And
but
so
it has some tail. If you think about the Regge trajectory, there's always tail of Regge trajectory, which goes to negative t, where you're expecting to find some perturbative contamination, let's put it this way.
Okay.
So I would be very pessimistic about possibility of pushing this perturbative Regge trajectory towards small values of t, not to say positive value of t. But for negative, large values negative of t, you might say that you may stay still in perturbative regime, and there you could draw perturbative diagrams and try to describe behavior.
Is there, can I also ask, is there in Lipatov's approach the concept of planarity or not?
It's a very interesting question. What happens that if you don't impose planarity constraints, so you imagine you sum all diagrams exactly. Then if you go to high energy limit, the so-called leading logarithmic approximation, you will find that non-planar diagrams don't produce leading contribution. So non-planar diagrams suppressed in the energy limit, but starting from two, starting beyond linear order, when you're looking about corrections to, so you're looking for the intercept, you're looking correction which goes as a second power coupling constant. There, non-planar corrections contribute, and moreover, what you could show that in QCD, those corrections have a tendency to be unstable. In a sense, they become sensitive to the infrared physics in QCD.
Thank you.
Let's maybe move to Costas. Leonardo waved, so maybe this is still related to this point.
Yes, I had a related question. So we learned about the effective action on long strings, and presumably from lattice data, we can match the leading W4 correction that we learned about. And then there should be a simple question whether that action is integrable or not.
I perfectly agree. Moreover, this
what is the answer known?
Not that I know. If somebody could comment on this, I don't know the answer.
Thank you.
No, but probably I see Victor probably should know the answer about two-dimensional QCD.
Well, I think that this is related to what Sergey talked about and in the discussion that followed Sergey's talk. Yeah, we have some conjecture. I mean, the action data suggests that the flux tube is close to some integrable theory. So we know that it's not exactly integrable, of course. And then we have some conjectures that in the UV limit where you can possibly connect with perturbative QCD, integrability gets restored, but in some subtle way. We don't have an exact formulation, but the idea that there are some hard processes on the string worldsheet that are integrable.
But we know for sure it is not exactly integrable.
Yeah, that we know for sure. Both in 3D Young-Mills and in 4D Young-Mills from lattice simulations, you can see the level splitting that prohibits integrability. In 4D, we know it theoretically. In 3D, we know it experimentally.
Thank you.
Kostas?
Okay, I have a different question. It's about anomalous dimensions. Do we know the anomalous dimensions of multitrace operators for any value of lambda?
Oh, yeah.
Once again,
if we know the dimensions of multitrace operators.
The multitrace operators. This is, I think, a subleading order already. I mean, it seems that in the large limit, we only can say something about local single trace operators. Double trace would mean for me already a sort of a limit of 3-point function, yes, when you put two of them together. So I'm not sure.
But let's say if you took a 2-point function of two multitrace operators, you can read off the dimension as a function of lambda to leading order in the large n limit.
That's true, but I don't think quantum spectral curve formalism can be used directly for such calculation. At least I don't know any of such suggestions.
Or if we're just focusing now on single trace operators, maybe there is a comment. Somebody.
There is what?
No, I mean I thought I heard somebody talking, but a different question. So if we're just focusing now on single trace operators, do we know things like what is the number of nearly marginal operators as a function of lambda, kind of generic properties and properties of the spectrum of this type?
Because if you're staying in the planar limit, once again, there's two different questions. If you're staying in the planar limit, those double trace operators kind of trivial. Everything factorizes in the product of the correlation function with single trace.
That sense, yes. But for example, if you couple the double trace with single trace, then it smells like a 3-point function.
Then you would need to consider higher point functions. You need to solve first the high point functions. So then, of course, you would be able to read them off as a limit, coincident limits, or factorizable limits of those. That I agree. The question is whether already we have the technology to have this answer without doing this process.
It's an interesting question. Who knows? Maybe the QSC can be generalized in this way. At least it seems simpler than just 3-point function. Yes.
Let me make a small comment that one thing that we don't know yet how to tame completely are extremal processes from integrability, where, so for example, 3-point functions, which are extremal, which are ones where these double trace operators are most important, are very, very tricky because they're very singular to deal. It's typically easier to deal with things that are not extremal. One thing that is possible to do, but hard to do in practice, is to compute a 4-point function of single trace operators at genus order, at non-planar and so on. And then from the OPE, you could read off the dimensions of double trace. But in practice, it's not yet doable because of the complications that Grisha explained, that there are too many sums and integrals to do at this stage.
There's one exception. So if you remember the story of octagon from Frank Coronado, so if you take about 4-point correlation functions operated with large R charge, so 4-point functions, then you take OP, as you said, across the diagonal. So you have 4 operators which sitting at the corner of the rectangle, so that they talk, each operator, because of the choice of the parallelization, talks only to its neighbors. And then you could take OP across the diagonal. These two operators don't talk to each other, therefore in the OP, there will be no singularity associated with the short distance between them. From this OP, you do have access to the double trace operator with a large R charge. And then if you look in the papers on the octagon, you will see there is a explicit expression. And there basically, you could find those anomalous dimensions for these particular operators. for any value of the coupling constant.
The other question, the kind of how many nearly marginal operators you have as a function of lambda? Is this something? No.
Single trace or double trace?
Single trace.
Yeah.
It's a question about solution. Let's say it's a question like in story to B times Z. So let's just draw the analogy. So at one loop level, you know the anomalous dimension described by eigenstates of the Kazakov spin chain. So more or less you're asking the question, you specify quantum numbers of the operator, you're asking how many states you could get a solution to those to be that equation. I think these are well-defined questions. I don't know the answer. Maybe Vladimir knows.
Not really, not really.
More questions? There is a question. Marcos Spradlin, do you want to unmute yourself and ask the chat question, or if you just write no in the chat, maybe I can.
Is there is an analog of the Landau equation of strong coupling? Okay.
Okay.
What is the question?
Is there is an analog? If Mark could repeat, say himself.
No, he might be in a place with too much noise. So he was asking if there are analogous equations like the Landau equations at strong coupling. So these are equations that govern the singularities of amplitudes. So do we see them at strong coupling? I think it's.
The answer is yes. And if Sasha Zhiboyedov is there, he's better qualified to answer the question. It's about bulk singularities. So if you're thinking about computing for 4-point correlation function of the simplest operators, similar to those.
Yes.
Let's go on.
Yes. So if we have correlation functions, then if we're talking about perturbation theory for correlation functions in the bulk, it is again a product of propagators integrated over the vertices, and then one can derive Landau equations in exactly the same way. That's what we discussed with David and Juan. Now, my understanding is that what Marcus is asking is probably slightly different, which is that if we have a in the bulk perturbation theory is the answer, I would say yes. But if we are talking about finite lambda, and if the question is what are the singularities at finite lambda and integrability, okay, yes, then I don't know, but maybe someone else knows.
Yeah, I can just make a comment that I mean, some people in integrability are trying to compute more than 4-point functions, and it looks a little bit silly. Why more than 4? Precisely because of that. This is one of the main reasons, because we want eventually to go to 6 points and understand this resolution of this bulk singularity and how it works.
But sorry, I think he's asking about the scattering amplitudes, gluon scattering amplitudes.
Not those strings.
Yeah.
Okay.
That's precisely the point he was making.
Sorry, I missed that one. Okay, sorry.
And I guess you should be able to answer, no?
No, because clearly I was looking for waving hands, and then I heard half the question. So maybe if you summarize the question again, and maybe. But let's pass to Igor so that I can breathe again.
Yeah, thanks for the discussion. I guess QCD we know is hard. It's unlikely to be exactly integrable just from numerical data from the lattice. And N=4 super N mills has these wonderful properties, but there are lots of theories in between. So one question could be, is there some other really nice some theory with reduced supersymmetry, which happens to be exactly planar integrable? I mean, just to add to the pool of questions.
I think Eli has something to add about this. Can you add, Eli?
Yeah, we put out a paper a few days ago where we look at n equal to 2 superconformal theories, and we find signs of integrability, but it's of elliptic type. So it's much more complicated than what we know from n equal to 4. And of course, what we did is one loop. So there is really a lot to, it's really just the beginning.
But maybe one thing which I didn't have to say about, that there is some property which we observed for quite a number of different quantities, which already mentioned about this maximum transcendentality weight property. And this property has standard experimental observation. Namely, you take certain quantities and equal for theory, and then you go to other series which have less supersymmetry. And then what you will see is that for special class of quantities, not general statement, but special class of quantities, you will see the final result looks like you take n equal 4 result and you add something which looks much simpler. So this property, we don't understand neither where it comes from equal 4, but it's kind of experimental fact. And equal 4, its property is there. And it's not clear why this property get deformed if you go to series with less supersymmetry.
Well, let's have Schlotterer is waving. He might have something to.
No. I just had like a follow-up question to Ellie. So you found some nice structure, but it doesn't seem to fit in the ordinary framework of integrability, because if you want to construct a state, like a two-Maginot state, then there is some like a process in which the momentum is not conserved, right? If I understand correctly. And
So this is correct, but this is because we wrote, at least for now, we wrote everything naively. We using momenta. The correct way to do this is to start using theta functions, because the model is really elliptic, and there is not clear what will happen to all of these momenta. So this is an exercise to be understood, basically. I hope that all of these extra shadows of the momenta will all fit in the theta function, but this is some serious work to understand.
I see. And there is like a no known like a useful method to construct like a higher conserved charges and like algebraically construct the states.
No, there is algebraic Bethe ansatz for elliptic models, for dynamical elliptic models. But I mean, I can say some things. I don't know how long I should go on for. So the trick is you need to understand what is the corresponding vertex model. So for n equal to 2 theories, now we say that there is a 15 vertex model. And first of all, you need to properly construct this model. Maybe this model has a star triangle relationship. So this is where you start from. This is the equivalent of the Young-Baxter equation. And then you need to translate this to Felder type dynamical Young-Baxter equations. This is the framework.
And do you think you can go to Veneziano limit?
So the Veneziano limit, so in this paper, we studied mostly this Z2 orbifold of n equal to 4. In order to study super QCD, you just take one of the coupling constants and you send it to 0. So of course, yes.
I think Volodya has a related comment.
Yeah, I wanted to say that to me, to search for new Lagrangians, which might be integrable, is a very hard task. But once I remember, Sergio Ferrara asked me on one of my talks, can you use this quantum spectral curve construction, like this hypercube, with Q functions with certain conditions on them? Can you use it for the search of new integrable theories? So you start from the beginning of the from the integrable structure. Supersymmetry is a very nice and simple thing. It's said like a rotation of this cube on a certain angle. So it might be a search tool for new such theories. That's what I wanted to propose. Integrable theories. Or at least we might understand why only those two are integrable, like EBGM and n equals 4. Is the scheme is so tight that it admits nothing else.
I have a kind of a silly question for Volodya. Volodya, how do you imagine the 4-point function of 4 20 prime operators looking like in the final solution? These operators are trivial, they are vacuum, right? There's nothing. What will it be? Some integral over some Q functions, some multiple integrals, some integral equation, some functional equation. How do you think the 4-point function of 420 prime operators will look like?
The only idea which inspires me here for the answer is that I would think of the corresponding group structure, namely to look for the analogy with Klebsch-Gordan coefficients. you know, integrals of characters, etc. I think this gives the analogy, like from the matrix models, what are these 4-point functions, multi-point functions, and of course, Q functions are a new object for with respect to simple group theory, but still these integrals of Q functions remind me the integrals of characters. And transfer matrices are the generalizations of characters in integrable theories. So I would search in this direction for the, I mean, of course, the final answer for correlators should be using the QSC data you formulated as some integrals. But I think the analogy should be of this kind. Clebsch-Gordan coefficients quantized in some way.
Thank you. I suggest we thank Volodya and Grisha for this beautiful discussion. But as usual, we have time before the next talk, so we can continue a bit more informally. Let me confirm at what time is the next talk. So it's at yeah, we have plenty of time. So we can stay a little bit longer and ask for more informal questions, assuming Volodya and Grisha have time, and maybe in 5-10 minutes.
But Peter, coming to your question about possible answer, I think one thing which comes to my mind, so you have this octagon. So octagon appears in the limit when all our charges are large. Now thinking about developing like perturbation theory. So I want to now to expand it in the vicinity of this like infinite R charge, just to write something which looks like perturbed octagon. Doesn't make sense?
It makes sense, but it looks super hard to then get some intuition. Yeah, maybe the first turn.
Well, already the first term, right? Already the octagon doesn't look particularly simple, right? In the sense that you don't have complete expression. You have kind of representation in terms of some functional indeterminates, but these are objects which themselves they're well defined. But what do you expect from them? I mean, you have complicated object. It's already giving a complicated answer.
Yeah. Yeah, there I will first try to interpret physical the equations you got, this integral and differential equations. If one could interpret them physically, then I think that could be very powerful. Right, you have these integral equations, integral differential equations that in principle allow you to compute this octagon that Frank described at finite coupling, right? But as far as I understand, it's mathematical, right? You start with a determinant, you manipulate, and you get some equations. And those equations are beautiful, but then what is lacking there is an interpretation. And this is like adding some extra particle or something. Then maybe that would be the way to go, because if you could interpret them, maybe you could then generalize to any size.
And what about strong coupling? Did you manage to get a minimal area for the octagon?
Can ask, yeah. Gabriel has a camera on. Matthias, I'm not sure if he's here, but yeah, they were trying, but yeah, Matthias is not online. Yeah, I don't know if Gabriel wants to say something.
Simon wants to say something.
No. But the short answer is.
I missed the question. What was the question?
So the question is the following. So there are some correlation functions that at strong coupling have a geometrical interpretation, and they are given by a minimal area problem where you have to compute the minimal surface that ends on some geodesics that are inside ADS. So it's a different geometrical problem. It doesn't end on the boundary, it ends on some geodesics. And so since it's just a geometrical problem of computing some minimal area, it's like Gross-Mende, but in ADS. But we were not able to compute this minimal area, not even numerically yet. We are trying, we will still try a little bit more, but it's not easy. Maybe, I heard yesterday that Frank and Simon were also trying, so maybe they have a more clever approach.
No.
Now we put it on hold a little bit and we moved.
We failed also, so I mean, we haven't tried that hard.
But okay.
But it's a very well posed problem. There is an answer. There is an answer that the area is big.
Sometimes no, the fact that you know that there is an answer, you know there is a solution, right? So
what was the question?
Huh?
Can I ask a question to Ivan Kostov or Valentina Petkova or others? So this kernel that gives the octagon, determinant of 1 minus k, this Freedom determinant, like they wrote in a beautiful way, and I'm wondering if they had some comments on how to interpret it. Maybe does it look like this kernel is solving some difference equation or something, the sort of thing that we do in the quantum spectral curve, or if they noticed any connection of this type?
Oh, no, unfortunately, we didn't notice a difference equation satisfied by this kernel. And well, I don't know. We found a very simple fermionic interpretation of the octagon. But well, I don't know. There is well, in the limit, in the light-like limit, Grisha and Andrei, they found that you have this Toda field theory equations, but in the general case, I cannot say.
Yeah, I meant in the, for example, this is Kerr's deformation that takes the gamma octagon to gamma cusp, and we know, for example, how to think about the cusp in this dimension in terms of solving a difference equation from, well, a quantum spectral curve type equation. Yeah, just wondering if this sheds any light on how to interpret it.
Vladimir,
yeah, I have a question to Pedro, Shota, and maybe some other people working in this direction in the audience about the large radius limit. Can we? I mean, some people already work on 1/n terms and 1/n corrections, and those correspond to string amplitudes and really to the things which would be very complicated to compute even in flat space. Do we have a possibility to sort of make a concurrence to the people who compute the amplitudes, string amplitudes in the flat space? Can we go with all these nice integrability results to the flat space background on the string side and compute some amplitudes? What is the status of this?
It's totally impossible for now. That's super hard, that regime, because those are small strings that are already very hard, right? Because you want small strings like Konishi or something to scatter. So I think that non-planar corrections for small strings from integrability with genus, it looks, there are many problems we would have to solve before, I think. But maybe Shot has a more optimistic view.
For the instanton correction, actually, I think it's easier. So there is actually a chance that in I think within a year we can get something.
For the exponential.
The first instanton correction, to the 4-point function.
But from integrability or from?
Yeah, from integrability.
Okay. Because it's a different type of non-planar. Is it a good?
Well, it's just like a disk, like a bunch of disks.
Right. Okay.
I could add to this about instantons for 4-point function. So if you know there is a limit in which 4-point function goes into Wilson loop. So then you could use, and this relation should hold independently on whether planar limit or not. So then you could use this relation to predict instanton correction to this 4-point correlation function as this light-like limit when all adjacent operators are now separated. So there is prediction for instanton correction to 4-point function in this particular limit.
By the way, about my previous question about sorry to go back, but since you asked, I asked back. So my previous question about the form of the 4-point function. What about in the fishnet? Can you remind us, can you write the 4-point function in the fishnet as in terms of the quantum spectral curve or something like that, or it's a different approach?
Well, we have explicit expression for 4-point correlation function for special class of the operator fishnet theory. And those expressions are explicit in the sense that at V coupling. I mean, we have a representation, like integral representation, which holds for any value of the coupling constant. But if you expand it, let's say at V coupling, you could systematically go on, and we kind of know what class of function will appear there. So
yeah. Does it follow in this picture of group theory picture of Volodya with some kind of quantum Clebsch-Gordon or something?
Unfortunately, functions which appear in these expansions, they are known since 10 years. So these are kind of new functions which have been introduced by Francis Brown, single-valued harmonic polylogarithm. So these are kind of
that's weak coupling. That's weak coupling. We don't have weak coupling in this session. No, I mean, at finite coupling.
I would say already at weak coupling, you will have troubles understanding of what are these functions, the meaning of those functions. If you now ask me about finite coupling, it's much worse, right? But
the formula is there. I mean, you have simple representation for like integral representation for this finite coupling, but maybe it's hard to investigate. But the result is there for these particular 4-point functions.
I see.
But not for more complicated ones. This is for the shortest operators, which pass. I mean, it's like fishnet length 2 only.
Any other questions, speculations, comments, remarks?
Can I ask a question?
Of course.
I may have, so may have been already addressed because I was away for some time. So what is the status of integrability for ADS3 with Riemann flux? And what kind of observables can we compute from integrability in that case?
ADS3, integrability for ADS3.
Yeah, with Riemann flux.
It's much less advanced, I must say, due to all these new degrees of freedom which appear, zero modes, etc. So the quantum spectral curve is not constructed for this theory, unfortunately. But I don't know more details. I'm not really a specialist in this particular theory. Maybe somebody else can comment.
I think there's some psychological stumbling block there because there is no speed chain picture, no decoupling, some manageable. There's no manageable description of decoupling, and that really helped in ABGM and then class 4. While the string side looks very similar.
Yeah. I don't know if Fondrini is here. There was he had some nice paper recently about hexagons in ADS3. But... If there are no other questions, we can have a 10-minute break before the next talk. So let's please thank once again Volodya and Grisha for
everybody.
Thank you very much, and we can continue on Slack, of course. So.
Hey, good day. Eric, are you ready to do the sound check?
Yes, I'm here. Can you hear me?
I can hear you well.
Okay.
And do you see my slides?
Yeah. So let me just double check with Pedro, maybe. Hi, Pedro.
Hi.
Yeah,
please go ahead.
Yeah, so Ali talks for normally 40 minutes plus 10 minutes question. Is that right?
Perfect.
Okay, and then Lorenz is 25 plus 5. Is that right?
Exactly.
Okay, great.
And warnings, you decide with them what they want.
Yes, that's right.
Okay.
And the other thing I wanted to ask you is, so anybody who wants to ask a question unmutes themselves, right? I don't have to do anything.
You don't have to do anything, but you call the person to ask the question.
Of course, right.
And can you all see if I go back and forth with my slides?
Yes.
Yeah. Okay. And you also see my cursor?
Yes.
Okay.
Make you co-host here.
Oh, yeah. And do you think we can also co-host my student, Carlos Rodriguez, just to have a backup option? Okay, good. Yeah. Yeah.
Could you also co-host me, please?
Yep.
Okay.
So yeah, let me just do the other one.
Okay, just to test the emergency mode if my other computer decides to die.
Hi, Lorenz. I don't think we ever met, but
yeah, hi.
If I give you a 5-minute warning, is that okay?
That's great. Yeah, thanks. Yeah, let me also share the screen. Right, that works, right?
Yep.
Great.
Here. Okay. Okay, I've switched off my emails. So Eric, you can only reach me via Zoom.
Okay, sounds good. Okay, so let's resume. Welcome to the afternoon session of today. So our first talk will be a review talk, and it's a pleasure to introduce Oliver Schlotterer from Uppsala. Oliver.
Yeah, thanks a lot, Eric, for the introduction. And thank you so much to all the organizers for bringing together this beautiful conference and for giving me the opportunity to speak here. Yeah, the topic of this talk is string amplitudes. Fortunately, with this kind of audience, it's easy to motivate why we should be excited about string scattering amplitudes. First of all, the field started with an amplitude computation or proposal. And furthermore, yeah, string amplitudes have been continuously a valuable gadget to study the low energy effective regime of your favorite string theories. And in particular, amplitudes are key quantities to do precision tests of string dualities, usually at definite orders in the inverse string tension alpha prime. But also outside string theory, there are reasons to be excited about string amplitudes. Say if you're interested in perturbative gravity, you want to, for instance, test the ultraviolet properties of various supergravities, or you want to conceptually relate gauge theories and gravity, then you can use the double copy property of the closed string spectrum, that gravitons are, loosely speaking, squares of gauge bosons. And this, in particular, in the field theory S matrix, we can see starting from string calculation and taking alpha prime to 0. So string amplitudes being a valuable way of understanding the Bern-Carrasco-Johansson double copy of perturbative gravity. And also in math, it's quite common that mathematicians are collaborating with string amplitudeologists, simply because there are similar mathematical fun topics coming up in, say, number theoretic questions and the specific worldsheet integrals we have to do in alpha prime expansion of string amplitudes. And also particle physicists are often joining the table because Feynman integrals tend to have the same function spaces. Yeah, I'm thinking of zeta values, polylogs, elliptic versions, modular functions, more on that later in this talk. Yeah, so these are 3 pillars of motivation to kick this talk off. But most of all, this is a moment to say thank you into various directions. It's a really fortunate time to work on string amplitudes because we had support from so many different directions. So there's first of all in the string theory literature an enormous support, say from the foundations of the Ramon-Eves-Schwarz or the pure spinor formulation of the worldsheet model. There is a continuous inflow of new ideas how to deal with the subtleties of the respective formalisms, new ideas how to interpolate between them to find new models that unify the advantages of both. And also the ambitwister string theories that we heard about yesterday from Lionel and Freddie. Also those are strong support even for the full-fledged superstring with all its alpha prime dependence. You will see a 3-loop 4-point highlight of this. And yeah, I mentioned this fruitful intersection domain with mathematics. There's a continuum of people whose interests are somewhere between number theory and algebraic geometry. It's usually hard to categorify the individual contributors in mathematics. Maybe Zaghe and Zerbini might be more on the number theory side. Maybe Brown and Dupont are more on the algebraic geometry side. But all this to say, there are various mathematical perspectives that help us tremendously to understand the low energy structure and of string amplitudes. And this flow of ideas goes hopefully into both directions. So conversely, string amplitudes turned out to be pretty inspiring, say, to explore new kind of mathematical structures, new systems and modular forms. So I hope that all this inspiration transfer is seen as mutual from all these directions. Yeah, let me try to get a bit more specific about the mindset and content and outline of this talk. Let me start with a cartoon of a typical perturbative expansion of a string scattering amplitude. So as you know from the opening line in the textbooks, we are, in case of closed string scattering, supposed to go over Riemann surfaces of various genera, sphere, torus, and higher genus version for tree level 1 loop, 2 loop, and beyond. And now at each loop order, we are supposed to integrate over the moduli space, the shape of that surface and the way to put punctures on it, each puncture for one of the external states. And to be more precise, the external states occur via vertex operators, where, say, the polarizations and momenta of the scattering states are stored. And now, depending on which formalism you use, you have a bit more stuff inside the correlator, say B ghosts and certain regulators in the pure spinner, or picture changes in the RNS. I don't want to go into much detail here, but these are some spurious punctures that in the end of the day can be discarded from the correlator if you massage it good enough, at least to the low loop orders that I'm about to discuss. So accordingly, I'm not explicitly referring to supermoduli here. To the loop and leg orders to be discussed in this talk, we do have representations where the odd moduli are gone. Okay, and yeah, from this cartoon of how a string amplitude is computed, the structure of my talk is as follows. I'll spend the first half talking about new results for the integrands, how far you can simplify these correlators with vertex operators and more stuff. And then in the second half of the talk, I will look at the task of doing the moduli space integral. To be honest, I'm integrating more over the punctures than the moduli, but that's a different story. And yeah, we'll tell you some news about what has been done in the alpha prime expansion of these configuration space integrals. That's the structure of this talk. So let's start going into new results on the integrand side. Okay, here's an overview slide from which you can see that at tree level and one loop, we are already in pretty good shape. How well we know the massless amplitudes for the type 1 and type 2 superstring. So several disclaimers throughout the talk. It's massless states that I will scatter. It's for the moment in 10-dimensional Minkowski, though we are obviously all burning to take this to the ADS and so on. And yeah, I will specifically talk about 2-loop 5-point and 3-loop 4-points, where we have new simplified results for these correlators, free of spurious locations of BGOs or PCOs. And yeah, this is what I will describe in detail in the first half of this talk. Now, I do promise closed string amplitudes, but maybe it's quite economic if we truncate the problem to an open string calculation. So for the integrand / the correlators, this can be done using chiral splitting. So we would like to decouple the left and right moving worldsheet degrees of freedom, which at tree level is no problem. But starting from one loop, there is naively a coupling of the left and right movers. Namely, they share a zero mode, which you can interpret as a loop momentum. Literally, the loop momentum in a Feynman graph if you take the alpha prime to zero limit. So that loop momentum is the only obstruction to having a factorizing correlator at, say, genus 1 and 2. And let's get rid of this obstruction. Let's outsource this finite dimensional loop integral from that big path integral that defines the correlation functions. So all the integrand results that I will are tailored to the so-called chiral amplitude, here denoted by this calligraphic F, indexed by leg order n, loop order g. And this is really an open string quantity. It's evaluated at fixed loop momentum, all the simplifications being carried out at fixed loop momentum. And once you have this in an optimized form, then you just square it, loosely speaking. You adjoin a second half of it, and you then perform the loop integral. So this will be the mindset. That's why all the correlators you're about to see are about open string variables, which is tremendously reducing the complexity. So here's a warm-up, approximately 15-year-old result about 2-loop 4 points. The chiral amplitude, so the massless states are represented by gauge boson polarization vectors plus their gauge-geno partners. And yeah, all the polarization dependence in this 4-point function, it enters in a manifestly gauge invariant way using the linearized field strength. And the contraction is done using the standard T8 tensor as described in the textbook, as you know it already from tree level and one loop in the 4-point function. So what else is around in 2-loop 4 points? Now, these chiral amplitudes are form valued. And since we are at genus 2, there is more than one abelian differential. So we need to take care of these form degrees of freedom for each of the punctures. And it comes out of the calculation in both RNS and pure spinor that these holomorphic differentials come in anti-symmetrized combinations, these deltas here. That's quite beneficial, both for modular invariance of the closed string, but also for a nice field theory limit excluding triangle diagonals. Okay, so in both RNS and pure spinor, these anti-symmetric combinations were found, decorated by momenta. And this is the hardest part, to find the second line here. But there is an easy part in the first line, which I haven't described yet. This is the so-called chiral-Kober-Nielsen factor, simply the contribution from the plane wave, e to the ikx, which are present in each vertex operator. So that's a contribution you can foresee on the spot from bosonic string technology. So since the 70s or 80s, we have been knowing that guy for all loops and legs. So it's essentially some exponential of prime forms together with some decoration by loop momentum. Okay, so I hope that this review is setting the stage for the 5-point result, which is a rather recent thing from last year. So we have found a simplified expression for the 2-loop 5-point chiral amplitude for any 5 massless states. We have them for both gluons and gluinos, since the answer is written in so-called pure spinor superspace. So all the kinematic factors are encoded in certain superfields, where a theta variable targets the gluon and gluino components. And if you want to have the specific, say, gluon component, just pick up the right order in theta, which is automatized by now. And apart from kinematic factors, we again have form degrees of freedom. Whoops. So as before, there are these anti-symmetrized combinations, but now in a 5-point function, we are dealing with 5 forms. So yeah, that's why there is one additional omega here. And there's a free index, I, which runs from 1 to 2 over, say, the cohomology. And accordingly, this kinematic stuff has a free index. So this stuff here is what we call the subcorrelator, where all the kinematics can be found. And that free index can, for instance, be placed to a loop momentum. So now the zero mode structure in the pure spinor formalism leaves enough room to pick up a loop momentum. But also you can afford to do an OPE and then catch certain Worldsheet functions that are singular as the punctures collide. For sure, we must be careful about the periodicities of a higher genus surface. So what's the periodic way of implementing a simple pole? That's traditionally a logarithmic derivative of the prime form. But since we have already peeled off the form degrees of freedom, you only are interested in the leftover theta functions that go along with the forms here. And so these are the basic ingredients out of which the subcorrelators are made of. I don't expect you to go in detail through the combinatorics. Quite generally, you will see several formula of several similar length. Don't bother to look at them in detail. It's more to give you a flavor of how long these expressions are once we have simplified them far enough. Okay, so the structure is we have a couple of kinematic superfields decorated by certain Worldsheet functions with simple poles. And you may ask how to find that. Well, of course, explicit computation is one way, but here in this pure spinor work, we had a kind of bootstrap program to get the exact answer from an ansatz. Namely, by looking into the zero mode structure of the non-minimal pure spinor formalism, we can already anticipate which kind of superfields have the right to participate. So there's a vector building block T and a scalar building block S. Ask me later if you want to see it in full glory. But we can be pretty sure that everything at chiral amplitude is some permutation of these two guys. And what you can also learn from the zero mode structure in the pure spinor formalism, you can at most have one loop momentum or one OPE. So out of this alphabet of kinematic factors and Worldsheet functions, there's not much what you can do, in particular if you impose some consistency conditions like BRST invariance and homology invariance. So let me elaborate on that second point. Ideally, we would love to see a doubly periodic function as the punctures go around the A cycles and B cycles. But since we are in chiral splitting and deal with meromorphic building blocks, we don't get double periodicity. We get certain B cycle monodromies, inevitably, but they are such that they cancel upon loop integration. They can be compensated by a very specific shift of the loop momenta by external momenta. Yeah, so in summary, by combining homology invariance and BRST invariance, we get a unique way of composing the building blocks that were identified by pure spinor calculations, giving a unique result. And that, of course, deserves to be tested. So, for instance, we have checked that you get the correct supergravity amplitude. As a nice bonus, you get the supergravity limit even in a double copy form, where all the kinematic numerators, all the polarization-dependent things, obey the Bern-Carrasco-Johansson duality between color and kinematics. Okay, so supergravity limit is one of the many checks, but needless to say, our chiral amplitude is supposed to get the alpha prime corrections correct. It's supposed to work as far as you have the power to alpha prime expand the integrals. And specifically, we have tested the subleading orders in alpha prime to play out nicely with S duality of the type 2b superstrings. So we have checked whether the R to the 5th interactions that you can read off from the alpha prime expansion, that they do what they are supposed to do by S duality. And as a particular highlight of the 5-point functions that you don't have at 4 points, you can start violating the U1R symmetry of type 2b supergravity, and say couple 1 dilaton phi to 4 gravitons. And yeah, this is an extremely interesting corner of type 2b amplitudes violating R symmetry, which are purely stringy effects, and which in the full duality invariant picture are associated with modular forms of the axiodilaton. And I think we have seen something about that in Konkal Ben's talk yesterday. So these are some checks of the 5-point function, which also constitute the motivation that there are a lot of interesting new aspects at 5 points, which you don't have a fair chance of spotting at 4 points. So this is a major motivation why it's important to have control in the multi-leg regime. Yeah, so this was about pure spinor-induced result for 2-loop 5 points. There is an ongoing RNS calculation. Okay, let's say we already have a result, namely that a first principal calculation in RNS for the external bosons is giving the same result as doing pure spinors and then extracting the external bosons from the theta integral. So this is to say we have another high loop, high leg case of where RNS and pure spinor work out together and give the same amplitudes. Now, giving you more details of the calculation, maybe we leave this mostly for the private discussion. We have been using the same kind of formalism that Eric and Fong used 2005 to compute the 4-point function. And of course, it's a bit more work to do that's at 5 points, more sums over the spin structures, and more work to be manifestly independent on the gauge slice, namely the locations of some supercurrent insertions. Okay, and one multi-loop highlight, which is a very, very recent paper. This concerns 3-loop 4 points. There is an impressive proposal by Yvonne Geyer and Ricardo Montero and Ricardo Muchao-Stark. Just came to the archive 3 or 4 weeks ago. So these guys have started from ambitwister arguments and have found a beautiful construction to come up with a proposal to the full-fledged chiral amplitude for superstrings, which you can use to alpha prime expand as high as you have control on the genus 3 integrals here. So some of the things may remind you of the 2-loop results. So here is a delta similar to the anti-symmetrized differentials at 2 loops. Now it's a 3x3 determinant. And maybe the most subtle corner of the proposal is here, where you have a bunch of Sager kernels. So these are the fermionic 2-point functions in the RNS. And of course, we ultimately want to sum them over the even spin structures of the worldsheet fermions. And yeah, the spin sums have not yet been evaluated for us, but the authors have precision control on the degeneration limits of that contribution here. So they have given good evidence why this is a good choice. And yeah, the chiral measure made of chi8 and psi9, sorry not for defining it here. So these ingredients have already shown up in earlier literature. not only here, but also similar expressions have been seen in work of Eric and Fong from 2004. Yeah, so this is the recent proposal for the full chiral amplitude. And of course, we already have an impressive 3-loop result from 8 years ago, done by Carlos Mafra and Humberto Gomez, who computed the low energy limit of 3-loop 4 points and showed that the d to the 6 r to the 4th contribution ties in with S duality. So Carlos and Humberto had a substantial part of the chiral amplitude on the previous slide. Namely, they had the contribution which does contribute to d to the 6 r to the 4th. But that stuff below here, this only kicks in at higher order, namely d to the 8 r to the 4th. That's why it wasn't needed in earlier work. But instead, this contribution down here is crucially contributing to the super Yang-Mills and supergravity limit. It has crucial contributions to the Feynman diagram numerators, say for a tennis court graph depicted here. And this was actually the driving force, how Ricardo Square and Yvonne got their proposal. They insisted that these Bernd Carrasco-Johansson dual numerators should pop out in the degeneration limit. And this is what they managed to use constructively to build up the correlator. And part of the deal was to have a good nose for the modular forms that you need to decorate it with. I mean, it's in the heart of the ambi-twistor method at work that in the first place, the field theory numerators give you a certain degeneration limit. But the proposal is for generic values of the omega AAs. So it's the nose for the right kind of modular form that allowed Yvonne and Ricardo Square to really go to a generic point in moduli space. Yeah, so this is a really cool example of how ambi-twistor methods succeeded in giving a highly useful input for conventional strings at finite alpha prime. So this brings me to the end of the integrand part of this talk. So now for the rest, I will consider the chiral amplitude to be there and tell you a bit about the leftover job to perform integrals, and specifically order by order in alpha prime. So let's switch gears to the integral side. And this is a good moment to get rid of the loop momenta. So we have the loop momenta in the form of Gaussian by virtue of the chiral Kober-Nielsen factor. So we can, without much trouble, perform a Gaussian integral over loop momenta. And this is the moment where modularity can occur or can be manifested. So if you arrange the result of the loop integral and the Kober-Nielsen factor in a good way, you get a modular invariant Green's function, the so-called Arakelov-Green's function, if you make use of momentum conservation. So this is, if you wish, a higher loop version of the logarithm that you know as the Green's function at genus 0. And say at genus 1, that Arakelov-Green's function is a certain completion of log theta 1. And it's engineered to be, among other things, modular invariant. And it's engineered to integrate to 0 with respect to a suitably chosen volume form. So the alpha prime expansions that I will describe in the subsequent slides, it concerns the result of expanding that exponential and integrating polynomials in Green's functions. This is admittedly a very rough approximation. There are in truth some poles and logarithms in the Mandelstam invariants that are there by unitarity, but I will mostly ignore them for now, and we can discuss in private how you can reinstate that. Good, so let's see what you get by alpha prime expanding here and integrating over the punctures of the Arakelov-Green's functions. So on this overview slide, I want to do some name dropping for the function spaces in which you will find yourself as you integrate out the punctures. So I will keep the surface fixed. So I will keep the moduli or period matrix entries as unintegrated for the moment and tell you which kind of modular objects you will get. But let's also look at the open string side, where you restrict the Arakelov-Green's function to the boundary of the open string worldsheet. So there, for open strings at tree level, integrating the punctures gives you multiple zeta values. I guess you all know the Riemann zeta value with a single subscript. And here is a multi-argument generalization thereof, which is really a prominent object in number theory. So the multi-zetas, you really need multi-arguments from the 5-point function onwards. And for closed strings, it's no surprise that for closed string tree level, you again have multi-zetas, say by looking from the distance at KLT. But now there is a cute selection rule, which you don't see on the spot from KLT. There are many dropouts. The closed string tree level amplitudes, they only have the so-called single valued multi-zetas, where to 0th approximation, you drop the even ones and you preserve the odd ones. And you do more funny things at higher depth. And this may look a little bit like black magic, and I would in fact need a motivic setup to make this even well-defined. But let's gain some physics intuition about what this single valued map is for multi-zetas. Let's recall the prehistory that the multi-zetas come from logarithms or polylogarithms evaluated at unit argument. Imagine you integrate out the punctures one by one, and you go on strike before you integrate out the last puncture Z0. So in this almost last step, you will have polylogarithms, say in open string tree level. And polylogarithms are notoriously multi-valued and have nasty monodromies as you go around the origin or Z=1. And on the closed string side, these polylogs want to conspire to single-valued objects where you need support from the complex conjugates. And this is a way to define what a single-valued multi-zeta is. It's what you can get by evaluating single-valued polylogarithms at unit argument. So there's a single-valued map which commutes with evaluation, so to say, and which gives you a fully explicit construction. You start with open string data, you hit the multi-zetas with a single-valued map, and you get the closed string results for free, for the moment at tree level. And for sure, it's an appealing scenario to get closed string results for free also at higher genus. So that's why we find it essential to think about a higher genus uplift of a tentative single-valued map. To also do this, say, with functions of the modular parameters that you get when you start integrating open string punctures over a cylinder worldsheet, as it occurs at genus 1. So as you go to one loop, the function space of configuration space periods is getting way more interesting, involving, say, elliptic multiple zeta values, elliptic analogs of polylogarithms. And then on the closed string side, there is a beautiful system of non-holomorphic modular forms. So my apologies that the box is getting too small to spell out the names Doker, Green, Gürdogan, von Hoof, and also Doker, Green. And by comparing what you get from the open string case and the modular graph forms on the closed string side, there is a proposal on the horizon to do a single valued map really for the functions of tau that you get after integrating out the open and closed string punctures. So we are also at one loop on our way to get the closed string results for free by throwing suitable operations on the open string side. And yeah, also the closed string modular graph forms have an origin from functions of more variables. So here, these are certain generalizations of single-valued elliptic polylogarithms, investigated by Doker, Green, Piolin, and investigated by Doker, Kleinschmidt, Schlotterer. Okay, there's an obvious question in the air, how this graph goes on for higher genus. For the moment, I can only report on what has happened on the closed string side when all the punctures are integrated out. As far as time permits, I will tell you about higher genus versions of modular graph forms. So these are modular invariants or modular forms, certain modular tensors of non-holomorphic type, yeah, which I believe will have a lot of fun questions and answers that are of equal interest to string theorists and mathematicians. Yeah, so this is a zoo of interesting configuration space periods that you encounter naturally as you perform alpha prime expansions of string amplitudes. And the mastery of these function spaces is essential to get access to low energy effective actions, to do precision tests of, say, S duality of type 2B.
Ali, you have about 10 minutes left.
Thank you, Eric. Good. So I have a couple of details ready on, say, the one loop specific cells of the overview figure. In view of time, I will be rather brief. So what should I tell you about elliptic polylogarithms that arise on the open string side? So this is a natural generalization of the polylogs at genus 0 that Anastasia described for you yesterday. You saw in Anastasia's talk that polylogs at genus 0 are iterated integrals over D-log forms. So the D-log forms being tailored to the sphere. Now at genus 1, you need to find an analog of D-log, which is tailored to the torus instead. And the genus 1 version of D-log, it's in fact an infinite number of integration kernels Fk that can be nicely generated from this Kronecker-Eisenstein series up here. So the elliptic polylogs built from that have been studied in mathematics, and it was a wonderful fit because on the string theory side, these Fks turned out to be the universal currency for correlators in genus 1 cases where you have vertex operators on the torus. So here the Fks were, say, the common fun gadget to both mathematicians and string theorists. And also to particle physicists, this system of elliptic polylogarithms was really valuable to significantly push the research frontier of which Feynman integrals can be evaluated. Of course, there are many Feynman integrals that go far beyond the elliptic reach, but it's definitely a lot of progress to have the elliptic polylogs for, say, sunrise diagrams and alike on the Feynman diagram side. Now, a few more words about the modular graph forms. So for the closed string, you have the job to integrate Arakelov-Green's functions over the torus and also these integration kernels Fk. And both of them are doubly periodic functions tailored to the A cycle and B cycle of the torus. So needless to say, you can Fourier expand in the two real coordinates u and v on the torus. And in this double Fourier expansion, you get lattice sums of the form written down here. And you can interpret this as doing Feynman graphs on the torus. You can interpret these denominators, m tau plus n, as two-dimensional discretized momenta. So these modular graph forms, yeah, they arise from scalar field theory on the torus. And it's an intriguing system of non-holomorphic modular forms. So you have these absolute value squares here for the Green's function. And as you integrate more and more of the Green's functions, you get more and more of these lattice sums. So it's a bit like doing a multi-loop Feynman graph on the torus. Though in string perturbation theory, this is still genus 1. Okay, so this is to give just one sample of how such modular graph functions look like. And there are a lot of surprises, such as how many summation variables do you really need? There are many situations where you can simplify and, say, remove some of the summation variables in favor of a simpler sum in the second line. So there are many relations among these modular graph forms that are far from obvious to the lattice sum representation. This is one of the many reasons that this is an exciting subject to, say, classify the independent modular graph forms. And yeah, further crucial properties are that their Fourier expansion involves multiple zeta values. To the best of what we know, it's just the single valued ones. And since we are dealing with non-holomorphic modular forms, you can expect a really vast space of them, because it's only in the holomorphic world that the modular forms are easy to count. Okay, so there are these modular graph forms on the closed string side and elliptic multiple zeta values on the open string side. And I talked about this idea of a single valued map, which takes you from open to closed strings, which takes you from elliptic multiple zeta values to modular graph forms. So in order to have a chance to do that, you need to have a language that applies a little bit to both of them. And the language that does this job, it concerns primitives of holomorphic Eisenstein series. So both sides are iterated integrals over holomorphic Eisenstein series. I should be really schematic here. But the upshot on that slide is you are well advised to use this language of iterated Eisenstein integrals. This, first of all, exposes all the algebraic and differential relations that the modular graph forms may have. And it secondly builds the bridge between open and closed strings. And it furthermore builds the bridge to mathematics. The master of iterated Eisenstein integrals, at least from our string theory perspective, is Francis Brown, who had a series of beautiful papers on iterated Eisenstein integrals and their single-valued versions. And it's an ongoing process to get the best out of Francis' work. Yeah,
you
so
have about 5 minutes.
These iterated integrals are what helps you to go from open to closed strings at genus 1. And we want to do similar things at higher genus. So let me give you a schematic impression of what modular graph forms at higher genus are, approximately. So you can, again, integrate polynomials in Arakelov-Green's functions. But now you have a lot more integration measures for choice. So now you have a G vector of abelian differentials on a genus G surface. So there is now a combinatorial layer which kind of measure you want to use, in which way you contract the indices I and J that you don't see at genus 1. So the groundbreaking papers on modular graph forms are essentially those up here, where the simplest example has already been studied for a while and used to do impressive explicit checks of S-duality. You can go even wilder and generalize the modular graph forms to tensors, but maybe I shouldn't go into much detail in view of time. But the cool thing to say about modular graph tensors is that you take the most general integration measure that you may reconcile with modularity. And these are auxiliary objects that are super valuable to study the relations between the scalar modular graph forms. So even if you didn't have the intention in the first place to study tensors, it is rewarding to do so nevertheless. So here is one relation to show off among the scalar modular graph forms. And in order to prove it, the only method we know up to date is to use the tensors as an auxiliary object to carry out a brief proof. But who knows what further methods will hit the market as the months and years go by. All right, I have been shamefully neglecting the gravity sector of type 1 superstrings. There are, of course, disk diagrams and cylinder diagrams with closed string insertions, as you study the, say, Einstein-Young-Mills sector in type 1 and all the alpha prime corrections to that. So these are further classes of configuration and moduli space integrals where exciting progress has been attained. So let me go through the tree level version where Stefan Stieberger and Tom Taylor had important papers. So there, the gist is that a closed string insertion in the bulk of the disk can be traded for 2 open string insertions on the disk boundary. More details you find in the reference. And the same kind of integrals over the upper half plane, which is a nice parametrization of the interior of the disk, the same kind of math technology appears in deformation quantization, where there was a really beautiful paper by Banks, Panzer, and Pym, where they applied a variant of single-valued integration, and where you can see that it's similar math in perturbative string calculations and corrections to Kontsevich star products. And yeah, the reason why this is timely is that Stefan Stieberger had a recent paper of doing these mappings at genus 1 to map a closed string insertion on the cylinder boundary to a doublet of open string insertions on the boundary. I'm sorry, I should have said in the bulk of the cylinder for the closed string. Okay, so there's really a lot to do also in the gravity sector of type 1, and exciting progress just happened recently. Good, I'm supposed to wrap up soon. There are so many topics where I feel really bad that I haven't touched upon them. Maybe the most pressing one in view of all the configuration space integrals. I haven't finished the job and I haven't integrated over tau or say the complex structure moduli at higher genus. But you get very close to doing that last integral if you know about Laplace equations and Poincaré series of modular graph forms. And I realized that it's hopeless to go through all these bullet points. My apologies for directly hopping to the last slide. So these are the key messages I would really love to drive home. So you saw in this talk some examples of recent progress on string perturbation theory, focusing on explicit evaluations of massless string amplitudes, ranging from genus 0 to genus 3, 4 points and 5 points. And so much of that recent progress was owed to mixing sources of inspiration on the RNS front, on the pure spinor front, and also getting input from our ambi-twister friends. And you also heard new results on the mathematical aspects of doing the integrals over punctures, where crucial inflow from mathematical ideas has helped a lot. And you may complain that most of this has been at finite order in perturbation theory, at low order in alpha prime. Maybe some of you have missed the impact on non-perturbative physics. And let me mention one aspect about this, which is tied to the non-holomorphic Eisenstein series that you saw in Konka-Wen's talk. The non-holomorphic Eisenstein series at arguments 3/2 and 5/2 is describing the exact type 2b couplings of r to the 4th and d to the 4th r to the 4th. And there are pressing questions of what comes beyond e3/2 and e5/2. And we know one more layer from d to the 6th r to the 4th. And I believe that a good toy model for this function space of the non-perturbative completions in type 2b, I believe a good toy model are the modular graph forms, which are, if you wish, the non-holomorphic Eisenstein series at the integer arguments. So what we have to learn is how to take the most general modular graph form and go into the half-odd integer world. And this will give a candidate function space for the non-perturbative story in type 2b. So that is why I expect a vast impact of this over the next years. But for this, there's definitely a lot of help needed. So I hope that this talk could motivate some of you to join us in all these adventures for the future. I should really stop. Thank you for your patience. That's it.
Let's thank Ali for a beautiful talk. And maybe unmute. So now the floor is open for questions. So Nathan.
I would like some more details about this ambi-twister proposal. Can you say a little bit more about what has been checked and what are the ingredients used for constructing the expression?
Okay, let me try starting from here. Okay. Yeah, so the ambi-twister approach at loop level, it has certain scattering equations for the complex structure moduli that localize you on this degeneration limit, where the diagonals go to I infinity and where the A cycles pinch. And then your genus 3 surface is mapped to a multinodal sphere. So here for 3 loop 4 points, this is a 10-point sphere diagram. And there is a standardized prescription to convert these Bernd-Carrasco-Johansson numerators into a correlation function on the sphere. So we know exactly which 10-point correlator on the sphere we want based on the BCJ numerators. And now the next step is the big adventure, how to reverse engineer which function in generic points of moduli space has the right limiting behavior. What is the original expression that gives the 10-point correlator on the sphere in its degeneration limit? And then I guess that Ricardo, Square, and Yvonne were playing a bit of trial and error games, writing down various modular forms where they know their degeneration limits, and they adjusted the relative coefficient until it really reproduced the BCJ numerators.
But does that claim to uniquely define this? I mean, so it agrees in some limit, but is that enough to uniquely define the 4-point amplitude?
It's unique to the extent that the space of modular forms is unique. I don't know whether this is true or not. And in particular, if you find cusp forms that can contribute here, then these cusp forms cannot be determined from the Noble sphere limit. So to the best of my knowledge, it's not unique, but I hope that one of the authors is in the audience to contradict if necessary.
Thank you.
Hiroshi?
Yeah, thank you. So very nice talk. So, so I have a question about the comparison with S-duality predictions that you mentioned. I guess you are referring to a coefficient of higher derivative terms, such as product or curvatures. And I guess you are yet to do the integral over base Riemann surface moduli, such as tau. So before you do that, how would you make such comparison?
So if you allow me, I will try to answer your question at the level of a 2-loop 4-point example. So this is the chiral amplitude for the open string half. Then you square it to get to the closed string. And by just looking at the polarizations and the momenta, the low energy limit for the closed string is already d to the 4th, r to the 4th. So if you now set the momenta and the Koba-Nielsen factor to 0, then all you have to do is integrate these deltas over the moduli space, meaning you integrate over the punctures that give certain imaginary parts of period matrices, and then you catch the volume of moduli space. So in the low energy limit, it's, if you wish, just the volume of the genus 2 moduli space of period matrices. But the difficulty level goes up as you take the external momenta from the Koba-Nielsen factor, as you pull down these Arakelov-Green's functions. Then it's getting substantially harder to do the Z integral in presence of the Green's function. So at the subleading low energy order, this is d to the 6 r to the 4th, your task is to integrate this Chang-Kawazumi invariant written down here. So one Green's function, as I promised, taken from the Koba-Nielsen factor. This is the unique measure that is non-vanishing along with the Arakelov-Green's function. And after you have integrated the punctures Z and W, you're supposed to integrate this over the moduli space of 2x2 period matrices. And for this, there's a beautiful work by Eric, Michael, Boris, Rodolfo, where they did it using a Laplace equation with respect to the moduli. You can trade this Chang-Kawazumi invariant for a Laplacian plus a contribution that localizes on the separating divisor. So this is a case where the full integral has been done, where the coefficient has been worked out and matched exactly with the predictions from S-duality. So on the S-duality side, this is a function of the axiodilaton along with d to the 6 r to the 4th that obeys an inhomogeneous Laplace equation. Laplace minus eigenvalue of the thing we want equals the square of E3/2. And there is, I think, some work by Green van Hoof where they worked out all the perturbative terms of this S-duality invariant.
And okay. I didn't realize that in these cases you can't actually carry out this integral. And so do you get the coefficient right on the nose?
You get it right, yes. By this paper here, you get it right.
Thank you.
Okay. Are there other questions or comments for Ali? Edward?
I have a small comment just about the genus 3 proposal. I think that the question of whether the holomorphic formula is unique is slightly premature. There's a very fundamental question of whether such a holomorphic formula should exist. That's extremely unclear, at least from the RNS formula. Because, for example, if you integrate over odd moduli, keeping fixed the superperiod matrix, you don't get something holomorphic. There might be some framework that gives a holomorphic formula, but explaining why that is true would be fundamental.
Okay.
Thank you for your comment. Ali, do you have a...
Nothing to add to this. Thank you, Edward.
Okay. Any other questions or comments?
Maybe I can just say from the pure spinor framework, it's also, if you go above the low energy, it's also tricky because then you can start getting the subtleties from the lambda bar poles. So.
Right. So this low energy analysis, it had terms of the B ghosts, which were not too divergent in lambda bars, where say milder regulators were enough to do the job.
Piotr?
Yeah, since you're on this slide, or the one before maybe, with the 3-loop graph amplitude. So didn't Carlos also had a non-zero mode term in his amplitude, like the yi mu that you write? I thought he had a derivative of the propagator in there as well, while in their proposal it appears only in the blue term.
Okay.
So I'm wondering if Carlos' term mixes both the red and the blue, or if everybody thinks it's really just the red term. But it would be better to ask this question to the authors directly, I guess.
Mm-hmm.
Yes, maybe. I think in view of time, we may have to move on, and perhaps this question can be relegated to the Slack channel discussion. So let's thank Oliver again. And we will now move on to the last talk of the day by Lorenz Eberhardt. Lorenz, can you?
Yeah, can I just
share?
override you, Oliver, or how does it work? All right, yeah. Okay.
Okay, please.
Thanks very much. Let me start by thanking the organizers for organizing such a wonderful conference and by giving me the opportunity to speak. So today I want to talk about the question how string theory can achieve some sort of semi-classical sum over geometries. And this talk is based on essentially 2 papers I wrote during the last year. So we all know that gravity should emerge somehow from string theory if we go to large distances. And we also know that the gravitational path integral in a semi-classical approximation includes a sum over all distinct topologies with a given boundary conditions. So even those topologies that do not contain saddles may contribute. So one sort of toy example where this was studied a lot during the last 2 years is JT gravity, where, for instance, if we want to compute the gravity partition function with 2 circles as a boundary, then we need to fill in this geometry in all possible ways. And we really get an infinite number of terms here with higher genus corrections and so on. And we already heard talks about that in the conference. So, but I really want to talk about string theory here. So there are a couple of obvious comments that one can do. So first of all, we only know how to formulate perturbative string theory on a fixed background. So what we usually do is we start with some background and we consider, we study some perturbative string corrections around that background. So, and we have to start with a saddle background, meaning that background has to satisfy some sort of supergravity equations of motion of the effective space-time theory. So, or equivalently, you can say the worldsheet has to be a CFT, otherwise we cannot even do perturbative string theory. So then it's not entirely obvious to me how such a semi-classical sum over geometries that in particular should perhaps even include non-saddle geometries, how should it emerge from some sort of string path integral? And I should also say in this talk, I will just talk about the usual perturbative string theory. I will not talk about string field theory, because I think, yeah, just to keep it a little bit simpler, I'm not sure whether string field theory has something more on that to say. And we can sharpen our question a little bit if we consider the ADS-CFT correspondence, because there we exactly know what the answer should be. So if we fix some asymptotic ADS boundary condition, and we really want to compute the full string partition function, whatever that means, then we should get the full boundary CFT partition function, which we know in principle exactly. And we have, of course, examples of ADS-CFT dualities, which we believe to be exact. So there's no ensemble average or something like that going on. And so, of course, you all know these two examples. And now the question is, how do we reproduce this exact boundary partition function from string theory? Let's suppose we have infinite computational power. What should we do? It's not very clear to me. So something naive we might try, which we would do sort of in semi-classical gravity. We could sum over all the bulk saddles, by which I mean you take all the supergravity backgrounds that have the correct asymptotic boundary condition. You can formulate some sigma model on that and study perturbative string theory on that. And you can compute your perturbative string partition function, which very schematically is some exponential that accounts for the disconnected worldsheets. And then you get the usual sum over genera in that worldsheet theory. That, of course, is not the whole story. There might be effects of order 1 over G strings, such as the instantons. So summing over different saddles is effects of order 1 over G strings squared. And then who knows what we should include as well. So to me, it's very, very fundamentally unclear, given any background, what should be the recipe to compute the string path integral. And we also had this question already in the discussion. So I want to convince you in this talk that this this prescription is very fundamentally wrong, at least in a very specific example. And the fundamental reason why this is so wrong is that if you sum over all the saddles, then you overcount situations. You overcount states, and namely, essentially, you can represent some semi-classical geometries as highly excited states in other geometries, such as some gas of strings. If you take some condensate of many strings, then it can look effectively like another geometry. So you shouldn't sum over all the geometries in some sense. And so there is one example where you can make this very precise. And this is this tensionless version of the ADS3 CFT2 correspondence that Matthias was talking about already this morning. So we have this proposal for an exact ADS-CFT dual pair. And exact, I mean that they're exactly dual, and we have good control on both sides. And the proposal is that the string theory on ADS3 S3T4 with 1 unit of NS flux is the same theory as the symmetric product orbifold. So I would refer you to Matthias' talk this morning for more references and details on that. So now what we can do is to use that correspondence, which we have under good control, put the string on different backgrounds that is still asymptotically the same tensionless ADS3 S3T4. And we can just study what geometries should appear and so on to get the boundary CFT partition function, which we know very well because it's essentially a free CFT if you want. And let me just spoil already the main result. The main result will be that there is no sum over geometry. So in this simple example, and there is some caveats to it that I will explain later, what we simply have is that the CFT partition function is given by the exponential of the perturbative string partition function on any given background. So you can choose your favorite background with the given boundary conditions. So for instance, you say the boundary should be a torus. We want to study the thermal CFT partition function. Then you can take thermal ADS3 and you study the sigma model on that. You compute the perturbative string partition function, take its exponential, and you get the CFT partition function on the nose. So of course, we are very lucky in this situation that there doesn't seem to be any d-instanton corrections that we have to take into account. Usually, of course, we have such things. But the important thing here that I want to underline is that we shouldn't sum separately over the thermal ADS3 saddle and the black hole saddle and so on. So the result will just pick your favorite saddle and compute the string partition function. And all other semi-classical backgrounds will arise as some highly excited string states on the background you chose. So another way of saying this is that perturbative string theory in this tensionless limit is sort of background independent. So you start with some background on which you formulate your perturbative string theory, but then in the end, it's completely independent of the background you started with. You could start with thermal ADS3, the BTZ black hole. You can even start with conical defects and so on, as I will explain later. So that's the sort of main message of the talk. And now I want to get a little bit more into the details of why this is true. So first, I have this disclaimer slide. What is the meaning of geometry in this tensionless limit? So in the tensionless limit means that the string can become very large. It can become as large as the size of ADS3. And so the string states in this tensionless limit typically look something like this. So here I drew the time equal to 0 slice of ADS3, which is a hyperbolic disk. And then the string looks something like this. And it really winds around ADS3 some number of times. So all the string states are very non-local. They're spread over the space-time. And that's even true for the graviton. So even the graviton is represented by a string state that wraps once the boundary. And so you might worry that there is no local notion of space-time because the graviton is such a non-local vertex operator. So I would argue what I understand as geometry here is really the background geometry. So there's one notion of geometry that goes into it, namely the geometry that defines the sigma model. You define the sigma model on some background geometry, and then you study perturbative strings on it. So that's what I mean by geometry. And so instead of summing over geometries, what I really will do is to sum over worldsheet theories, because every worldsheet theory represents one background geometry. So that's the disclaimer. So now I mostly want to talk about the thermal partition function. So let's consider the example where the boundary of ADS is a torus. Of course, I haven't stressed this. I'm considering Euclidean ADS since I want to compute some like analog of the Euclidean gravitational path integral. So let's pretend for the moment that we are in 3D gravity. And in 3D gravity, what we would do is to sum over all the saddles of the three-dimensional gravity theory in ADS3. And all the saddles are very easy to write down. So there is the thermal ADS3 saddle. So in this picture, in all these pictures, the time in the boundary always goes up. So it goes around this cycle, and the time cycle is non-contractible in the bulk. That's the essential feature of thermal ADS3. Whereas for the BTZ black hole, it's exactly the same geometry, but now the time cycle runs around this direction, and it's contractible in the bulk, as typical for a Euclidean black hole. And you can declare any other cycle to be your time cycle, and that gives rise to this sum over this SL2Z sum over Euclidean black holes. After that, you can include some one-loop determinant around these saddles. That's what was done in Maloney and Witten. It turns out that this doesn't give you a very well-defined answer. So there are problems with it, and so people have various proposals of what you should do. So one proposes that you should include conical defects into the path integral. And then we probably should also include these non-saddle geometries as we discussed for the JT gravity in the first slide. So essentially now we want to mirror this in string theory as best as we can. So we can essentially mirror the first two lines here. So we can take the string path integral on all these saddle geometries like thermal ADS3, compute as best as we can the perturbative string partition function. We can also do it on the conical defects. We don't know how to do it on this non-saddle geometries. By the way, the conical defects, you might wonder, they're well defined in this case. Usually conical defects lead to tachyons, but in this tensionless limit, they don't. So these are well-defined string partition functions. Okay, so I will mostly discuss now the string partition function on the first of the geometries, namely thermal ADS3. And the other geometries are very similar. And what simplifies the analysis enormously is that you can actually show, you can prove that the string partition function is one loop exact in the string coupling. So we only have to worry about the genus 0 and genus 1 contribution. And you should, in a slide or two, you should get a sense of why this is true. But you can rigorously prove that. And okay, then we have to discuss first the sphere partition function, which is the leading contribution. And the sphere partition function in string theory is sort of a mysterious object because there is this unfixed Möbius symmetry, and we're not really sure how to fix it. But it should reproduce sort of the on-shell gravity action. So here I will cheat a little bit, and I will just use the gravity result for the sphere partition function. In fact, it's fully fixed by conformal symmetry, so it's not anything super magical. So the sphere partition function is the piece that is proportional to 1 over g string square, which is 1 over g Newton. So that's the on-shell gravity action, which is simply given by this, where tau boundary is the boundary modular parameter of our thermal ADS3, and C is the central charge of the boundary CFT. And as I said, it's not known how to compute that result in string theory. Now there's another subtlety that I think is specific to ADS3. I don't know any other background where this appears. is that in the correspondence with the symmetric product orbifold, we had this parameter n. And n you can think of in some brain construction as being the number of fundamental strings. So we have n fundamental strings and one NS5 brain whose near horizon limit sort of creates the background. So you can think of n as being the number of background strings, but now we're throwing probe strings on top of it. And so perturbative string theory essentially has no reason why this number should be kept fixed. And it was argued already some years ago that in fact, the perturbative string partition function computes the sort of grand canonical partition function. So it doesn't give you the partition function of a single symmetric orbifold, but rather of this ensemble of symmetric orbifolds. So here ensemble just means you sum over all the n's and you include some chemical potential for all the symmetric orbifolds. And there's in fact a very simple simple formula for that partition function, a symmetric orbifold, which is given here. So it's an exponential of a simple sum over the original torus partition function with different modular parameters. The interpretation of that sum is that these are all the possible holomorphic covering spaces of the boundary torus. So this partition function of the symmetric orbifold is expressed as a sum of all the possible holomorphic coverings. And the idea of this correspondence is that these holomorphic covering surfaces are indeed the worldsheet. So that's something that Matthias already mentioned this morning for correlation functions, but it's equally true for these partition functions. Okay, so this is the answer we're aiming for. And now we want to reproduce it on the worldsheet. Okay, so I explained you the sphere. We borrowed from gravity. So until now, we haven't done anything. And I told you also the homogeneous corrections vanish. So the only correction we have to look at is the worldsheet torus partition function. And so we need now the torus partition function, the sigma model that describes thermal ADS3. And that's obtained by doing a Z orbifold of the theory that describes global ADS3. And so similarly, the worldsheet theory is just a Z orbifold of the worldsheet theory of global ADS3. So, and luckily for us, the worldsheet theory that describes global ADS3 was constructed long ago. So it's convenient to use this hybrid formalism of Berkowitz, Waffe, and Witten that Matthias also mentioned this morning. And so we just need to modify it a little bit and include this Z orbifold. So I can also refer you to Matthias' lectures at Strings, where he described all the nuts and bolts of this formalism. So if you want to know what's going on behind the scenes, I recommend you look at these lectures. Okay, so that's the formalism we're using, and you can just use it and compute directly what is the worldsheet torus partition function of that string theory. So I already combined it with the sphere here. If you do it, then you get this relatively simple answer. But let me decode it a little bit for you. So it involves the sum over 4 integers A, B, C, D. These 4 integers are nothing else than, you can think of them as being the worldsheet instanton sectors. So these are all the possible ways how we can embed our worldsheet, that is a torus, inside the target space, that is a solid torus. And we also want that essentially that the worldsheet is very close to the boundary. As I showed you in the beginning, we want that the worldsheet winds the boundary asymptotic. So we're essentially looking from maps from the torus to a torus, and they're characterized topologically by 4 integers. So this is the sum over all the possible embeddings of the worldsheet into spacetime. And then we get this, I included for you this P parameter that we had in the boundary, that was the chemical potential, and you can introduce it on the worldsheet. And it's weighted by this determinant of ABCD. And then maybe the most important part of this partition function is this delta function that Matthias also mentioned this morning in the context of correlators. And what it means is that this worldsheet partition function really localizes in the modular space of Riemann surfaces. And the tau here is the worldsheet modular parameter, and we have this boundary modular parameter also. And the two are not independent. They satisfy, so this worldsheet partition function is only non-zero if they satisfy this relation. And what it means is that the partition function localizes in the modular space of Riemann surfaces to all the covering surfaces of the boundary. So that should ring a bell with you. That's what I told you 3 minutes ago, is essentially the answer we're looking for. We wanted to express the boundary partition function as a sum over all the covering surfaces of the boundary torus. So, and we saw that these covering surfaces, we see now that they're in fact the worldsheet. So now it's relatively simple to just integrate over the modular space of tori because we just have delta functions. So it's far, far easier than what Oliver just told us, what you have to do in the flat space string theory. You just have to integrate over delta functions, and that's, of course, very easy. So now the final result that you get in perturbation theory is that the thermoadius-3 partition function is simply an exponential of that expression. So there are some integers that go of the ABCD because you only have to integrate over the fundamental domain, and so not all integers the delta function not always has to support in the fundamental domain. So you get this very simple expression, and somewhat surprisingly, at least to me, that exactly matches the symmetric product orbifold partition function. So we don't have to tweak anything around. And you can repeat the same exercise for the other backgrounds that I mentioned. So we just did it for thermoadius-3. You can do it for the BTZ black hole. You can even do it for backgrounds that have conical defects in them. And you always find the same answer. The answer that you find is always a symmetric product orbifold partition function. But it's sort of in a non-obvious way. So that only works after combining the sphere and the torus and so on. So it's not completely obvious that this works. And I should also mention again that these equalities are true to all orders in string perturbation theory. And maybe you also know by now why the higher loops are not contributing. The reason that higher genus surfaces are not contributing in this case is that the worldsheet should be this holomorphic covering surface of the boundary. But since the boundary is a genus 1 surface, also the worldsheet has to be cannot be a genus 2 surface, because a genus 2 surface cannot cover a genus 1 surface holomorphically. Okay, so
Lorenz, you have about 5 minutes.
All right, thank you. So these equalities are true to all orders in string perturbation theory. And now I will just be somewhat bold and assume that they're just true non-perturbatively and try to see what that means. So we saw that the string partition function, now it's just the CFT partition function on the nodes. Let's briefly discuss what this means for the Hawking-Page transition. So we know that if we compute the gravity path integral in a semi-classical way, we usually learn that at low temperatures in the boundary, the thermoadius-3 phase is dominating, and at high temperature, the black hole phase, which is in this case, this Euclidean BTC black hole, is dominating. If we do it in this tensionless string theory, instead, the picture is somewhat differently. So we just saw that we can just reproduce the full boundary CFT partition function from using a single geometry. So let's stick, for instance, with this column where I use the thermoadius-3. And however, there's still a phase transition taking place, but now it's a phase transition between different string configurations in that same background. So at low temperatures, the strings that contribute are basically winding once around that circle. So in the beginning, I showed you basically the circle that sits inside here at a constant time. And so at low temperature, strings that wind only once around that circle are contribute. Whereas at high temperature, strings are dominating that wind many, many times around that circle. So that's the dominating string configuration. And there is exactly an exchange of dominance at the critical temperature between these two configurations. And so you could say that the long string on thermoadius-3, exactly from the string point of view, looks the same as the Euclidean BTZ black hole. And that's an instance of the string black hole correspondence. I think that was first written down by Sasuke and Korchemsky Horowitz, and in the 83 context by these people. One thing I should also stress, of course, nobody forces you to use the thermoadius-3 description. You could equally well describe these states like the BTZ black hole. You can also, in the tensionless string, you can describe by the BTZ black hole, where now the strings are winding only once around that circle, whereas the thermoadius-3 from the point of view of the BTZ black hole looks, again, like a highly excited string. Okay, and lastly, I also want to mention that this sort of maybe surprising mechanism gives also an explanation why there shouldn't be a factorization problem in this instance, I think. So we know that the factorization problem basically has to do with that there's an ensemble average in the boundary, so that there are multiple boundary theories, but here we have only a single one, or yeah, I mean this ensemble, this grand canonical ensemble, but still it's not a random ensemble. So to analyze that, we should consider this tensionless string now on some Euclidean wormhole geometry. So since it has to be a set of geometries, the boundary surfaces have to have at least genus 2. So the sort of geometry we're looking at is now this one. times the internal space, of course. And in blue, I drew again schematically 2 worldsheets in that geometry. What you can again show is that the string partition function, so the worldsheet partition function again localizes in the modular space of Riemann surfaces, and it localizes to contributions where the worldsheet either covers the left or the right boundary holomorphically. So essentially, the worldsheet is only here or here after you did the worldsheet path integral. So you could say that all the worldsheet configurations of worldsheets in the wormhole, they cancel out after you do the worldsheet path integral. And with that, you can argue that the string partition function on the wormhole in fact factorizes. So the string wormhole partition function now has a contribution from all the worldsheets covering the left boundary and all the worldsheets covering the right boundary. And so you get exactly a product. So I should mention that the previous part was entirely rigorous. Here you have to make some leap of faith, essentially because there are higher genus surfaces involved to show that. Okay, and yeah, so we just said that the worldsheets essentially cannot enter the wormhole, at least after you did the worldsheet path integral. So you could also say that the wormhole from the string theory point of view just looks exactly the same as a disconnected geometry, because the worldsheet sort of has no way of knowing whether there is a wormhole or not a wormhole. And essentially that leads to no factorization problem because the wormhole partition function exactly factorizes. And again, there's no need to include the wormhole and disconnected geometry separately. You can just stick with your favorite geometry, compute the string partition function, and you get the full factorized exact result. All right, that brings me to the end of the talk. So let me just flash some lessons in front of you that you should take home. So the first I really want to emphasize is that this tensionless string is sort of very useful to explore quantum gravity in the opposite regime we're usually talking about, namely at very short distances, which is very far away from the semi-classical regime, which is captured by supergravity. So it, of course, would be very nice to sort of interpolate between the two, but I don't know how to do that. The worldsheet theory of this model simplifies enormously, mostly because of this localization in the modular space of Riemann surfaces. And so perturbatively, at least, it's under very good control. And hopefully also non-perturbatively, we heard Matthias is looking at boundary states and so on. So maybe we will get some update on that soon. The natural ensemble of the duality that is described by string perturbation theory is the grand canonical ensemble, which sort of allows us to probe all these sort of black hole phases. We also saw that the tensionless string is essentially background independent. It doesn't matter on which background you start, you always find the same answer, and you will not need to sum over different geometries. And finally, I argued that there is no factorization problem at all because the string partition function on the wormhole manifestly factorizes into the left part and the right part. Thank you very much for your attention.
Okay, well, let's thank Lorenz for a very clear talk. And now the floor is open to questions. So there is one from the node at IAS. I don't quite see who it is. Please go ahead.
Given what you have shown here and the fact that if you perturb away from the orbifold point, that corresponds to a perturbation near the boundary, if I understand correctly, would you say this is an argument in general or not? That even if you perturb away, you would have this feature?
Sorry, what do you mean perturbation near the boundary?
Well, when you add the vertex operator,
yeah,
that takes you away from this orbifold limit, that's some operator you insert on each of the boundaries of the wormhole separately. Would reduce to.
Why are you saying so? So the vertex operator is essentially just well, it's one specific vertex operator you can construct, I guess. I haven't tried to do that. But do you think there are two because you can like independently?
Well, you have one at each boundary. Suppose you have a wormhole, so there.
Yeah, perhaps.
One at each boundary.
Yeah, I'm not sure whether you can. So, for instance, for the T4 moduli, I don't see that you can choose them differently on both boundaries of the wormhole. Maybe you can do that, but I'm not sure. It would be interesting.
Alejandra?
Hi, Lorenz. Thanks for the nice talk. I think, yeah, I have many questions, but I'll ask one, and then if the organizers allow me, I'll ask some more after other people go around. But one question I had, from the symmetric product point of view, how much did it matter that you said T4? It feels like if you just say like, okay, I have like this this grand canonical partition function for symmetric products, you could prove that it would never admit like a black hole fairy tale like expansion, that it has to be organized in a way like in terms of this, in a way that you would interpret it as a single like geometry.
Yeah, I partially agree. So of course the black hole fairy tale was mostly done for the elliptic genus. The elliptic genus protected, as you know, so there should be a fairy tale for that because you can go to the semi-classical gravity regime. Okay, so other geometry.
In terms of modular forms, that if you can write this as a, like, are you basically telling me that the partition function of the symmetric product on T4 cannot be written as a sum over images?
Okay, I'm not sure whether I would definitely say that because of like, I mean, of course, there might be some way of writing it in that way. So I can't guarantee that there won't be a way. But at least the natural thing that comes out from the dual string theory is not a sum over modular images.
Amir?
Yes, hi. Thank you, Lorenz, for the nice talk. I just have a quick question about the sphere partition functions. You mentioned it's kind of a mysterious object because it vanishes on shell because of the infinite volume of the SL2C group, the Mobius group. And so I was wondering, is the contribution on the sphere partition function that you use, is it the boundary term? I mean, it vanishes modulo the boundary term, as I should say, but I'm not sure if it has a proper derivation in string theory. So I was wondering if you can just give more information about that particular point, contribution to the sphere partition function.
All right. Yeah, so there are essentially, the first point is that the sphere partition function, if I would compute it in gravity, then what we usually do is the holographic renormalization procedure. And we know, of course, that there is a conformal anomaly that, so it's only well defined after you give me a boundary metric. Yeah, so I'm also not sure whether you can make a meaningful derivation of that in string theory. Perhaps you can. So yeah, essentially there are two infinities that somehow perhaps, like the usual argument is there's the target space divergence and the group divergence. So yeah, actually it's something I'm thinking about. So, but I haven't definitely.
I can email you. Yeah, definitely. Oh, okay, thanks.
We can discuss on Slack.
Absolutely.
Edward?
I just wanted to make an attempt to, possibly it's useful to restate what you said this way, although I'm really just restating what you've said. In string theory, we think there's topology change. So you can make continuous transitions from one topology to another, sometimes on shell, and then we understand it, and probably much more generally off shell, which we don't really understand.
Mm-hmm.
And since you're doing an exact path interval, starting with one saddle, that means it would have to include the information of any other topologies to which you could make a continuous transition, meaning that they're actually in the same sector of field space in string theory. So your results are showing that for this theory, apparently all the topologies are in the same sector of field space. There's complete topology change between all of them.
Yeah, I agree, but it wasn't clear from the onset, to me at least, that it suffices to do a perturbative string path integral on one geometry that reproduces all the others.
Well, I agree, but
I agree with that.
The result can be taken to mean that off-shell, we don't exactly know what off-shell transitions mean at string perturbation theory, but perhaps they mean that you can make continuous transitions in smooth two-dimensional field theories that aren't necessarily conformal. That's a guess for what off-shell transitions mean. So your result might be interpreted as a suggestion that all the saddle points are continuously connected via non-conformal 2D field theories.
Yeah, sounds more or less reasonable to me. Yeah. At least in this instance.
Ofer?
Hi. So do you expect any of these features to survive to k bigger than 1?
Yeah, so that's the usual question. So many won't, I'm sure. So some perhaps will. So, okay. I can tell you the ones that probably won't, and maybe then there are some that remaining that will. So the technical ones that won't is, for instance, there's no localization in moduli space. That's very well known. So of course that like all the perturbative control just goes completely away as soon as you go to k bigger than 1. The other thing so the strict like any geometry goes also cannot be really true because, for instance, at least if we go to a conic defect, it's not well defined as soon as you go to k bigger than 1 because of the tachyon. So starting from one loop, all the moduli space integrals will diverge. So that is certainly not the case. And I think also this Givian-Kutasov-Sever Rabinovici paper shows that if you go to k bigger than 1, then the black hole is should be essentially separately included, and it's not representable just by long string state. So yeah, I think most of the features will go away. Also, there should be d-instanton contributions. I think I don't understand why they're not here. Yeah, so essentially all the things go away, I think, but probably some features maybe. Yeah.
Ashok?
Yeah, so I have a general question. I mean, about the general lesson you can draw from here. In string theory, there are also axion-like fields, and often the coupling to these axion-like fields come from non-perturbative saddles, right? The perturbation theory is insensitive to the axions. So do you expect that somehow summing perturbation theory, you can recover the dependence on the axions, or do you separately need to include these non-perturbative saddles?
Yeah, I don't know. So in a general background, I don't expect that to be true. So in this background, it's, yeah, I haven't looked at this, what the coupling means in this background. But in a general background, I don't think that there's any reason for this to be true.
Yeah, I mean, specifically the d-instantons or Euclidean d-branes, they have specific axion-like coupling, which is not present in the perturbation theory.
Yeah.
Okay,
yeah, I haven't looked at d-branes, yeah.
Yeah, let's have one last question by Kostas, and then we'll close this session.
Hi, thanks for this nice talk. Do you think the results extend to Handel bodies?
Yeah, so I actually looked at this because it's very similar to this wormhole story. And yeah, so it does extend yeah, so there are some things I can't really prove because just by technical obstacles are kind of big, because this hybrid formalism becomes very difficult if you go to a higher genus, and you need to go to a higher genus. Yeah, so you can prove this localization essentially fully. So this the fact that the Worldsheet path integral localizes the modular space of Riemann surfaces, that continues to hold true, but I don't know what the actual value is. So I just know that there's a delta function in the modular space. I don't know if you integrate over it what the value will be that comes out. So that's essentially the status. But I think it's very natural that it continues to be true.
And is there a hope to do it for Lorentzian rather than Euclidean geometries?
Yeah, but the question is what you want to compute. I mean, not partition functions, I guess. So yeah, maybe you can compute some scattering amplitudes. Yeah.
Correlators.
Yeah. Yeah. But I think it's doable. Yeah.
Okay, well, let's continue any further discussion in the Slack channel, and thank Lorenz again for a beautiful talk.
Thank you all.
So if there are further questions, people can stay online. I'm not going to kick everybody out.
Okay.
Yeah, just talk, whoever wants to talk.
I just want to repeat Alejandra's question. I'm very, very puzzled how this is consistent with the fairy tale interpretation of the elliptic genus. It sounds, if you're right, it sounds like that's just a mistake.
No, I don't think it's a mistake at all. Let me try to clarify. So if we're looking at the elliptic genus of the K3 symmetric orbifold, then we know that there's a marginal deformation of the orbifold. And if you go to finite distance in modular space, then you go to a regime where you have a semi-classical gravity dual. So, and since this elliptic genus is protected, you could, let's argue from this point in modular space where there is a semi-classical gravity dual, where we should write the elliptic genus as a sum over different over modular images. But now, since it's protected, you can of course also go to the tensionless limit, and then the tensionless limit, it still has the same form. But I just don't think that this sum over modular images in the tensionless limit has some direct bulk interpretation. It's just because they're connected by some marginal information.
So, but then it's very confusing to me. When should we and should we not sum over geometries? You're saying it seems to depend on what geometry we're working, or what regime we're working.
Yeah, we just know the two. So we know the extreme regime where we have supergravity, we know very well. And there we absolutely should sum over geometries, like we do in super-mills and so on all the time. But now what is in between, it's very murky to me, I don't know. And now there is this kind of clear spot that I understand again is at this tangent limit where you shouldn't sum over geometries. Or if you want, there is some emergent sum over geometries coming from the long strings. And what happens in between, I don't really know. I
Yeah,
guess
I
there
mean,
has to be some continuous transition between the two.
I don't see how the two options are continuously related.
Yeah, I mean, there has to be some continuous transition between those two extremes. Yeah, yeah, you can just talk. I think it's very informal.
So, I mean, in a sense, I mean, you can interpret it as having already summed over geometries just by the fact that you've summed over Worldsheet topologies.
Yeah, Worldsheet topologies, but not target
Yeah,
space
but
topologies.
no, I mean, just the fact that you've summed over Worldsheet topologies, you've implicitly already summed over geometries in target space.
Why is that?
There are some hints of this in some early work by Zeitlin when he was computing the path integral over the Worldsheet path integral in the dilute gas approximation, where you basically consider a handle operator approach to represent the Riemann surface of high genus, and then you assume that the handles interact weakly, and then you can sum these handle operators, and then you see that the sum actually can be rewritten as a path integral over metrics. So the sum is already containing the path integral over metrics that you expected to see, so you don't actually need to put it in by hand.
Yeah, I mean, that's...
And there are strong indications that this holds more generally.
Really, but what would you expect if you take the string partition function on ADS5 and somehow resum it, that you get the full answer?
Yeah, because it should be independent of the background, right?
Yeah, but it's not.
This is just... Yeah, so this is just I mean, this actually wasn't my question. This was just sort of just to mention something from the literature. My actual question was...
If you can put the paper in the chat, that would be great.
Yeah, sure.
Later, yeah.
I'm actually also doing some related work with Dieter Lust and Gerd Wally that we hope will appear soon. But anyway, my actual question was, suppose that you deliberately integrate, instead of integrating over moduli space, you integrate over Teichmuller space. So you deliberately overcount.
Mm-hmm.
I'm wondering if you can undo this overcounting with an appropriate Faddeev-Popov determinant in the corresponding boundary theory. Are there any hints that might be possible?
I'm not sure. If you just integrate over Teichmuller spaces, you will of course get the divergent answer, right?
Yes. And my question is whether this overcounting can be sort of reinterpreted in the CFT and absorbed into as a symmetry in a corresponding target space, so that you can remove it by an appropriate Faddeev-Popov determinant.
I don't really understand how you could remove it in target space, because in target space you already did your moduli space integral, so you already got infinity. You somehow have to remove it before.
No, I mean in the CFT path integral.
Yeah, so yeah, the only comment I can make in this instance is that something very vaguely like what you're saying happens, is that if you have the Worldsheet partition function, then it involves the sum over ABCD. Now you're supposed to integrate it over the fundamental domain. And these ABCDs, they transform on the modular transformation. So what you can do is to extend the integral over the fundamental domain to, in this case, a strip. So it's only the Schottky version, but and instead sum over less integers. And that's essentially why you get less integers in the end. So that's very vaguely maybe. But yeah, I'm not sure whether something like what you're saying can be done more generally.
Okay, thank you.
Thanks.
Lorenz, I had a question. Thanks for the nice talk. I'm a little confused about the use of the word perturbation theory. So, I mean, the fact that you're getting the boundary symmetric product for all values of n suggests, I mean, the intuition would be that you have macroscopic strings in the bulk. also for all n.
Yeah.
Right. I mean, Q5 is 1, but Q1 runs over everything. So how are these two things squared? Are you really doing perturbation theory? Meaning, in your calculation, are you at all points of time following the rules of conformal field theory, or is there anything new compared to the usual?
Yeah, so there is some mild amount of cheating involved. So let me explain you. First of all, okay, basically everything that involves this cheating comes from this grand canonical ensemble.
Mm-hmm.
So the cheating that is involved. So first of all, I'm using perturbation theory, but I'm trusting it beyond the regime where it's usually applicable.
Yeah,
so
yeah, that's why I asked the question. Yeah. Mm-hmm.
So yeah, so okay, that's the question. So yeah, you compute this result, you get it honestly in perturbation theory. So yeah, the thing in the box, but then I think it's kind of natural, since you get an exact agreement, that you would trust this result also beyond perturbation theory. I mean, it's very hard for me to believe that you should somehow deform that result, but then add some other contributions that undo this deforming or something. So yeah, so I fully agree that this is beyond what you would usually trust perturbation theory, because there's certainly back reaction. If you have these long strings, then you would usually think that there's back reaction. In a sense, there is, because you see that it's equivalent to the black hole. So there was back reaction, but somehow the CFT gives you the exact answer. I have not a super good reason why that is the case. That's the question.
I see, but calculationally, nothing. The whole calculation follows the rules.
Yeah, the only cheating that I mentioned before involves the sphere partition function. So the sphere I'm putting in by hand, and you have to put it in slightly like there's slight subtlety how you put it in by hand, just because you get this. I mean, you get this grand canonical ensemble, so there's not a single central charge in the boundary. So I was telling you here that the sphere is here. The sphere is proportional to the central charge. So the sphere is computed in the sort of canonical ensemble, if you want, and the torus in the grand canonical. So you first have to translate the sphere into the grand canonical ensemble, and then sort of like mix it with the torus. That's why I wrote here the sphere plus torus. You might wonder why the sphere is here. So yeah, they sort of interact.
A related question was, how should I think of G string in this calculation? Is it strictly 0, or should I think of it as asymptotic?
Good question. So essentially P is G string. So P that appears here is the, sorry,
this P here, yeah.
P is the chemical potential of the grand canonical ensemble. That's essentially G string. You might complain about this because this is a torus partition function. And so you would expect G string to be not appear here. But in fact, so this P is exactly the 0 mode of the dilaton, so it's what you would call G string. And in this case, you can show that this just counts always it weighs exactly all worldsheets by the degree of the covering map.
So this is like this old story of Givon and Kutasov and Seiberg.
Yeah, more or less. Yeah. I agree. That's more or less. I mean, it's different background and so on, but yeah. Right. So P is essentially the string coupling that appears here. And so actually you can't put it too big. If you put it too big, then there's some Hagedorn transition that happens. So you have to be careful.
I see. Sorry, just one last question. So P is G string, not 1/n.
Yeah, I think if you do some Legendre transform and go back to the canonical ensemble, then like the saddle point sets your G string to be something 1/√n.
Okay. Yeah. So the intuition that you should stop trusting this at when the number of strings is n is, it's still correct, but if you just do it, then you get the whole answer.
Yeah. I mean, I haven't looked at correlation functions in this framework. So there's this Kim and Parati paper that I mentioned, and they give a framework of how to compute correlation functions in this framework.
What do you mean by n?
N is the n of the symmetric obifold, number of copies in the symmetric. It's the analog of the n in Spurier-Mills.
But to even talk about this P, you had to go to the grand canonical ensemble.
Yeah. And
so
like
P
the usual
Legendre dual to n.
Exactly. Yeah, that's right. So I think like the usual picture is that G string is something 1/√n. So you have to do the Legendre transform back to the canonical ensemble to see that.
Okay.
Can I ask?